These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. In this video, I'm going to be talking about scientific notation. Scientific notation is a trick that mathematicians use for writing down very big or very small numbers. So to give you an example, you might have already seen some examples of scientific notation, but let's say we had, I don't know, let's say this number, 800, whoops. Here we go. 839, 1, 2, 3, 1, 2, 3, 1. Okay, I hope you'll agree. This is a big number. I could make a number even bigger than this, but this is a pretty big number. How could we write this down in scientific notation? You can see it's kind of a pain to write down the number the way I wrote it, but in scientific notation it would be written as, let's see, 3, 6, 9, 12, 15, 18, 21. Get that right? 3, 6, 9, 12, 15, 18, 21. It would be written as 8.39 times 10 to the 23rd. And I think you'll agree this is just a more convenient way to write the number. Here we have this number. It would be kind of a pain to write this down. So this is just a more convenient way to write down a big number. How did I know this was the right way to write it? Well, that's the whole point of this series of videos, or this video. In this video, I'm going to be talking about how to convert regular numbers into scientific notation and vice versa. But the basic idea is not actually all that tricky. This notation means take this number and shift the decimal point 23 places to the right. And if you do that, you would get this big number. To give you another example, how about this? Now, this is a very small number. This is a tiny, tiny fraction. This is a small fraction. So this would be kind of a pain to write down, but in scientific notation, it would just be 3.7 times 10 to the 5, 6, 7, 8, 9, 10, 11, 12, 13. I think that's 10 to the negative 13. Did I get that right? 6, 7, 8, 9, 10, 11, 12. Okay. Now, how do I know this is the right way to write it in scientific notation? Well, again, that's the whole point of this video, to show you how to go back and forth between normal numbers and scientific notation. But the basic idea is not very complicated. This notation means take the number 3.7 and then move the decimal point 13 times to the left, in which case you would get this number. All right, well, maybe now you can see why scientific notation is helpful, because it lets you write down numbers that would normally be inconvenient to write in a convenient notation. Normally it's inconvenient to write a very big number or a very small number because it takes up so much space. But these ways of writing the numbers take up much less space. Basically, you can see the idea here is, rather than writing out all the decimal places, we can just say how many decimal places there are, roughly speaking, as a power of 10. So the power of 10 is just basically, roughly speaking, telling us how many decimal places there are, or more exactly, it's telling us how many times to move the decimal point. So we don't actually have to write out the number with all those decimal places. So when is scientific notation helpful? Well, if you're just taking a math class that covers scientific notation, it would be useful to understand that topic. But scientific notation is often applied in science, say, where you might say chemistry or physics, where you might be dealing with very big or very small numbers, or any situation where you have very big or small numbers, scientific notation can be helpful. I guess what I mainly have in mind here is I'm making this, this video as a preparation for people that are taking a physics class. But the truth is, anybody who needs to understand scientific notation better hopefully will benefit from these videos. Okay, so let's start going over that information. By the way, I'm intending this video for people that find this topic to be difficult, so I'm going to go pretty slowly and repeat myself a lot. If you don't find this topic to be that difficult, then this is probably not the best way for you to learn the topic. In fact, if this is pretty easy for you, you might have already figured out all you need to know about scientific notation from the two examples I just gave you. But if this material doesn't come quite so naturally to you, well, that's the point of the rest of the video. I'm going to go through the material now more slowly and explain some reliable methods for using and converting scientific notation. All right, so what are we going to be covering in these videos? First of all, I want to give you a basic, relatively brief understanding of some of the very basic mathematic ideas that underlie scientific notation. We won't go into very great detail there, but just to give you a basic feel for it. Then we're going to talk about how to convert from regular notation into scientific notation. And vice versa. That's maybe the most important skill we're going to go over, how to convert numbers from regular into scientific notation and vice versa. Then I'm going to talk a little bit more about the interpretation and meaning of scientific notation. How to interpret and compare numbers in scientific notation. That might sound a little touchy-feely, but I think that's very important. You're going to be working with a lot of scientific notation if you're going to be studying science, say, and you don't want to just be treating the numbers as if they were like, I don't know, objects that you don't know the meaning of. You want to have a feel for what scientific notation means. So I think this is an important part of the videos. Again, we're not going to go into any deep philosophical matters here. We're just trying to get a basic beginner's understanding of how to interpret numbers that are in scientific notation. So these will be first two things. Then we're going to talk about how to use scientific notation on a calculator. That's an important skill that pretty much everybody is going to need. And then this is the point where maybe some of you who might be in a hurry might just stop right there. Then the last part is going to be how to do calculations with scientific notation without a calculator. So you can see why I said this part is kind of optional, so to speak. If you intend to always have a calculator with you for the rest of your life in any situation where you ever need to use scientific notation, well, then maybe it's not so necessary to know how to do calculations without a calculator. On the other hand, if you have the time, I think most of us might occasionally be in a situation where we don't have a calculator handy and we want to do a calculation with scientific notation, or particularly you might have to take a test where you're not allowed to use a calculator, or take a standardized test like the MCAT where you're not allowed to use a calculator. So I expect some of the students that would benefit the most from this section of the video are people that are preparing for the MCAT and other standardized tests. If you're preparing for the MCAT, it's very important to be able to do calculations in scientific notation without a calculator, and I'm going to go over that in this portion of the videos, in this portion of this video. Okay, and I think those are the main topics that we're going to be talking about here. Now, you might have noticed, if you've looked at the information about this video, that this video is turned out to be pretty long, right? What is it? Turned out to be 5 or 6 hours, maybe more now. So 5 or 6 or 7 hours. I haven't put all the different pieces together yet, but I know it's come out to be pretty long. You might think, gee, why should I invest so much time in scientific notation? Well, the answer is, first of all, the answer to that is because you're probably going to be using scientific notation over and over and over and over and over in the rest of your academic career, and then maybe possibly in your practical life in your job, depending on what type of technical field you go into. So it really does behoove you to get very comfortable with scientific notation. You're going to be using a lot of scientific notation over and over if you're taking science classes. And you want scientific notation to be boringly easy for you. That's the goal of this series of videos. That's why this video is so long. This video is so long because I want to help you learn to find scientific notation boringly easy and obvious. And that's well worth putting in, I don't know, 5 or 6 or 7 hours, because that should pay off in many dividends as you continue to use scientific notation over and over and over in the rest of your academic career. So that's the reason why this is a long video series, and that's why I think it's worth putting in that time, because scientific notation is so important and so fundamental for many other topics. When you're working on a hard subject, you don't want to have to stop and think about the scientific notation. You want to be able to focus on that hard subject. So I think it's well worth the time to really master this material. But as I might have said earlier, maybe putting in this much time is really only necessary if you find this material to be somewhat challenging or difficult. If you don't find scientific notation to be a challenging or difficult topic, you could probably just read what your textbook has to say about scientific notation, and then you might be fine right there. So that's fine. Not everyone has to watch these videos. If this is an easy subject for you, well, go ahead and learn about it from your textbook. But if you're having some trouble getting a feel for scientific notation, or if you find yourself making lots of careless mistakes, or if you're not really sure how to interpret or understand numbers in scientific notation, then I think it's well worth putting in a few hours to really nail this subject down, so that then you can build on this knowledge when you're working on harder topics later on. By the way, keep in mind that there is a table of contents in the info box for this series of videos. So if you ever get to the point where the video is becoming so boring that you can't bear it, and you want to move on, you can always maybe use that table of contents to try to move ahead to the next topic. But I'm not going to try to avoid being boring. I think boring is good. The goal is for you to learn this material so well that it becomes boringly easy. Obviously, if this material is already boring for you, there's no point in you watching the videos. But most of the people watching the video now are probably people that are still having some trouble with scientific notation. Well, I hope that you all get to the point where you're finding these videos to be very boringly easy. But you can always use the table of contents if we spend too long on one topic and you want to skip a topic or move ahead to another topic. By the way, perhaps I should mention that I recorded some of the parts of this video in a different order than they appear in the video. Some of the parts of this video got rearranged as I decided to put some topics in front of other topics. I just wanted to mention that, so sometimes during the video it might seem like I've forgotten that I've already mentioned a topic previously. Well, that's the reason for that. Well, the first thing we should do is review how exponents work, because you can see that scientific notation is based on the use of exponents. you know what this means? Hopefully you know this means 3 times 3 times 3 times 3. 3 multiplied by itself 4 times. So write down what this means. That means 3 times 3 times 3. 3 multiplied by itself 3 times. This means 3 times 3. So the exponent tells you how many times to multiply by the base. This number up here is called the exponent, and the number down here is called the base. So here the exponent was 4 and the base was 3. And then in this example, the exponent was 3 and the base was also 3. And then in this example, the exponent was 2 and the base was 3. Here's the first example that's a little bit tricky, but maybe you can figure out that this just means 3. We just have a single 3 now. But what about if I write 3 to the 0th power? What does that mean? Perhaps you've already learned what that means. Here's a good way to figure it out. Well, let's see. Couldn't this up here have been written like this? And this could have been written like this, because multiplying by 1 doesn't change the value. I think if I put those 1s in each of these, that now establishes a pattern. So what should 3 to the 0 be? It should now be 1. Notice here we had 1 multiplied by 4 3s. Here we had 1 multiplied by 3 3s. Here we had 1 multiplied by 2 3s. 1 multiplied by 1 3. Well, now here we have 1 multiplied by 0 3s. So all we have is the 1. So 3 to the 0th power equals 1. You might have thought that 3 to the 0th power would be 0. That might seem intuitive, but it turns out that's not the way it's defined. 3 to the 0th power is not 0, it's 1, and I just tried to give you a little argument for why that actually makes good sense. So, for example, what would be 4 to the 0th power? Well, by the same argument, that would also be 1. What would be, say, 5 to the 0th power? That's also 1. What's 32 to the 0th power? That's 1. So anything to the 0th power equals 1, not 0. Almost anything. 0 to the 0th power is undefined, I think. But besides that, anything to the 0th power equals 1. Anything to the 0th power equals 1. So that would give us all of these. All right, so keep in mind then what's x to the 0th power? It's 1, not 0. And here's an argument for why it makes sense for something to the 0th power to equal 1. Maybe I'll give you 1 or 2 other arguments for why that makes sense. If you start in this row, notice that how would you find 3 to the 3rd? You could take this and divide by 3. Do you see what I'm saying? If you take this row and divide by 3, I'm going to get rid of the 1s to show that I'm giving you a different argument here now. If you take this row and divide by 3, you would get this row. If you take this row and divide by 3, you would cancel out one of the 3's and get this row. If you took this row and divided by 3, you would cancel out one of the 3's and get this row. So, how would you find 3 to the 0th, which is the next row down? Well, if we're following the same pattern, we should divide by 3 again. And that would again, now 3 divided by 3 would just leave you with a 1. Let me give you one other example here. Notice that 3 to the 0 is kind of our starting point, right? I'll put back these 1s here. 3 to the 0th is 1. And then say 3 squared would be 1 times 2 3's. When you're doing multiplication, the natural starting point is the number 1, not the number 0. When you're doing multiplication or division, the natural starting point is 1. You can see it would not be natural to start with the number 0 if you're doing multiplication, because then you could never get away from it. 3 times 0 is still 0. 3 times 3 times 3 times 0 is still 0. So when you're thinking about multiplication and division, it doesn't make sense to start with the number 0, because when you multiply anything times 0, you just get another 0 back. The natural starting point for multiplication and division is the number 1, not the number 0. Well, exponents are about multiplication and division, so it makes sense to start with the number 1, not the number 0. So those are a couple of arguments for why it makes sense why something raised to the 0th power should come out to be the number 1, why that's a reasonable definition that the mathematicians have come up with. Well, let's see. A natural thing to ask now is what would happen if we had, say, a negative exponent, say 3 to the negative 1. Well, you can actually use the patterns I was talking about earlier to figure that out. Remember I said that you could get this row by dividing the previous row by 3. This divided by 3 gives this row. This row divided by 3 gives this row. This row divided by 3 gives this row. So the next row down we should get by dividing by 3 again. So this row would be 1 divided by 3, or 1 times 1 divided by 3. Maybe a slightly better way to look at that is you could get this row by multiplying the previous row by 1/3. This row multiplied by 1/3 gives you this row. This row multiplied by 1/3 gives you this row. This row multiplied by 1/3 gives you this row. This row multiplied by 1/3 gives us this row. So following the same pattern will allow us to figure out the negative exponents. This row multiplied by 1/3 gives you this row. And then following that same pattern, this row, if you multiplied by 1/3 again, wouldn't you get this? Because 1/3 times 1/3 is 1/3 squared. So to the negative 3 power, that would give us this. I don't know why I'm putting all my answers all the way over here to the right. So that would give me 1/3 to the 3rd. And one more example. Do you see how each row here is the previous row multiplied by 1/3? If you took 1/3 to the 3rd and multiplied it by 1/3, you would get 1/3 times 3 times 3 times 3, which is 1/3 to the 4th, which is what we got here. Okay, so hopefully now we're starting to see what negative exponents mean. By the way, in order to make this pattern come out nice, we could have written this row like this, right? We could have said 3 to the negative 1st power is 1/3 to the positive 1st power, just like 3 to the negative 2nd is 1/3 to the 2nd power. So what we're seeing here then is positive exponents give you big numbers, and negative exponents give you fractions, very small numbers. What's the general pattern here then? Let's say we had x to the negative y power. Can you write down a pattern for what that is? I hope you gave that a shot. Isn't the pattern this? X to the negative y is 1/x to the positive y. Just like 3 to the negative 2 is 1/3 to the positive 2. Or 3 to the negative 4 is 1/3 to the positive 4. So here's the definition of negative exponents to go along with our definition of a 0 exponent, which is 1. Okay. We tried to explain that these are reasonable definitions for negative exponents because they kind of continue the same pattern in a sense that we had up here with the positive exponents. Every time we reduced the exponent, it was like multiplying by 1/3. Well, we could continue that pattern down here to the negative exponents. So for practice, I'd like you to fill in this table, write down what all of these mean. I don't want you to calculate actual numbers. I don't want you to figure out, gee, this is equal to 60, that this is equal to 16 or whatever. I want you to write down a table that looks like our previous table so that we're understanding what the exponents mean. Please pause the video and try that. I hope you paused the video and tried that. So the positive exponents are easy. This means 4 times 4 times 4 times 4. This is 4 times 4 times 4, 4 times 4. 4 multiplied by itself twice. Only a single 4. Now we know anything to the 0th power is just the number 1. And then this would be 1 over 4, or 1 over 4 to the first power. And this would be 1 over 4 to the second power. And this would be 1 over 4 to the third power. And this would be 1 over 4 to the fourth power. Of course, we could now calculate actual values for all of these. For example, this line over here is actually what? 64, right? And this line over here is like 1/16. But right now I just want to focus on this pattern for exponents. Okay, so those are some of the key ideas I wanted to review for exponents. In particular, I wanted to give you a better understanding of what a 0 exponent means or what a negative exponent means. Now, when you're working with scientific notation, you're working with powers of 10. So that's what we want to move to start talking about right now. Maybe it would be good for you to actually write out a table here again. Write down what each of these means. I don't want you to actually calculate numbers for these, but write down what these mean like we did in the previous examples. I hope you tried that. This would be 10 times 10 times 10 times 10. This would be 10 times 10 times 10. This would be 10 times 10, a single 10. Remember, anything to the 0th power is the number 1. Now this would be 1/10. This would be 1 over 10 squared. This would be 1 over 10 to the third. There's many different ways we could write these negative exponents. We could also write this as 1 over 10 times 1 over 10 times 1 over 10. Or you could write this as 1 divided by 10 divided by 10 divided by 10. There's a bunch of different ways you can write this out. I'll write it this way, though, just to show the pattern. This is 1 over 10 to the fourth. Now, actually, what actually are these numbers here? If you actually multiply these out, you could do these in a calculator, and you would get that this is 10,000. This is 1,000. This is 100. Obviously, this is the number 10. This is the number 1. So you might notice a pattern here. 10 to the fourth is the number 1 followed by 4 zeros. 10 to the third is the number 1 followed by 3 zeros. 10 squared is the number 1 followed by 2 zeros. 10 to the first is the number 1 followed by 1 zero. And 10 to the 0th is the number 1 followed by no zeros, followed by 0 zeros. In fact, this kind of is just yet another argument for why it kind of makes sense to define anything to the 0th power as the number 1. Now, 1/10 in decimal notation, you can check this on a calculator, and you would get that that would be 0.1. And if we tried to work out this on a calculator, you would get 0.01, or 1/100th. And 1 over 10 to the third on a calculator would come out to be like this, or 1,000th. This is the 1,000th place. 1 over 10 to the 4 would be 1/10,000th. Now, unfortunately, the pattern here doesn't quite match the pattern up above, right? 10 to the third is the number 1 followed by 3 zeros, but 10 to the negative third, there's actually only 2 zeros to the right of the decimal point. 10 to the negative fourth only has 3 zeros to the right of the decimal point. 10 to the negative first has no zeros to the right of the decimal point. So this doesn't quite tell you the number of zeros. I guess it would tell you the number of zeros if you put a 0 here, too. That doesn't change any of these. But it still doesn't tell you the number of zeros to the right of the decimal point, which is in a way, the significant zeros. What the exponents are really telling us is how many times to move the decimal point. If you start with the decimal point over here, then this would mean move the decimal point one place to the right. This would mean start with the decimal point here and move it 2 places to the right, say. Or this would mean move the decimal point 1 place to the left. And this would mean move the decimal point 2 places to the left from where it started over here. Notice that the first time you move the decimal point to the left, you don't actually have to insert a 0. That's why the number of zeros doesn't match the exponents. Okay, that was a little bit of a detour, though. We don't need to go into that in too much detail in order to use scientific notation. Anyway, here, these are what some powers of 10 look like. Now, what happens when you multiply a number times 10? You can check this on your calculator, or you can do it on paper, and either way you'll find that when you multiply this by 10, you get this. Let's multiply that by 10. If you do that on paper or do it on your calculator, you'll get this. And then you can try on your calculator or on paper multiplying by 10 again. Now you'll get this. And if we multiply that number by 10, you'll get this. Do you see the pattern here? If you haven't figured it out yet, why don't you try pausing the video? Try to figure out the pattern. What happens when you multiply a number by 10? I hope you paused the video and thought about that. Well, the answer is when you multiply a number by 10, it moves the decimal place 1 place to the right. When you multiply a number by 10, it moves the decimal point 1 place to the right. Here we move the decimal point from between the 8 and the 2 to between the 2 and the 4. Then we multiplied by 10 again, and that moved the decimal point from between the 2 and the 4 to between, well, to the right of the 4. Now that might be a little bit tricky to see because it might seem like there are no decimal points here. Maybe I should have discussed this earlier. Where are the decimal points here? Where's the decimal point if you don't see a decimal point? For example, suppose I give you this number, 532. Where's the decimal point? Well, the answer is that if the decimal point is not given, that really means there's kind of a hidden decimal point which is to the right of the number. 532 equals 532 and then a decimal point. Or say 69, where's the decimal point in 69? Well, if you were going to write it in, it would actually be to the right of the 9. Or if you had the number 8, where's the decimal point? That's really this number. There's always a decimal point, but when it's to the far right of all the digits, we don't usually write it down. So now going back up to here, you can see we really did move the decimal point, right? We moved it from between the 2 and the 4, and then we moved it to the right of the 4. And then over here, we took the decimal point from the right of the 4 and moved it to the right of the 0. And over here, we took the decimal point from the right of the 0 and we moved it to the right again. And in order to move it 1 place to the right, we had to stick in a 0 as a placeholder. I guess we had to do that in this row as well. Here we were moving the decimal point 1 place to the right, and in order, since there was no digit there already, we had to stick in the number 0 just as a kind of a placeholder. So we can see that multiplying by the number 10 always moves the decimal point 1 place to the right. We also just reviewed where the decimal point is when it's not actually written. There's always a decimal point, and if it's not written, the decimal point is actually hidden to the right of the rightmost digit. Okay, very good. Now, then notice that we could have just as well said 8.24 times 10 to the fourth equals 82,400. Do you see how this just summarizes what we figured out up here? This means 8.24 times 10 times 10 times 10 times 10. 8.24 times 10 times 10 times 10 times 10, multiplying by 10 4 times. Well, every time you multiply by 10, you need to move the decimal point one place to the right. So if you're multiplying by 10 to the fourth, that means you have to move the decimal point 4 places to the right. And you can see that's what we did here. 1, 2. And then for the last two moves to the right, we have to stick in zeros as placeholders. And that would give us this number here. Or if we had, say, 8.24 times 10 to the third, that just means move the decimal point 3 places to the right. And that would have given us this number, 8,240. So now we're starting to see why using powers of 10 is a convenient way to write big numbers, because a power of 10 just tells you how many times to move the decimal point. Multiplying by a power of 10 just tells you how many times to move the decimal point. Now what happens when you multiply by 1/10? Well, you can try this on paper again, or you can try it on your calculator, and you'll discover that when we multiply this number by 1/10, we get this. And what happens when we multiply this number by 1/10? You can check on your calculator that you'll get this. What happens when we multiply this number by 1/10? Then we'd get this. Let's do one more example. Let's take our previous answer and multiply by 1/10 again. And then you'll end up with this. You can confirm all these on your calculator or by doing them by hand if you know how to do that. Okay, so what happens when we keep multiplying by 1/10? Do you see the pattern here? If you don't see it yet, why don't you pause the video and try to figure out the pattern? I hope you gave that a shot. Well, the pattern is every time you multiply a number by 1/10, that shifts the decimal point one place to the left. Multiplying by 1/10 shifts the decimal place 1 point to the left. Here we moved from between the 5 and the 7 to between the 3 and the 5. Then when we multiplied by 1/10 again, the decimal point moved over to the left of the 3. Then when we multiplied by 1/10 again, we shifted the decimal point another place to the left, and we had to insert a 0 to occupy that new digit. And then when we multiplied by 1/10 again, we moved the decimal point one place to the left again and had to add yet another 0. So every time we multiply by 1/10, we're moving the decimal point one place to the left. By the way, another way of saying that you're multiplying by 1/10 is that you're dividing by 10. We could have just as well said that when you divide by 10, you're moving the decimal point one place to the left. Well, do you see the pattern? When you multiply by 10, you move the decimal place one point to the right. And when you divide by 10, you move the decimal point one place to the left. I'll say that one more time. When we multiply by 10, we're moving the decimal point one place to the right. And when we're dividing by 10, we're moving the decimal point one place to the left. You can play around with that on your calculator and confirm that for whatever numbers you like. By the way, of course, all these patterns only work for powers of 10. If we were, say, multiplying by 3, multiplying by 3 doesn't just move the decimal point, it also changes the numerical values. And dividing by 3 doesn't just move the decimal point, it changes the numerical values. So that's the neat thing about the number 10. The neat thing about the number 10 in our number system, the neat thing about the number 10 is that when you multiply or divide by the number 10, the numerical values stay the same and we just shift the decimal point. By the way, if you wanted to, you could have written all these numbers like this. Remember, it's totally optional whether you put this 0 to the left of the decimal point or not. I guess textbooks and calculators generally do put this 0 in. I usually leave it out just because we don't really need it. So then another way to have written this would have been, we could say 35.7 times 10 to the negative 4. What does this mean? Well, this means 35.7 times 1/10 times 1/10 times 1/10 times 1/10, right? This means 35.7. We already learned that negative exponents can be rewritten like this. And I hope it's apparent to you that that's the same as this. I didn't quite spell this out before, but I hope you agree that this number is the same as just multiplying by 1/10 4 times. Well, we know that that just means move the decimal point 4 places to the left. Move the decimal point 4 places to the left. 1, 2, 3, 4. We have to put in a couple of zeros as placeholders, and we ended up with the same answer we already got up above here, because this is what we get when we start with 35.17 and multiply by 35.7 and multiply by 1/10 4 times. So what does it really mean if we say 35.7 times 10 to the negative 3? That means take this number and move the decimal point 3 places to the left, and you would end up with this. All right, so we're starting to see the basic ideas then behind scientific notation. Scientific notation is based on using powers of 10 to tell us how many times to move the decimal point, as I was already kind of sketching out at the very beginning of this video. I hope I've given you then some basic intuition for why scientific notation is based on powers of 10. And the next thing I want to do is just talk about how to convert numbers then between regular numbers and scientific notations. We want to go over how to take a regular number and change that into scientific notation. Or how to take a number that's in scientific notation and change it to a regular number. It's important to know how to go in both directions. And maybe you've already figured out, basically all you have to do is take one of the numbers and move the decimal point a bunch of times. Changing between regular and scientific notation is just about moving the decimal point, and then maybe writing down a power of 10. The basic ideas here are pretty simple, but this is a skill that you're going to be using like a lot just as an ordinary part of doing many types of, say, physics or chemistry problems or whatever type of subject you're studying. So it's important to have a reliable method for doing these problems that helps you to avoid making careless mistakes. What types of careless mistakes might a person make? Well, when someone's in a hurry, they might say move the decimal point to the right when they really need to move it to the left. Or move it to the left when they should really move it to the right. Or they might use a positive power of 10 when they should really be using a negative power of 10, and vice versa. The rules are a little bit harder to remember than you might think because there's really 4 different sets of rules. Why do I say there's 4 different sets of rules? Well, let's say that you're moving between regular and scientific notation. You need to know how to deal with positive powers of 10 and with negative powers of 10. But also then, if you're moving from scientific notation to regular notation, again, you'd have to know how to deal with negative or positive powers of 10. So it really comes out that there's actually turned out to be 4 different situations, and when you're in a hurry, it's just easy to make careless mistakes. So I want to try to give you a method that doesn't rely on just thinking through the intuition every time, like we have so far. A reliable method that just gives you a mechanical way to do these conversions. And all you need to do to use this method is just to focus on whether you're trying to make numbers bigger or smaller. One thing we should review for this then is notice that when we have a positive power of 10, we could think of that as a big number. These are all pretty big numbers. 10 to the 0th power, that's our reference number, that's just the number 1. And then 10 to a negative exponent, notice that when you're using a negative exponent, that's really a way of writing a fraction. I guess that's the main point I wanted to make here. Negative exponents are fractions, or very small numbers. One thing I should have mentioned before, I didn't mention this before, notice that negative exponents don't give you negative numbers. Do you see what I mean by that? Negative exponents don't give you negative numbers. 10 to the negative second, that's not a negative number. It's positive 0.01. So don't confuse negative numbers with negative exponents. I think that's a common mistake that students often make, or a careless mistake. It's easy to slip into. Negative exponents are actually give you positive numbers. They just give you small fractions. Okay, so the main point I wanted to make is when you have a negative exponent, the number is less than 1. And when you have a positive exponent, the number is bigger than 1. I'm going to say that again because that's the basis of the mechanical method we're going to go over. When you have a negative exponent, the number is small. It's a fraction less than 1. When you have a positive exponent, the number is bigger than 1. Positive exponents give you numbers that are bigger than 1. Negative exponents gives us small fractions that are smaller than 1. And 0, 10 to the 0th, gives you the number 1. So now let's see how we can just use that as a trick here for writing numbers. Okay, so let's see here. Let's say that we have, let's see, where do I want to start with this? Say we have this number. Now I want to write this in scientific notation. So how can I write this number in scientific notation? Well, actually, there's something I forgot to mention here. The official way to write scientific notation is to have the numerical portion be between 1 and 10. So to do that here, I'm going to write this number as 8.53. Do you see how that makes this number between 1 and 10? 8.53 is between 1 and 10. And all I have to do now is figure out the right power of 10. Well, how many times did I move the decimal point? Remember, where did the decimal point start? Since it wasn't written, the decimal point must have originally been over here. And then we moved it once, twice, 3 times, 4 times. Am I getting that right? Yeah. I'm just using the comma here to make the number easier to read, although maybe now I'm getting confused by that, so I'll take it out. So we moved the decimal point 4 times, but the question is, then should this be 10 to the positive 4 or 10 to the negative 4? Well, if you really understand the intuition behind the ideas we talked about earlier, you should be able to figure out whether this should be 10 to the positive 4 or the negative 4. But like I said, I want to give you a mechanical way to do that's less prone to careless mistakes. So here's the method. What happened to our numerical portion of the answer here? Let's say that we could write this originally as, say, this. Here's the original number. We didn't originally write the number 1, but we could, because that doesn't change anything. Multiplying by 1 doesn't change anything. So notice that this number here, what's happened to this number is it's gotten smaller, right? 8.53 is smaller than 85,300. So how can the right-hand side be the same number as the left-hand side? Only if this number has gotten bigger. We want this then to be a big number. I want this to be now bigger than the number 1. Well, then I need to use a positive exponent. A positive exponent. And now we're done. Here's the answer. So to write this number in scientific notation, you would write it like this, 8.53 times 10 to the 4th. And the key is these 2 little arrows here. Since we made this number smaller, we must be making this number bigger. 10 to the 4th is bigger than 1. That's how I need to use a positive exponent here. Now, like I said, you don't have to use this mechanical trick. You could have figured out based on common sense the reason this has to be 10 to the fourth. But I'd actually encourage you to learn this trick because it'll let you make fewer careless mistakes and spend less time thinking about this issue when you're in the middle of more complicated problems. Let me show you a bunch more examples of how this method works so that you can get a feel for why I think this is a good shortcut that helps us to avoid careless mistakes. So let's say we had the number 937, and I want to write that in scientific notation. I'm going from the regular number to scientific notation. Maybe the first trick I'm going to use is I'm going to rewrite this as 937 times 1. That doesn't change anything. And then I'm going to write over here 9.37. Why did I write it this way? Because remember, the numerical portion is supposed to be between 1 and 10. Well, this is between 1 and 10. Now I'm going to write a power of 10. How many times did I move the decimal point? Well, the decimal point started here, and it moved once, twice, in order to get to here. But then the question is, should this be a positive 2 or a negative 2? Well, compare the two parts of our answer here. The 9.37 is smaller than the 937 that we started with. It's a smaller number. In order for the overall answer to be the same, then this number has to be bigger than we started with. So the two changes cancel and we still have the same number we started with. Well, then I need to use a positive exponent because I want this exponent to give us something that ends up being bigger than 1. I'm comparing the 10 squared to the number 1. Well, 10 squared is bigger than 1. Hopefully, if I do a bunch of more examples here, if this isn't making sense yet, you'll start to see the pattern. Point 0.00341. Now, let's write this in scientific notation. Well, as a trick, first of all, I'm going to write that as the original number times 1. That doesn't change anything. Now I'm going to write the numerical portion. Remember, the numerical portion should be between 1 and 10. Well, this number is between 1 and 10, right? Then I'm going to write the power of 10. Let's see, how many times did I move the decimal point here? Well, we moved once, twice, 3 times, 4 times. We had to move 1, 2, 4 times. But should this be a positive 4 or a negative 4? Well, it might already be obvious to you whether this should be positive 4 or negative 4 because we've just been doing a bunch of examples and thinking about this. But again, let's keep going over this mechanical method for figuring this out so that you can see clearly what the sign of this exponent is even when you haven't been thinking about this issue for a while. So using the mechanical method, let's see here. Well, notice that 3.41 is a bigger number than the number we started with, right? This was a small fraction, 0.00341. This number got bigger, so I put an up arrow here. In order for the overall number to be the same as we started, this number should be smaller than this over here. Well, how can we make a power of 10 that's smaller than 1? Well, remember, that means that you need to use a negative exponent. As we reviewed earlier, 10 to a negative exponent is less than 1. 10 to a negative exponent gives you a fraction that's less than 1. So here's one of our first examples using this method where we ended up with a negative exponent. And here's the answer. Do you see what I'm saying? Do you see what I mean when I say that we want the numerical portion to be between 1 and 10 when you're using standard scientific notation? For example, you would not want to write it as, say, 34.1. You would not have wanted to write it like this, even though this does represent the original number. This does represent the original number, but it's not in standard scientific notation. The standard scientific notation is when the numerical portion is between 1 and 10. So this correctly represents the original number, but it's not in the conventional notation. I'll cross it out because this is not the conventional notation. Or again, this correctly represents the original number. You can check that on a calculator if you want. But it is not standard scientific notation because the numerical portion here is not between 1 and 10. I don't know if I made this sufficiently clear earlier, but when you write a number in standard scientific notation, the numerical portion is supposed to be between 1 and 10. Oops. So let's write this number in standard scientific notation using the mechanical approach that we've been talking about, which is a way of avoiding careless mistakes. Well, let's see here. The first trick is to rewrite this as the original number times the number 1. We'll see in a second, once again, why adding the number 1 is a useful trick. Now, the numerical portion should be rewritten as a number that's between 1 and 10. So that would be 5.4, right? Because 5.4 is between 1 and 10. You wouldn't want to write it as 0.54, because that number is less than 1. And you wouldn't want to write the numerical portion as 54, because then the numerical portion would be bigger than 10. This is the way to write the numerical portion so that it's between 1 and 10. And then the tricky part is to figure out the power of 10 that we need. Well, how many times did we move the decimal point? Once, twice, 3 times. It can help to actually write down this type of little arrow here, so you're actually counting the number of times we moved the decimal point. To get it from here to between the 5 and the 4, that was 1, 2, 3 times. But should this be positive 3 or negative 3, where here we use the trick we've talked about a couple of times, notice that the numerical portion here has gotten bigger. 5.4 is bigger than 0.0054. So to balance that, we need this portion to be smaller than before. So I need this to be smaller than the number 1, which is kind of its counterpart in the original number. Well, we know that to make this smaller than 1, we have to give it a negative exponent. So the correct way to put this into scientific notation would be 5.4 times 10 to the negative 3. It's a good idea to actually write down these 2 arrows here so that you can keep track of which part of the answer is getting bigger when you change into scientific notation and which part is getting smaller. Let's change this into scientific notation. So at this point, hopefully you're pausing the video and trying each of these on your own. Please pause the video and try this on paper before you proceed. You're going to learn much more from this video if you're trying each of these examples on your own. Well, I hope you gave that a shot. So using our technique, I'll rewrite this as same number times the number 1. This is a multiply sign, right? Not a decimal point. I hope that's clear. So we're going to change the numerical portion into 6.98 because this is now between 1 and 10. And then I can see that the numerical portion here got bigger than what it started at. Therefore, I want the power of 10 portion to be smaller than 1, which I can do with a negative exponent. And how many times did we move the decimal point? Well, this time we only moved the decimal point once. So in scientific notation, this would be 6.98 times 10 to the negative 1st in standard scientific notation. Now, in real life, maybe in this type of situation, there wouldn't be much point to using scientific notation. Remember that the main point of using scientific notation is for dealing with very large and very small numbers. This number is not that small, so maybe it would be more convenient just to write it as 0.698. In fact, usually it would be more convenient to write this as 0.698 rather than writing it in scientific notation. Nevertheless, there's still some situations where it's convenient to use scientific notation, even when the number isn't particularly big or small. So scientific notation is especially useful for very big or very small numbers, but the fact is any number could be written in standard scientific notation, and that's what we did here for practice. Please pause the video and write this in standard scientific notation. I hope you did that on paper. So our trick here is to rewrite this with the number 1. All right, and now I'm going to write this portion so that the numerical portion is between 1 and 10. Well, this would be the way to do that. 8.3 is between 1 and 10. How many times did I have to move the decimal point? Well, where was the decimal point in the original number? At first, we didn't write a decimal point in the original number, but we've discussed that when you don't have the decimal point explicitly written, that really means that the decimal point is to the far right. So we could say the decimal point started here, and then it moved once, twice, 3 times, 4 times. We moved the decimal point 4 times. But should this be 10 to the positive 4 or 10 to the negative 4? Well, here's how we figure that out. This portion has gotten smaller compared to the original number. 8.3 is smaller than 83,000. Therefore, this power of 10 should end up being bigger than the number 1. Well, the way to make this bigger than the number 1 is to go back to using positive exponents. So the correct answer here is 8.3 times 10 to the 4th power with a positive exponent. Now I'd like you to pause the video and write this as a regular number. Did I get this right? Oh, I meant to write it like this. Let's try again. All right, so what I meant to say is, here we have a number that's in scientific notation. I'd like you to rewrite it in ordinary notation. Rewrite this in ordinary notation. Please pause the video and give that a shot. All right, did you notice that this question is a little bit different than any of the problems that we did before? All of the earlier problems that I've given you so far, I've been giving you numbers that were in regular notation and asking you to change them into scientific notation. But this last problem, I reversed it. I gave you a number that was in scientific notation and asked you to rewrite it in regular notation. Were you able to figure out the method for that? Well, here's the way that I would recommend. So I'm going to rewrite this 7, 2, 5. Let's see here. So what are we trying to do here? So I'm going to rewrite this now. Now, since we're writing this in regular notation, we're going to get rid of the power of 10. Or another way of putting it is we're going to change the power of 10 into the number 1. And notice that in order to do that, we would be decreasing this portion. This portion here has changed from a number that's bigger than 1 into the number 1, so it's gotten smaller. That means, therefore, that this portion should get bigger. And how do we make this bigger? By moving the decimal point to the left or to the right. Well, we need to move the decimal point to the right to make this bigger. How many times should we move it to the right? Well, that's what the power of 10 tells us. It tells us to move the decimal point 8 times to the right. So that would give us 1, 2, 3, 4, 5, 6, 7, 8. I'm running out of space here. One, 2, 3, 4, 5, 6, 7, 8. And the decimal point ends up here. And then we can rewrite this so that it looks prettier. We've got 1, 2, 3, 4, 5, 6 zeros. We can put in some commas to make it easier to read. And we end up with this number. 725 million. So this is the first time we've seen the systematic method for taking a number that's in scientific notation and rewriting it as a regular number. So let me review the method that we used here. It should be clear that you're going to be moving the decimal point 8 times. It should be clear we're going to move the decimal point 8 times. The only question is, should we move the decimal point to the left or to the right? Now, you could just figure out, based on kind of the common sense of exponents and powers of 10, whether to move the decimal point to the left or the right. And that's a perfectly good way to figure this out. But I also would like you to learn this mechanical method because, as I've said before, it'll help you to make fewer careless mistakes when you're doing a bunch of these calculations in the middle of a more complicated problem. Well, when you're doing a more complicated problem, you don't want to have to slow down and think about the basics of scientific notation every time. And you don't want to have any chance of making a careless mistake. So the mechanical method here for figuring out which way to move the decimal point was to say to yourself, well, I'm removing the power of 10, which basically means that I'm replacing the power of 10 just with the number 1. That means that portion of the number is getting smaller. Therefore, the other portion has to get bigger to balance that out, and the way to make it bigger is to move the decimal point to the right. It takes a few seconds to explain that logic, but I hope that you agree that with a little bit of practice, it can be a pretty mechanical process. Well, we'll do a few more examples. Please pause the video and rewrite this number in normal notation. I hope that you tried that on paper. So let's see here. So this power of 10, I'm going to rewrite as the number 1. We're getting rid of the power of 10, which means we're rewriting it as the number 1. Well, notice this portion then is getting smaller. 1 is smaller than 10 to the third. That tells me that the other portion has to get bigger, and that tells me to move the decimal point to the right to make this portion bigger. How many times should we move it? 3 times. And now we know that we're going to move it to the right. Once, twice, 3 times, so that it ends up here. We need to put in a couple of zeros as placeholders. And then we can rewrite this so that the whole thing looks prettier without all the apparatus that we used. And we end up with 8,500 as our answer. Please pause the video and rewrite this number in ordinary notation. And again, I hope that you really are doing each of these examples on paper, pausing the video. That's the way to really learn this method. Remember, it's not good enough to be kind of watching the video and saying, yeah, I kind of understand that. I understand that pretty good. I'm pretty on top of this. This is stuff that has to be boringly easy for you, because this would only be part of a harder problem, usually. So make sure you're actually doing all these on paper so that you're getting to the point where these problems are boringly easy. And so also that you know that you have so much confidence with the method that you're never going to make a careless mistake and move the decimal point in the wrong direction. Well, the technique here is to say to ourselves that since we're getting rid of the power of 10, it's as if we're replacing it with the number 1, which is smaller than the original power of 10 here, which means this portion of the answer should be getting bigger. So I'm going to move the decimal point to the right. And how many times am I going to move it to the right? Twice, because of this exponent. Once, twice. So then I can write the new number as 899. Then here's where we put the decimal point, times 46. Here's our final answer. Obviously, in the final answer, there's no point copying the times 1. That was just a trick that we use for figuring out which way to move the decimal point. Please pause the video and rewrite this number in ordinary notation. Okay, well, we're going to get rid of the power of 10. And now we need to say to ourselves that when we replace the power of 10 with the number 1, we're actually replacing it with a bigger number. Remember that a power of 10 raised to a negative exponent is a fraction that's less than 1. 10 raised to a negative exponent is a fraction that's less than 1. So by getting rid of this, we're actually made this part of the answer bigger. Therefore, this part has to get smaller. so that the two sides balance out, because we're still supposed to be representing the same number. How can I make this number smaller? By moving the decimal point to the left. Now I know I need to move the decimal point to the left 7 times. Once, twice, 3, 4, 5, 6, 7. So the decimal point ends up here. And then we need to put in a bunch of zeros as placeholders for these digits. And now I can rewrite this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 zeros. Then the 5 and the 7. All right, and here's our answer. We've rewritten this in standard notation. Notice that the number of zeros that we ended up with here was not the same as the exponent. We moving the decimal point 7 times only required us to put in 6 zeros. As I think I mentioned earlier, if you want to, you could also write the answer like this. It's just a matter of taste whether you put in a 0 to the left of the decimal point or not. So here's our answer. So I guess this is the first time that I gave you an example with a negative exponent. So were you able to figure that out? This is the first time we've gone over an example now with a negative exponent. So I don't know, do you remember we said earlier there's really 4 different cases that you might need to deal with. And now maybe you have a clearer idea of what I meant when I said there was 4 different cases. You could change a regular number into scientific notation that involves writing down a positive power of 10, or you could write a regular number into scientific notation that involves writing down a negative power of 10. Or you could start with a number in scientific notation with a positive power of 10 and change it into regular notation. Or you could start with a number in scientific notation that involves a negative power of 10 and write it in regular notation. Those are the 4 different cases that we've gone over. But instead of learning 4 different methods, we basically tried to learn one method that will handle all of those. And the basic trick is to say to yourself that one version has a power of 10 and the other version has the number 1. Our trick is to always write the regular notation multiplied by the number 1, taking up the place that in the scientific notation version is taken up by the power of 10. And then we simply focus on the fact that one part of the number is going to be getting bigger, so the other part of the number has to get smaller so that it still represents the same number. And that will always tell us whether we're moving the decimal point to the left or to the right, or whether we're using a positive or a negative exponent. Well, it's kind of tedious to try to describe the whole method in words, but I hope that by going through these examples, you're getting a good... It can allow you to avoid making careless mistakes without having to give a lot of deep thought to the problem. Please pause the video and rewrite this number in standard scientific notation. No, please write this as a regular number in regular notation. Well, the power of 10 is going to be rewritten just as the number 1. That would involve increasing it. 1 is bigger than this power of 10. Therefore, the other portion is going to get smaller. And the way to make this smaller is by moving the decimal point to the left. How many times should we move it to the left? 4 times. 1, 2, 3, 4. That involved putting in a few zeros. So then we can rewrite our final answer, 0.003884. 0.003884. You might say to yourself, why do we need this whole mechanical method? Shouldn't we just automatically know to move the decimal point to the left since we're using a negative exponent? Well, yeah, kind of. If that works for you, that's fine. But the problem is, say, go back up to this example, notice here we ended up with a negative exponent, but we were moving the decimal point to the right. Here was the original number, and we were rewriting it in scientific notation. And even though we ended up with a negative exponent, we were moving the decimal point to the right, not to the left. Well, hopefully you can see why there's a difference between them. The reason for the difference was that in this case, we were starting with regular notation and changing into scientific notation. Whereas down here, we started with scientific notation and ended up with regular notation. That's why we ended up moving the decimal point in different directions in the two different cases. So those two cases do make sense, and you could figure them out from scratch each time. But my experience is that it's easy for students to make careless mistakes because of all these, because of the two different situations where you would use a negative exponent. And I think you're less likely to make a mistake again if you just use this mechanical approach of focusing on the fact that we're making one part of the number bigger, so the other part of the number has to get smaller, and that tells us which way to move the decimal point. So hopefully comparing these two examples here might convince you that it's not quite as easy as you might think to remember when to move the decimal point to the left and when to move it to the right. It's not good enough just to say, it's not good enough just to focus on whether you're using negative or positive exponents. It also depends on whether you're going from scientific notation to regular or from regular to scientific notation. And to help people not have to think through every single step of that every time, instead, I think it's better for a beginning student just to use this mechanical method that we've been going over. So I'll give you a few more examples. I'd like you to rewrite this now in standard scientific notation. I hope you gave that a shot. So we need to make this between 1 and 10, and when we do that, it gets bigger. 5.6 is bigger than 0.56. Therefore, this portion should have gotten smaller, which requires a negative exponent. How many times did we move the decimal point? Once. So here's our answer. Please pause the video and write this in ordinary notation. We're changing the power of 10 into the number 1, which involves making it smaller. So this portion should get bigger, and the way to make it bigger is by moving the decimal point to the right 4 times. 1, 2, 3, 4. Here's the answer. Please rewrite this in ordinary notation. So the power of 10 is being removed or changed into the number 1. That would decrease this portion of the answer. So this portion has to get bigger so that everything balances out, which means we're going to move the decimal point to the right 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That could have been a little neater here, but here's where we need the zeros. One, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. The decimal point is here, but ordinarily you wouldn't write the decimal point for this type of number, and it would probably help to put in some commas to make this number easier to interpret. Does everyone understand why one part should be getting bigger while the other part gets smaller? It's because we're trying to write two different ways of writing the same number. The whole point of this approach is to say that what I have on the left represents the same number as what I have on the right. These are two ways to write the same number. Therefore, if one part of this representation is smaller than in the original representation, the other part has to be bigger so that those two changes can cancel out, and so that overall this would still represent the same number. Rewrite this number in scientific notation. I hope you tried that on paper. Well, we know the technique is to change the numerical portion so that it's between 1 and 10, which would happen like this, which makes that numerical portion smaller. We know another trick that we've been using is to say that the original number was multiplied by 1 and that the place of that is taken by a power of 10 over here. Now we want this portion to be bigger than this portion, so this should be a positive power of 10. How many times did we move the decimal point? Well, remember the decimal point started here. It wasn't written, so we assume it's to the far right, and then we moved it once, twice. So here we could either use a dot for multiplication or an X. The disadvantage of using a dot is that it might get confused with a decimal point. The disadvantage with using an X is it might get confused with the variable X. You have to be careful either way. All right, so here's another example of the method. Now, ordinarily, it might be more convenient to write this number in regular notation. There's not too much point writing it in scientific notation since it's not that big. But if you had to write it in standard scientific notation, this is the way that you would do it. Again, do you see why one part has to go up while the other part goes down? Because we want this number to represent the same thing as the number on the left-hand side, which we could have written as 857 times 1. Do you see, it wouldn't make sense to say that this portion is smaller than this and to make this portion smaller as well. If we made both of these two things smaller than originally, there's no way that the right-hand representation could be the same number as the left-hand representation. The only way that the right and the left can represent the same number is if they're equal. Well, how can the right-hand side be equal to the left-hand side if this portion is smaller, only if this portion got bigger? Something else I wanted to point out here that might cause confusion. Notice that in this case, we moved the decimal point to the left, even though we were using a positive exponent. We have a positive exponent, but we were moving the decimal point to the left. Why? Well, the reason for that is because we didn't. Because we started with regular notation and shifted into scientific notation. If we had started with the scientific notation and we were trying to rewrite it in regular notation, then the positive exponent would indeed tell us to move the decimal point to the right. But since we're starting with regular notation and changing into scientific notation, a positive exponent turns out to be associated with moving the decimal point to the left. Well, as I've mentioned a couple times already, I think it can be confusing to try to work out that pattern when you're in the middle of a harder problem. So once again, what we've done here is we've learned a systematic mechanical method that will always end up giving you the right, that will always end up moving the decimal point in the right direction or giving you the correct exponent, whether positive or negative. The way to make sure everything is working out correctly is just to keep track of which part of your answer is getting bigger and which part is getting smaller. If you do that each time, if you just keep following this mechanical method, you'll get the problems right without having to think through the logic behind whether we're using a positive or a negative exponent or whether we're moving the decimal point to the left or right. Without having to think deep thoughts about these, we can get these right just by using these two arrows, one going up and one going down, to make sure that things balance out. Please rewrite this in standard scientific notation. We need to rewrite the numerical portion so that it's between 1 and 10. So I've done that. Now, what about this last 0? Well, now this last 0 is optional. I don't know, I hope you're familiar enough with decimals to know that the number doesn't change whether or not we put in the 0 in this position. This is an optional 0. If it makes you feel more comfortable, you can put it in, but it's not necessary in this particular place. On the far right, to the right of the decimal point, this 0 is not important. Obviously, this 0 is very important. So let's see here. This portion got smaller than our original answer. Therefore, this portion should be bigger, which tells us we need a positive exponent. How many times did we move the decimal point? Well, the decimal point started here, and then it moved once, twice, 3 times, 4 times. And again, we decided that should be positive 4, so that this portion of the number is bigger than its counterpart that we started with. So I think that's our answer right there. So again, I hope you're trying all these examples on paper. And I hope that you're finding them boringly easy. The goal of this video is to teach you how to handle scientific notation so that it becomes boringly easy, so that you know you won't make careless mistakes in the middle of a harder problem. That's why we're going over so many examples, so we can get to the point where these problems are boringly easy. Please rewrite this in standard scientific notation. Well, here we go. Remember, this is a multiply sign, not a decimal. I hope that's clear in the videos. I'm putting the decimal points down low and the multiplies up high. Maybe it would be better to use an x for multiply, although then that could be confused with the variable x. Let's see, so this is for multiply. The numerical portion should be between 1 and 10. So here we have a numerical portion that's between 1 and 10. This got smaller. 9.9 is smaller than 99. So the power of 10 should be bigger than the number 1. We move the decimal point once here. So this is 9.9 times 10 to the first power. in ordinary situations, you probably wouldn't even bother to write this in standard scientific notation. It's easier just to call it 99. But if you had to, you could write it like this in scientific notation. So let's try writing this number in in ordinary notation. Write this in ordinary notation. I hope you did that. So let's see. The power of 10, we're going to replace just with the number 1. 1 is smaller than 10 to the 8th. So this portion of the answer should be getting bigger. The way to make this bigger is to move the decimal point to the right. The decimal point starts over here, and then I'm going to move it 8 times. 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5, 6, 7, 8. So this would be 300 million. Let's see. Please write this in standard scientific notation. No, I meant write this in regular notation. I'm going to need some space for this one. So 1 is smaller than 10 to the 23rd. So this portion should be getting bigger to balance out this portion that got smaller, and to make this bigger, I moved the decimal point to the right 23 times. Okay. So let's see, that would be 1, 2. Let's see, I don't know if I really... so I've moved it twice, and now I'm going to move it 26 more times, which would mean... no, wait, I moved it twice. I'm going to move it 21 more times, which would mean 21 zeros. So that would be 602. That's the first 2 times I moved to the right, and now 21 more times, or 21 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Three, 6, 9, 12, 15, 18, 21 zeros. So there's 21 zeros. Yeah, so overall, that would mean I've moved the decimal point 23 places to the right from where I started. You can check that. So here's the answer. This is how we would write this number in standard notation. And again, you can start to see how it really is much more convenient for very large numbers to use. I keep misspeaking. What I meant to say is this is how we would write the number in regular notation. But you can see that the scientific notation is much more convenient than the regular notation for such a large number. Let's see, just for fun, these are the thousands, millions, billions, trillions, quadrillions, quintillions. So I think this would be 602 sextillion. 602 sextillion. Millions, billions, trillions, quadrillions, quintillions. Yeah, 602 sextillion. All right, obviously it's actually not very important to know the names for very large numbers, because actually naming very large numbers is not a very effective approach. A much more effective approach is just to put them into scientific notation. Please write this number in regular notation. Write this in regular notation. Well, we'll need some space for this again. We're going to replace the power of 10 with the number 1. Now the number 1 is bigger than 10 to the negative 19, so the rest of the number here should be getting smaller. So how can I make this portion smaller? By moving the decimal point to the left 19 times. So here's the first time, and then we're going to do 18 more times, which will require 18 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so overall, we moved the decimal point 19 times to the left. So here would be the answer. Here's how we could write this number as a regular number. And again, you can see how the regular notation is really much less convenient than the scientific notation. Please write this in scientific notation. Times the number 1. So we need to write this so that it's between 1 and 10. 8 is between 1 and 10, the numerical portion. That means the power of 10 should be smaller than its counterpart over here, which would mean a negative exponent. So now we've rewritten this in scientific notation. Are you getting bored yet? I hope so. If you're bored, that's good. If you're bored, that means that these problems are boringly easy for you and you're not likely to make careless mistakes on them. That's our goal. This is a little bit of a trick question, but how would you write this in standard scientific notation? This is kind of a trick question. This probably is not of very much practical importance, but notice that the numerical portion here is already between 1 and 10. So we don't need to make any change, so we're not moving the decimal point at all. If we're not moving the decimal point at all, I guess we could write it like this. So if you're going to write this in scientific notation, I suppose you could write it like this, 8.53 times 10 to the 0 with power. But to tell you the truth, maybe there wasn't much point of covering that. That's not something you're likely to use in practical situations. I suppose in any practical situation, you would just write the number as 8.53 here. There's really no reason at all to use scientific notation for such an ordinary number like this. So I guess that was, sorry, that was a little bit of a pointless example, but I couldn't resist covering this kind of weird case. Let's rewrite this as a number in scientific notation. So let's see here. This has to be written so that it's between 1 and 10. So the numerical portion got bigger. So this needs to represent a number that's smaller than the number 1. Let's see, we move the decimal point 1, 2, 3, 4, 5, 6, 7 places. And I know this should be 10 to the negative 7 because I wanted this to be smaller than the number 1. 1, 2, 3, 4, 5, 6, 7. Well, I'm starting to get bored. I guess that's a good sign. If I'm bored, that must mean that I understand the method and I'm unlikely to make careless mistakes. Please rewrite this as an ordinary number. Let's see, 1 is bigger than 10 to the negative 11, so I need to make this portion smaller, which I do by moving the decimal point to the left. And how many times are we going to move it to the left? 11 times. So here's the first time. And then 10 more times would involve 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's check to make sure I really did move it 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's the answer. Okay, it feels like we've done a bunch of examples. Starting to lose track. Seems like quite a few examples. Okay, so let's see. What next? Please convert this number into regular notation. Try to convert this number into regular notation. Well, this is a little bit different from the examples we've done so far, but you might have been able to figure this out. There's a couple different ways you could do this, but if you were going to use the same method that we've been using so far, the first thing you'd probably want to do is rewrite it like this, so that it looks more like standard scientific notation. Now it has a coefficient out in front. And now we can use the same method that we're used to. So let's see, I'm going to change the number 10 into the number 1, which makes it smaller. This power of 10, I'm going to get rid of the power 10 or change it into the number 1. So this has to get bigger, which means I'm moving the decimal point to the right, 3 places to the right. 1, 2, 3. So we end up with the number 1,000. Notice that 10 to the third just means 1 followed by 3 zeros. Please pause the video and rewrite this number in regular notation. Well, one approach you could use is to rewrite it in standard scientific notation. Now we're going to get rid of the power of 10. That means this part has to get bigger, so I'm going to move the decimal point 6 places to the right. 1, 2, 3, 4, 5, 6. So to move the decimal point 6 places to the right from over here to over here, I'd have to put in 6 zeros. So then our final answer is 1 million. So 10 to the 6th just means 1 followed by 6 zeros, or 1 million. Please write this number as in regular notation. Well, you do it like this. Here's the decimal point, 1, 2, 3, 4, 5, 6, 7. I need to put in 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. So this is 10 million. So 10 to the 7th is the number 1 followed by 7 zeros. Well, if you're seeing the pattern here, maybe it's not really necessary to use this systematic technique anymore. 10 to the 7th is just the number 1 followed by 7 zeros. 10 to the 6th is just the number 1 followed by 6 zeros. 10 to the 3rd is the number 1 followed by 3 zeros. 10 to the 11th would be the number 1 followed by 11 zeros. 10 to the 27th would be the number 1 followed by 27 zeros. But if you ever forgot or weren't sure of that rule, you can confirm it using our normal method for scientific notation. Notice that these two numbers are the same. So if you want to, you can write this in standard scientific notation as 1 times 10 to the 7th, or you could just write it as 10 to the 7th. Those two numbers are the same. Please pause the video and write this number in regular notation. Write this in regular notation, please. Well, again, one way we could do this is to rewrite it first so it's in standard scientific notation. Then I'm going to get rid of the power of 10, which means I'm replacing it with a number 1. So if we're thinking of this 10 as turning into the number 1, it got bigger, so this portion should get smaller, so I have to move the decimal point to the left. The decimal point starts over here, and I move it 1, 2, 3 places. So we end up with 0.001. Well, I don't know if you remember, but in decimal notation, this is the tenths place, and this is the hundredths place. So this is the thousandths place. So this is 1,000th. Just like 10 to the third was 1,000, 10 to the negative third comes out to be 1,000th. The fraction 1 over 1,000. Notice that we don't end up with 3 zeros here. We end up with 2 zeros to the right of the decimal point, because the first time we moved the decimal point, we didn't need to plug in a 0. We were just moving it from the right side of the 1 to the left side. So 10 to the negative 3 means the number 1 preceded by 2 zeros to the right of the decimal point. It would also be legal to write it like this. Then you'd have the 3 zeros, although there's still only 2 of them to the right of the decimal point. Please write this number in regular notation. I hope you're pausing the video and giving that a shot. So let's see, 1 times 10 to the negative 6. So we could just keep using our same standard approach. 1, 2, 3, 4, 5, 6. So here's the number. So 10 to the negative 6 is the number 1, then with 5 zeros to the right of the decimal point. How would you describe this in words? Well, this is the tenths place, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So this equals 1/1,000,000th. 1/1,000,000th. We kind of already knew that, right? Didn't we go over at the very beginning of this series of videos, we saw that 10 to the negative 6 was really the same as 1 over 10 to the 6, right? Which is 1 over 1,000,000. So this just confirms some of the stuff we talked about at the beginning of the session. So notice that 10 to the positive 6 is 1,000,000. 1,000,000. 10 to the negative 6 is 1/1,000,000th. Rewrite this number in regular notation. Well, I'm going to have to put in 1, 2, 3, 4, 5, 6 zeros so that we've moved the decimal point 7 times altogether from this position over here. 1, 2, 3, 4, 5, 6 zeros. So 10 to the negative 7 involves 6 zeros to the right of the decimal point. And of course, this would be the same as 1 over 10 to the positive 7th. So this is the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. This is the 10,000,000ths place. So this is 1/10,000,000th. 1/10,000,000th. You can confirm that by thinking about the decimal places or by remembering 10 to the positive 7 was 10,000,000. So 10 to the negative 7 by symmetry should be 1/10,000,000th, a very small fraction. Hopefully, again, now we're getting a better sense for what these negative exponents mean. And again, this should really hammer home the point. Negative exponents don't mean negative numbers. They mean tiny fractions. A negative exponent doesn't mean a negative number. It means a tiny fraction. Write this number in regular notation, please. Pause the video and try that. We're moving the decimal point to the left because I want this part to get smaller. I'm going to move the decimal point 9 places to the left from here, which involves putting in 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Because the first time we moved the decimal point, it was just moving from one side of the 1 to the other. So that gives us 1, 2, 3, 4, 5, 6, 7, 8. Here's the number. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10,000,000ths, 100,000,000ths, billionths. So this must be 1/1000,000th. 1/1000,000th. So what would 10 to the 9 be? That must be 1,000,000,000. 1 followed by 9 zeros. You can confirm that using the methods we already talked about earlier. So these are some common powers of 10 that you're likely to work with a lot. It's good to have these in the back of your head. You should know that 10 to the third means 1,000. So 10 to the negative third means 1,000th, 1,000th. You should know that 10 to the negative 6 means 1/1,000,000th. So 10 to the positive 6 means 1,000,000. Anyway, so let's see, what was I saying? I was saying that you should know that 10 to the negative 6 is 1,000,000th, and 10 to the positive 6 is 1,000,000. You should know that 10 to the negative 9 is 1/1000,000th, and 10 to the positive 9 is 1,000,000,000. By the way, anyway, in the U.S., this would be 1 billion. I actually think there's some countries where a billion refers to a different number than this. Unfortunately, not all countries use the same naming system. I think though most English-speaking countries, this would be called 1 billion. Probably most of the people watching this video are from an English-speaking country. So anyway, you might want to be a little bit careful. And so in the US, and I think most other English-speaking countries, this would be the number 1 billion. I think there's some places where it's not called 1 billion. But anyway, if so, then you're on your own. But for our purposes, we'll call this 1 billion, and we'll call this 1/1000,000th. Okay, so let's see. Okay, so I wanted to review those various powers of 10. Please pause the video and rewrite this number in normal notation. I hope that was easy for you. This is the number 1. Pause the video and rewrite this number in normal notation. I hope that was easy for you. This is the number 10. Pause the video and rewrite this number in normal notation. Well, that would come out to be 0.1, right? We could use the same techniques that we've gone over earlier. This would be 1 times 10 to the negative 1. We're going to replace the number 10 to the negative 1 with the number 1, which makes it bigger, so this number should get smaller, and we make it smaller by moving the decimal point 1 place to the left, and we end up with 0.1. But the fact is, this number is so common, you should pretty much just have memorized that this is 0.1. How would you pronounce this in words? This is 1/10, right? One-tenth. So 10 to the first is 10, and 10 to the negative first is 1/10. Pause the video and rewrite this number in normal notation. That'll be 1 followed by 2 zeros, or 100. Pause the video and rewrite this number in normal notation. Well, using the same technique we used up here, we would end up with 0.01 for this. Notice that even though the exponent is the number 2, we only end up with 1 0 to the right of the decimal point. We've talked about that pattern a bunch of times. And do you recognize, how would you pronounce this in words? Isn't this 100th? 100th, as opposed to this, which is 100. This is 100th. And again, this comes up so commonly that it's probably worth just having memorized that this means 100th. And I think we've already seen this is 1,000. So rewrite this number in normal notation. I hope you're actually physically writing those down. Hopefully that's pretty boring for you at this point, but it's still good practice. Well, using the techniques we talked about before, that would come out to be this, which is 1,000th. This is 1,000, and this is 1,000th. Rewrite this in ordinary notation. That would be 1 followed by 6 zeros. Rewrite this number in ordinary notation. Well, we know this number is less than 1, and if we move the decimal point 6 times to the right from over here, we end up with 5 zeros. 1, 2, 3, 4, 5. And in words, this would be 1/millionth. Rewrite this number in ordinary notation. Well, if you start with the number 1 and then move the decimal point 9 places to the right, you have to put in 9 zeros. And you end up with 1 billion. Pause the video and rewrite this number in normal notation. Well, if we start with the number 1 and move the decimal point 9 places to the left, we end up putting in 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5, 6, 7, 8. And this is 1 billionth. Okay. Of course, we could keep going. 10 to the 12th would be 1 trillion, and 10 to the negative 12th would be 1 trillionth. Here's the numbers that are probably most commonly used in physics and chemistry courses. So I'll just stop with these for the time being. These particular examples come up so often, you should kind of sort of have them memorized. You should pretty much have memorized that 10 to the third is 1,000, or that 10 to the 6 is 1,000,000, or that 10 to the negative 2 is 100th, or 10 to the negative 1 is 1/10. Of course, if you forgot any of them, you should be able to figure out this table using the various techniques we've already talked about so many times in this video. Okay, so here's a useful table of common powers of 10. So the point is, when you're doing a problem in science or in chemistry or physics or some other science, very often you're dealing with powers of 10, and you should have a feel for what those powers of 10 mean. So hopefully what we have here will give you a feel for what the basic powers of 10 are. And hopefully, again, maybe hopefully we're getting a better feel for what negative exponents mean. Those are probably a little bit more mysterious than positive exponents. But I hope that if you can see the symmetry between the negative exponents and the positive exponents here. 10 to the 9th is a billion, 10 to the negative 9 is a billionth. 10 to the 6 is a very big number, 1 million. 10 to the negative 6 is a very small number, 1 millionth. So hopefully that writing them like this helps us to see the symmetry and get a better feel for what negative exponents are. It makes them less mysterious. There are ways of writing small decimals. Please write this number in standard scientific notation. Pause the video and write this number in standard scientific notation. Well, if we were going to use the techniques we talked about earlier, we would write this like so. We would write the numerical portion as just the number 1, because it's supposed to be between 1 and 10. That would involve a down arrow, because 1 is smaller than 10,000. So this portion has to get bigger. Let's see here. We know this should then be a positive exponent, because we want it to be bigger than the number 1. And how many times did we have to move the decimal point? Well, the decimal point started here, and we moved it once, twice, 3 times, 4 times. So if you were going to write this number in scientific notation, it would be written as 1 times 10 to the 4th. Or it would probably be fine just to call it 10 to the 4th. Those are 2 ways of writing the same number. Now, it's possible that this was so easy for you that you didn't have to be so systematic. You might just have said, well, this is 1 followed by 4 zeros, so it must be 10 to the 4th. That's fine, as long as you got the right answer. Please rewrite this number in scientific notation. Write this number in standard scientific notation, please. Well, using our standard approach, we would rewrite the numerical portion so that it's between 1 and 10. So we just write it as the number 1. That would involve making this numerical portion bigger, because 1 is bigger than 0.00001. So the part that's represented by the 10 to the power should be smaller, so I know this should be a negative exponent, because 10 to a negative power is smaller than 1. And we had to move the decimal point once, twice, 3 times, 4 times, 5 times to get it to this position. So we end up with 1 times 10 to the negative 5th. This number is 1 times 10 to the negative 5th. Or you could just write it as 10 to the negative 5th. Please rewrite this number in scientific notation. Well, the numerical portion has to go between 1 and 10. 1 is bigger than the numerical portion over here. So the part that's represented by the power of 10 should be getting smaller, so it should have a negative exponent, because that'll make it smaller than this number 1, which it's replacing. And we move the decimal point once, twice, 3, 4, 5, 6, 7 times to put it over here. So this is 1 times 10 to the negative 7, or if you want, you can just write it as 10 to the negative 7. If you've really internalized some of the patterns we looked at before, you might just have said to yourself, well, this is the number 1 with the decimal point shifted left 7 times, so it must be 10 to the negative 7. So if you have another way that's that gets you the right answer here, that's fine. As long as you're getting the right answer, that's fine. You don't have to use the same exact technique as I've been using on these very simple problems. So you could just say to yourself, I know this is going to be 10 to a negative exponent because it's a fraction that's smaller than 1. And it involves, if you start with the number 1, you'd have to move the decimal point 7 times to make this number, so it should be 10 to the negative 7. If that's the way you thought about it, that's fine. So please rewrite this number in ordinary notation. No, scientific notation. Please rewrite this number in scientific notation. Well, you could just say it's the number 1 followed by 5 zeros, or 10 to the 5th. But our scientific approach, our systematic approach, would be to say, here's the number 1, which is smaller than 100,000. So the power of 10 should be getting bigger, so it should be a positive exponent. And we had to move the decimal point 1, 2, 3, 4, 5 places. So again, we get 10 to the 5th, or 1 times 10 to the 5th. And this is what you would get if you took the number 1 and then moved the decimal point 5 places to the right. So to summarize standard scientific notation means writing a number in this form: a times 10 to the b. A times 10 to the b. B here could be either a positive or a negative exponent, or possibly, that would be a little weird, it could be the number 0, although that would be pretty weird to be using scientific notation for that. Generally, b is going to be a positive or a negative exponent. And a would be a positive or negative coefficient. A could be positive or negative as well. A is what I've been calling B is the coefficient. Let's try again. B is the exponent, right? B is the exponent, or we could call B the power. A is what I've been calling the coefficient, or the numerical portion. I believe the technical term for A is the mantissa. And one more thing about standard scientific notation. Remember that in standard scientific notation, I've been saying that the number A, I'm drawing the number A in a kind of a weird way, aren't I? As if I was typewriting it. I don't know why I'm doing it that way. All right, well, now that I think about it, it doesn't even look like the letter A to me anymore. All right, well, this is supposed to stand for the letter A. And so the letter A here, this is supposed to be, I've said a bunch of times, this is supposed to be between 1 and 10. A is supposed to be between 1 and 10 for a number to be in standard scientific notation. Let me clarify that just a little bit. A is supposed to be greater than or equal to 1 and strictly less than 10. A should be greater than or equal to 1 or strictly less than 10. That's why in our previous examples up here, we wrote this as 1 times 10 to the 5th, not as 10 times 10 to the 4th. This number is the same as 100,000, but this is not standard scientific notation because the mantissa is supposed to be strictly less than 10, not equal to 10. So this would not have been the correct way to write it. Or to give another example, say up here, another way we could have written this is as 10 times 10 to the 3rd. This number could be written as 10 to the 10 to the 3rd. Now, this is a correct way to write this number, but it's not standard scientific notation, because this coefficient is supposed to be less than 10, not equal to 10. So this would not be the standard scientific notation. So I just wanted to be a little more precise about that. On the other hand, A can be equal to 1. In certain very simple cases, the coefficient does equal 1. That's what has happened in all of the simple examples we've just been doing for the last few minutes. So in the past, I've been saying that the coefficient is supposed to be between 1 and 10. In the past, I've been saying the coefficient is supposed to be between 1 and 10, but now we can see, maybe I should have been a little bit more precise. The coefficient should be greater than or equal to 1, but strictly less than 10. And also, to be careful here, we should also say, or, if the coefficient was negative, then it would be between -1 and -10. If you had a negative coefficient, then the a would be between -1 and -10. But it shouldn't equal -10. So in this case, the coefficient would be strictly larger than -10, although it could be equal to -1. All right, so that's just to be a little bit more careful about describing what we mean by standard scientific notation. So here's a kind of a formal definition of standard scientific notation. It's a coefficient times 10 to a power, and the coefficient should satisfy one of these two inequalities. This is what I've meant when I said that the coefficient was supposed to be between 1 and 10. All right, well, I hope now that we've gotten to the point where those types of standard problems are boringly easy. There's still some other topics that would be important for us to talk about with scientific notation, though. So let's move on to something that is related but slightly different. Let's say that we got this number, 837.98 times 10 to the 5th. Now, is this number in scientific notation or regular notation? Well, I wouldn't say that it's in regular notation. I guess you would say it's in scientific notation, but it's not in standard scientific notation. Do you see why I would say that? I would say it's in scientific notation because it is expressed as a coefficient times the power of 10. But why is this not in standard scientific notation? Well, remember that the numerical portion here is supposed to be between 1 and 10 in standard scientific notation, and this is not between 1 and 10. So now I'd like to go over how to change numbers into from kind of maybe one version of scientific notation to another. So let's put this in standard scientific notation. So let's see. Well, pause the video and see if you can figure out how to do that. I hope you gave that a shot. I hope you were trying to adapt the method we were just talking about. So the first thing I would do here is I would write the numerical portion so that it's between 1 and 10. Because we know that's the standard for standard scientific notation. And I would notice that doing that makes this part smaller than we started with. 8.3798 is smaller than 837.98. Now, what's going to be the new power of 10? Well, let's see here. The key is we can see this portion should be getting bigger, right, to balance this portion that got smaller. We moved the decimal point here twice. We moved the decimal point twice, so we need to change this exponent by 2. But the question is, should this be 10 to the 7th or 10 to the 3rd? I hope you can see those are the two obvious possibilities. Since we've moved the decimal point twice, we should change this exponent by 2. Well, we can see it should be 10 to the 7th because we were predicting this part of the number should be bigger than in the original expression. This part should be bigger because this part got smaller. So writing this in standard notation would turn it into this. So this is one of the reasons we've been going over this mechanical approach. The mechanical approach is useful because it allows you to handle a whole bunch of different situations that come up. Not just the earlier situations when we were going between scientific and regular notation, but also situations where you're going from one version of scientific notation to another version of scientific notation, maybe from the non-standard to the standard version. All right, I hope everyone can see how we ended up with this as our answer, but we'll do some more examples. So please write this in standard scientific notation. Pause the video and give that a shot. Well, to put it in standard scientific notation, we would change this to 1.28 so that the numerical portion is between 1 and 10, and we'll see that made this portion smaller. So this portion has to get bigger. Now we move the decimal point once, so we're going to increase the exponent by 1. I knew to increase it and not decrease it because I was predicting this part should be getting bigger to balance this part which is getting smaller. So here's how we would rewrite the original number in a more standard scientific notation. Please pause the video and rewrite this in standard scientific notation. Well, the numerical portion should be rewritten so that it's between 1 and 10. That involved moving the decimal point once, twice, 3 times. Let's see. Now, in this case, the numerical portion got bigger, right? 5.67 is bigger than 0.00567, so the power of 10 should be getting smaller. And should get smaller 1, 2, 3 times. So 8 minus 3 is 5. So here we would have this rewritten in a more standard notation. The numerical portion got bigger, so the power of 10 had to get smaller. How much smaller did it get? Well, that depends on how many times we moved the decimal point. We moved the decimal point 3 times here. So this was similar but a little bit different than the examples I gave you before because we ended up decreasing the exponent. Please rewrite this in standard scientific notation. Well, the numerical portion should be written as 8.33. It got bigger. So the power of 10 should be getting smaller to balance that. We've moved the decimal point once, twice, 3 times. All right, and let's be careful here. That would make this now negative 11, right? Because negative 11 is 3 units smaller than negative 8. Notice that what matters here is who would be bigger or smaller on the number line, not the absolute values. Negative 11 has a bigger absolute value than negative 8, but absolute value is not what matters here. So that the point here is simply 10 to the negative 11 is certainly a smaller number than 10 to the negative 8. Well, that's what we wanted. And that's true. You can see if we go back to the work we originally did, 10 to the negative 4 is smaller than 10 to the negative 3, 10 to the negative 3 is smaller than 10 to the negative 2, 10 to the negative 2 is smaller than 10 to the negative 1. So 10 to the negative 11 is smaller than 10 to the negative 8, 3 units smaller. I'm going to give you a slightly different number type of problem. Now, I'd like you to rewrite this so the numerical portion looks like this. So this is in standard scientific notation, but let's suppose that for some reason we wanted to rewrite it so the numerical portion looks like this. What power of 10 would we use? Pause the video and figure that out. Well, let's see. We increase the numerical portion here. 8,117 is bigger than 8.117. So the power of 10 should be getting smaller. How many times smaller? 1, 2, 3 times smaller, because we ended up moving the decimal point over here. So the 8 gets 3 times smaller and turns into the number 5. So if for some reason you wanted to rewrite the original number as 8,117, the power of 10 would turn into 10 to the 5th. Now notice that in this case, we started with standard scientific notation, and we changed to something that was non-standard scientific notation. But every once in a while, it might be convenient to change something into non-standard scientific notation. For one thing, we got rid of the decimal here. Sometimes it's useful to be able to work on problems where you're not using any decimals. For example, that can be a useful trick when you're taking a standardized test like the MCAT, where you're not allowed to use a calculator. if you're not allowed to use a calculator, it's oftentimes useful to get rid of all the decimals. And we could do that by putting things into a type of non-standard scientific notation. So now let's do that here. Let's rewrite this number so that the numerical portion is just 837. So let's rewrite this into a kind of non-standard scientific notation where the numerical portion is 837. Please pause the video and try that. Well, 837 is bigger than 8.37, so the power of 10 should be getting smaller. We moved the decimal point twice. Well, 10 to the negative 10 is smaller than 10 to the negative 8. We changed it by 2 units. So this would be a way to do this conversion. This is not standard scientific notation anymore, but it might be useful for some situations where you'd like to do calculations without any decimal points. And again, this just gives us an example of how this general method that we've gone over for scientific notation is very flexible. This technique of making 2 changes that balance each other out in direction can be used in a bunch of different situations when you're working with various conversions that involve scientific notation. Let's say we want to write this number. This is already in standard scientific notation, but let's say we wanted to write it as expressed as this power of 10, 10 to the negative 9 instead of 10 to the negative 7. Pause the video and figure out the numerical portion. Well, let's see here. 10 to the negative 9, that's smaller than 10 to the negative 7. So this portion should have gotten bigger. We can do that by moving the decimal point to the right. And the difference in these 2 exponents is 2. 10 to the negative 9 is 2 units smaller than 10 to the negative 7, so I'll move the decimal point twice. And we end up with 600 times 10 to the negative 9. So here's 2 ways to write the same number. We already started with standard scientific notation, but there might be some reason why you wanted to work with, say, 10 to the negative 9 instead of 10 to the negative 7, and in that case you would write the numerical portion like this, as the number 600. Okay. Well, now, next thing I'd like to do is just make sure that it's clear to you, in a sense, what the significance of scientific notation is. So let's use this number, 6.02 times 10 to the 23rd. I think I did an example with this number earlier. But anyway, this is what's called Avogadro's number. It's the number of particles in a mole. Some of you may have not heard that concept before, but many of you probably had. It doesn't matter whether you've heard of a mole or not, but some of you may know that this is the number of particles in a mole. Just like, what's the number of particles in a dozen? This is the number of particles in a dozen. Well, this is the number of particles in a mole. Well, so what's the significance of the scientific notation here? The main thing I want to stress here is that if you see this number, you should say this is a very big number. That might seem pretty obvious, but I just want to make sure that that intuition is clear to everybody. When we use scientific notation with a big power of 10, that means we have a very big number. So what is a mole? A mole is a very big number. We know that a dozen is not that big of a number. A dozen is just 12. That's a pretty ordinary sized number. But a mole is a very big number. Even if you've never heard of a mole before, the point is, when you look at this, you should say that's a big number. And let's just remind you why that is. Again, please translate this into ordinary notation. I hope you paused the video and put this into ordinary notation. So let's see, how would we do that? So, well, we're going to take this number 10 to the 23rd, and remember, we're going to change that to the number 1, right? By getting rid of this, that means that portion got smaller, so the rest of the number should be getting bigger, which we do by moving the decimal point to the right. And how many times are we going to move it to the right? 23 times. So the first 2 times you move it to the right, it'd be like this. Now we have to move it 21 more times, which would involve 21 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Put in some commas so that it's easier to interpret this number. I think we did an example with this number earlier as well, but I just want to talk a little bit more about how to interpret this now. So did I get that right? Did we move the decimal point 23 times? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I think I got that right. Okay, now I can erase all the little apparatus that we had. So we know that this number, 6.02 times 10 to the 23rd, is actually equal to this number. And I just want to convince you that, as we predicted, this is a very big number. That's the only point I just want to hammer home here. When you have a big positive power of 10, that means you're dealing with a very big number. So a mole is a very big number. If you've studied a little chemistry or physics, you might know that if you had, say, 22.4 liters of ideal gas, it would the number of ideal gas molecules, if you had 22.4 liters at standard temperature and pressure, how many gas molecules would there be there? Well, there would be 1 mole, 6.02 times 10 to the 23rd, which would be this number here. Does it make sense that that's such a big number? Well, it should. Remember that molecules are really, really small. Molecules are really, 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 really small. So how many molecules can we fit in 22.4 liters? 22.4 liters is not a huge space, but it's a pretty ordinary sized space. Well, in 22.4 liters, since we're putting in such small little molecules, we should be able to fit lots and 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 lots of molecules. And that's the way it turns out. In 22.4 liters, we can fit this many molecules of ideal gas, a lot, a really big number of molecules. Okay, so again, I just want to really hammer home and make sure that it's clear that whenever you see a number written in scientific notation with a big power of 10, that you should say, aha, that's a very big number. That might seem obvious, but I want to make sure that's clear to you. How about this number? What's the significance of this number? What should you think when you see a number like this? Well, the main thing that should jump out at you is that this is a very small number. A very small number, because it has a big negative exponent. Another way to put it, this is a tiny fraction. This is a tiny fraction, a very small number, a tiny fraction. Is this number negative? Is this a negative number? No. This is a very small positive number. The exponent is negative, but the number is not negative. It's a very small positive number. I just want to make sure that's clear. In fact, just to hammer that home a little bit, let's get just a little bit more practice and write this number in regular notation. Please write this in regular notation. I hope you paused the video and tried that to get a little bit more extra practice. Well, we're going to take the 10 to the negative 31 and we're going to change that into the number 1, which would involve making it bigger. 1 is bigger than 10 to the negative 31st. that means that the remaining portion of the number has to get smaller. So we know we're moving the decimal point to the left to make this portion smaller. How many times do we move it to the left? 31 times. The first time we move it to the left would be this. And then every other time we move it to the left, we're going to have to stick in a 0. So I guess that will make 30 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So here would be the number. Did I get that right? Did I move the decimal point 31 times? Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. I think I got that right. Okay, so here's the number. Remember that if you wanted to, you could stick one extra 0 over here, but that's optional. So this number equals this number. And as we can see, this is a very small number. It's a tiny, tiny fraction, just a little bit bigger than 0, but it is a positive number. Notice that negative exponents don't give you negative numbers. They give you tiny fractions. This is a very small positive number. Incidentally, the significance of this number, this happens to be the mass of an electron in kilograms. Does it make sense to you, then, that this is so small? Well, it should, if you've learned anything about electrons. Remember that an electron is a tiny, tiny, tiny subatomic particle. We were talking earlier about how molecules were small, but electrons are way, 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 way smaller than even molecules are. So electrons are tiny, 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 so it should make sense that they have hardly any mass. The mass of an electron is a tiny, tiny number when we use a unit like kilograms. Kilograms are a unit that's really designed for ordinary-sized objects. Kilograms are a unit that's designed for ordinary-sized objects like apples and baseballs and people. So if you tried to apply a kilogram to an electron, you're going to get a ridiculously small answer. And that's what we got. All right, now again, the whole point of this little discussion here is just to try to make sure that it's crystal clear in your mind what the significance of big positive exponents is and what the significance of big negative exponents is in scientific notation. So we can see that if a number in scientific notation has a big positive exponent on the 10, that just means it's a very, very big number. And if you have a number that's written in scientific notation and it has a large negative exponent on the 10, that means it's a tiny positive number. It's still positive, but it's a tiny, tiny fraction, a very small number like this. So the key thing is I want to make sure that the significance of negative exponents are clear. So you should study this example to make sure you're clear about the significance of a negative exponent. A negative exponent, a big negative exponent in scientific notation means a tiny, tiny fraction, a very small number, but still a positive number. Okay, just to hammer that home a little bit more, what would be the absolute value of 6.2 times 10 to the negative 18? These are absolute value bars here. What's the absolute value of this number? Pause the video and write down your answer. Well, here's the answer. It's just the same number. The absolute value of the number is that number. But remember, the absolute value of a number is just kind of the positive portion of the number, but this number is already positive. This is already positive, so here's the number. I hope that nobody wrote down this as the answer. I hope nobody took off the negative sign on the exponent, because the point here is that the absolute value sign only changes the number if the number is negative. But remember, this number is not negative. It had a negative exponent, but it was not a negative number. So this is actually a small positive number. Well, the absolute value of a small positive number is that same positive number. So hopefully this makes it a little bit more clear once again that negative exponents don't mean negative numbers. So let's say that you see the number 5.28 times 10 to the 25th. What's the main thing you should notice about this number? What's the main thing to notice about this number? I just want to make sure it's very clear to you. The main thing you should notice about this number is that this is a very big number. It has a large positive exponent of 10. You should interpret that as a very big number. So if this was a piece of information that was given to you in a problem, you should ask yourself, gee, why does it make sense to be using such a very big number here? Or more important, if this was an answer that you figured out in a problem, if you were doing a problem and this came out as the answer, you'd want to double check to make sure that it really makes sense that, that you should get such a very big number. So for example, I don't know, if you're trying to figure out what your taxes are this year, and it comes out that this is your taxes, you should say, wait a second, this doesn't seem right. This seems like a very big number, much bigger than that would seem reasonable for me to pay to the IRS. So you should always make sure if you get an answer in scientific notation that it makes sense, that it was reasonable to get such a big number as your answer. If, for example, let's say you're trying to figure out how many chickens there are in a farm, well, if you decided that this was the number of chickens on a farm, I'm pretty sure you made a mistake. There probably is not that many chickens on the farm. On the other hand, if you're trying to figure out, I don't know, how many atoms there are in the chickens on the farm, well, this might be, vaguely reasonable. It's somewhere, it should be a very big number. I don't know exactly how many atoms there would be, but it would make sense that it should come out to be a very big number. So if you're trying to count atoms or molecules or electrons, this would be a reasonable answer, a very big number. On the other hand, if you're trying to count how many drinks you had last night, hopefully this would not be a reasonable way to write down your answer. Okay, so let's see here. Then suppose we had 8.92 times 10 to the negative 23rd. And I'd just like to ask you, what do you notice about this number? What's the significance of a number like this? What does this type of number mean in very broad terms? Well, the answer I'm going for is that this is a very small number. A positive number, but a very small number. So if this was the answer to a question that you were working out, hopefully you would try to figure out whether this answer really makes sense. You want to know, you want to ask yourself, does this answer really make sense? If you're trying to figure out, I don't know, how much your dog weighs, well, this does not seem like a reasonable answer if this is measured in, say, kilograms or pounds. This does not seem like the weight of a normal-sized object. On the other hand, if you're trying to figure out how much an object that's at the atomic or subatomic scale weighs in kilograms, say in an ordinary unit, this might be a more reasonable answer. So if you get an answer like this, you should always ask yourself, does this make sense for me to get such a tiny fraction as my answer here? Remember, this is not a negative number. How would you write a negative number in scientific notation? We haven't gone over that very much, but for example, let's say I wrote this. how would you interpret this number? You might want to pause the video and ask, how would you interpret this number? Well, this is a number, this is a negative number with a very big absolute value. This is a negative number with a very big absolute value. So this really is negative, but it has a very big absolute value. A negative number with a big absolute value. How would you interpret this number? You might want to think about this for a second. Well, you should say to yourself, this is a negative number with a really, really small absolute value. This is a negative number with a very, very small absolute value. So it's a negative fraction that's very, very close to 0. So now, again, this really is a negative number. It's not like the two negatives cancel each other out, right? Because they're in different places. So this would be a negative number that's a tiny, tiny fraction, a negative fraction. It's got an absolute value very close to 0. Let's continue of numbers that are written in scientific notation. Let's see, what did I want to say about that? Let's say we have, say, this number. What's more important in scientific notation? So here we have 10 to a power, and here we have this coefficient in front of that. I believe that actually the technical name for this coefficient is the mantissa, but I guess it's not really too important for most students to memorize that term. I'm just going to keep referring to that as the numerical portion, or as the coefficient. So this is what I'd be calling the numerical portion, or the coefficient, and here we have 10 to a power. Well, which of these two parts of the notation is more important? Which of these two things is more important for the number? Well, I want to convince you that the power of 10 is much more important. It's much more important to be accurate about the power of 10 than the coefficient. The coefficient actually is relatively unimportant. What matters is the power of 10. So let me give you an example to try to make that clearer. So let's say that I'm telling you that somebody has 3 times 10 to the 6th dollars. Somebody has 3 times 10 to the 6th dollars. What does that mean? That means they're pretty well off, right? Doesn't that mean they've got $3 million? You should be able to convince yourself of that using the skills we've been going over before. So this person is doing pretty good, I think. Now let's compare that to someone who, say, has got 3 times 10 to the 5th dollars. What does this mean? Well, you should be able to use the skills we talked about earlier to see that this means this person has $300,000. Well, that's pretty good, but it's not nearly as good as this person is doing, right? So you can see there's a huge difference just by changing the exponent on the 10. A huge difference just by changing the exponent on the 10. I guess that's the main idea I want to convey right here. You might think that 5 is pretty close to 6. You might think there's not much difference between 5 and 6, but it makes a huge difference when it's in the exponent. Small differences in the exponents have a huge impact on the size of the number. That's the point I'm trying to convey. A small difference in the exponent has a huge difference in the size of the number. Just changing by 1 unit here changed this by a lot. In fact, you can see it changed it by 10 times, which shouldn't surprise you, because we're multiplying by 10 one fewer time here. All right, and then suppose we did even more here, and we said, here's another person who's got this much money. Well, you should be able to figure out that this person has 3 with 4 zeros after it. So this person has only $30,000. All right, so this person is not doing nearly as well. Now notice that from the beginning here, we've only changed the exponent from a 6 to a 4. We've only changed from a 6 to a 4, but it's had a huge impact on the wealth of this person. Changing it by 1 unit had a big impact, but if we keep changing it, you can see it's had even more impact. So now if we changed it to 10 to the 3rd or 10 to the 2nd, you can see that would immediately move the wealth down to $3,000 or just $300. So changing the exponent by just a couple of units has a huge impact on the number. That's the point I'm trying to make. Changing the exponent by just 1 or 2 or 3 units has a huge impact on the number. In fact, every time it changes the number by a factor of 10, right? Every time we decrease the exponent by 1 unit, that's actually decreasing the value of the number by a factor of 10. Well, if you divide by 10 once and then twice, you're only at 1/100th of where you started. If you divide by 10 3 times in a row, you end up with something that's only 1,000th of where you started. You might have heard of the expression sometimes used. Sometimes people say that something is having an exponential effect. Well, this is kind of what they're talking about. Here we can see why so an exponential effect is jargon for a big effect. Exponential effects are big. Well, you can see where that phrase came from, because changing the exponent a little bit has a huge impact on the value of the number. That's why people use that jargon of an exponential effect for a big effect. On the other hand, suppose that we started with this person that again has 3 times 10 to the $6, or $3 million. And now let's compare that to someone else who, say, has 2 times 10 to the $6. What would this mean? Well, that would mean the person has $2 million. Now, do you agree that it doesn't seem like the effect has been nearly as much? Certainly, proportionally speaking, it hasn't been nearly as much. Proportionally, there was a much bigger difference when we changed the exponent than when we changed the coefficient. I'd rather have 3 million than 2 million, but both of these people are kind of in the same ballpark, wealth speaking. Whereas you would say that these two people are not really in the same ballpark, wealth speaking. This person is in a different class of wealth. And you can see that even more clearly if we continue to make changes. Let's reduce the coefficient one more time to the number 1. Well, we've reduced the coefficient now twice. The person's still a millionaire. Even though we reduced the coefficient twice, they're still a millionaire. They're not nearly as well off as this person, but they're still maybe in the same ballpark. Whereas, notice that when we reduced the exponent twice, we went from $3 million to $30,000. So I hope you would agree that that is a much bigger difference, especially if you look at things proportionally. So the point of this little example here is to convince you that the exponent in scientific notation has way more impact than the coefficient. It's crucial to get the exponent right. The coefficient matters much less. When you're interpreting scientific notation, you need to focus the interpretation on the exponent way more than on the coefficient. Small changes in the coefficient don't have a huge proportional impact on the number, but small changes in the exponent do have a big proportional change. And if you just change the exponent by just 2 or 3 units, that could be a change of a factor of 100 or 1,000 in the number. All right, so let's see, where should we go with that? So the next thing I wanted to talk about then is approximating then. So let's say we have, say, this number, 2 times 10 to the 8th. Since the coefficient doesn't matter that much, I just wanted to mention, in many cases, it would be reasonable just to approximate this number as 10 to the 8th and just ignore the coefficient. That would at least give us the right order of magnitude, so to speak. Or suppose that we had, say, 4 times 10 to the 11th. We could approximate that as just 10 to the 11th. Let's say that we have 3 times 10 to the negative 7th. Well, we could just approximate that as 10 to the negative 7th. So what I've been saying about positive exponents still applies to negative exponents. The power of 10 is way more important than the coefficient. The power of 10 basically tells you how many decimal places there are in your answer. That's way more important than exactly what the value of one of those decimal places is. So these would all be approximations you might use. Maybe in some contexts it would be useful to still write this in scientific notation. If you're going to keep writing it in scientific notation, you might write it like this, say, or like this, but these are the same number either way, so you can just write it whichever way is most convenient for you. All right, so the point is oftentimes it's convenient to round numbers just so that you're just focusing on the power of 10. So for example, then how would you round, say, this number? Well, I think many people would oftentimes be content just to say that this is about 10 to the 4th, because I've been saying that the coefficient is much less important than the power of 10. So that this is a pretty decent approximation. However, notice 7 is closer to 10 than to 1. So maybe it would make more sense to say that 7 times 10 to the 4th is close to 10 times 10 to the 4th. I'm using an approximate sign here to show that this is just an approximation of the original number. Do you know how to multiply these two numbers? Remember that when you're multiplying two numbers with the same base, you add the exponents. When you're multiplying two numbers with the same base, you add the exponents. X to the a times x to the b equals x to the a plus b. So really, maybe it's a better approximation to use 10 to the 5th here. So we can approximate this as 10 to the 5th. I think many people would just be content to call it 10 to the 4th. It's easier to approximate just by chopping off the coefficient, but it's a little bit more accurate to say this is closer to 10 to the 5th. So for example, let's say that we had 8 times 10 to the 11th. How would you approximate that? Well, some people might just say this is 10 to the 11th, but it's a little bit more accurate to say this is closer to 10 times 10 to the 11th, because 8 is closer to 10 than to 1, which is 10 to the 12th. Okay, so this would come out to be about 10 to the 12th then, approximately. Let's say, how about if we were doing 2 times 10 to the 13th? Well, notice here, 2 times 10 to the 13th, 2 is closer to 1 than to 10. 2 is closer to 1 than the 10. So we can just do the natural thing and say this is approximately 10 to the 13th. So here we end up, that's the technique we used up here. So in this approximation technique, basically we're going to approximate the coefficient as either a 1 or a 10. If it's closer to 1, you would approximate it as a 1. And if it's closer to 10, you would approximate it as a 10. And then you would get your answer. Although, again, maybe it's simpler in some cases just to forget about the coefficient and just mechanically look at the power of 10. That wouldn't be too far off. So if we had, say, 3.7 times 10 to the 8th, well, that would be approximately 1 times 10 to the 8th, or just 10 to the 8th. And if we had 7.81 times 10 to the 14th, well, that would be approximately 10 times 10 to the 14th. 7.8 is closer to 10 than to 1. So we'd approximate that as 10 to the 15th. So rather than using the original exponent, we bumped it up once. I've been writing all of these out, but with practice, you can probably skip these middle steps and go straight to here. You can look at this and say, well, the coefficient is less than 5, so we'll just call this 10 to the 13th. This coefficient is less than 5, so we'll just call this 10 to the 8th. Now this coefficient is bigger than 5, so we're going to bump the exponent up 1 unit to 10 to the 15th. This coefficient is bigger than 5, so we'll have the effect of bumping the exponent up to 10 to the 12th if we're doing an approximation. This coefficient is bigger than 5, so if we're going to approximate to the closest power of 10, it would be better to bump it up once to 10 to the 5th. So this is how we could approximate these. This is called, I guess you could call this approximating to an order of magnitude. Figuring out the power of 10 is called figuring out the order of magnitude. It basically means you're figuring out how many zeros the number has, or figuring out how many decimal places the number has. So we know, for example, this number has 8 zeros. This number has 11 zeros. This number has, I guess, 7 decimal places, so to speak. It's a little bit trickier to work with that, with the negative exponents. But the point is, or I guess you would have 6 zeros to the right of the decimal point. So anyway, roughly speaking, the exponent tells you roughly the number of zeros or the number of decimal places you have. That basically tells you, that's called the order of magnitude. So we're learning how to approximate these numbers to an order of magnitude. Let's see, suppose we had, say, then 5.8 times 10 to the negative 7th. Well, this one we could approximate as 10 times 10 to the negative 7th, or 10 to the negative 6. Again, because the coefficient is closer to 10 than to 1, we bumped the exponent up 1 unit. Or if we've got 3 times 10 to the negative 4th, that's like 1 times 10 to the negative 4th, or just 10 to the negative 4th. Here the exponent, the coefficient was smaller, it was closer to 1 than to 10, so we just kept the original coefficient. So why don't you try this example, 2.7 times 10 to the negative 11. How would you approximate that? I hope you gave that a shot. Well, that would be like 1 times 10 to the negative 11, or just 10 to the negative 11. Let me give you another example. Suppose we had 8.3 times 10 to the negative 5th. Pause the video and try approximating this. Well, 8.3 is closer to 10 than it is to 1. Remember that we're going to be adding the exponents. 1 plus negative 5 is negative 4. So the best way to approximate this would be by bumping up the exponent once to 10 to the negative 4. Okay, this is a useful skill to be able to look at a number in scientific notation and just approximate it as a power of 10. That can be useful to you if you have to do a calculation without a calculator and you just want to get an approximate answer. It might be useful if you're taking a standardized test. You might be able to just focus just on the powers of 10 and get a choice, get something that's close enough to the right choice. So that's a technique that's often useful for standardized tests like the MCAT, where you're not allowed to use a calculator. All right, might be a good idea to go back and redo these examples again then on your own to make sure you're comfortable with this idea of approximating numbers. Maybe I'll give you a couple more examples. So let's say we have please pause the video and approximate this to the closest power of 10. Approximate this to an order of magnitude. Well, 8.7 is closer to 10 than to 1. So we would bump the exponent up 1 unit. Pause the video and approximate this to the closest order of magnitude. Well, 3.9 times 10 to the 20th, pretty close to 1 times 10 to the 20th. 3.9 is closer to 1 than to 10. So we would just call this 10 to the 20th. Pause the video and approximate this number to an order of magnitude. Well, the coefficient is closer to 1 than to 10. So I'd call it 10 to the negative 30th. Pause the video and approximate this number Here the coefficient is closer to 10 than to 1. 1 plus negative 17 is negative 16. We bumped the exponent up 1 unit because this coefficient is actually like another 10. So we put in that 10 here. Okay, now if you're really in a hurry and accuracy, and you can really afford to approximate some, you can be even looser than this, and you can just ignore the coefficient and say, this number is pretty close to 10 to the 14th. This number is pretty close to 10 to the 20th. This number is pretty close to 10 to the negative 30th, and this is pretty close to 10 to the negative 17th. So it wouldn't be terrible to approximate this as just 10 to the negative 17th, but it's a slightly better approximation to call it 10 to the negative 16th. It wouldn't be terrible to say this is about 10 to the 14th, but it's a slightly better approximation, or, well, it's a significantly better approximation that might be useful in some contexts to say it's really closer to 10 to the 15th. Okay, so next point I wanted to make was, let's see. And again, what I'm trying to do here is that, why are we going over this approximation technique? Well, partly because I think it can be useful. Like I said, it might be useful like on a standardized test where you're not allowed to use a calculator, but also hopefully it's giving us a little bit more intuition to what scientific notation means. Hopefully this is hammering home the point that the power of 10 matters much more than the coefficient. That's one of the main lessons here. The power of 10 matters much more than the coefficient. It's a pretty decent approximation then oftentimes just to get the right power of 10 and forget about the coefficient. So how would you interpret these two numbers? What's the relationship between these two numbers? Well, they're both pretty big numbers because they've got big positive exponents. But the thing that should jump out at you, remember that what matters is comparing the powers of 10. So the thing that should jump out at you is that this number is 10 times bigger than this one. This number is 10 times bigger than this one. Would you agree with that, right? Because if I multiply this by 10, 6 plus 1 would give you 7, right? Remember the rule that we talked about earlier. When you're multiplying two numbers with the same base, you add the exponents. So everyone should hopefully agree that we can take this original number and multiply it by 10 to get this number. Again, even though the exponent only differed by 1 unit, they differed by 10, this is called, we would say this number is an order of magnitude bigger than this one. When we say one number is an order of magnitude bigger, we mean that it's 10 times bigger. What's the relationship then between 3 times 10 to the 7th and 3 times 10 to the 8th? I hope it's clear to you that this number is 10 times bigger than this number. 3 times 10 to the 8th is an order of magnitude bigger than 3 times 10 to the 7th. You can see that because the exponent is 1 unit bigger, so we know we're multiplying by 10 one more time. Yeah, that's the easiest proof right there, right? Here we're multiplying by 10 7 times, and here we're multiplying by 10 8 times. So there's an extra factor of 10 here. So this number must be 10 times bigger. Even though the exponent is only 1 unit bigger, the number is 10 times bigger. Okay, good. So if you compared, say, 3 times 10 to the 8th, and 3 times 10 to the 9th, what could you say about the comparison between these two numbers? Well, what should jump out at you is that the right-hand number is 10 times bigger than the left-hand number. The right-hand number is an order of magnitude bigger than this number. You can see this because here we're multiplying by 9 tens, and here we're only multiplying by 8 tens. Or you could also see it by actually, showing that if you multiply by 1 more 10, you would get this, because 8 plus 1 is 9. So what's the relationship between 3 times 10 to the 6 and 3 times 10 to the 8? You might want to pause the video and think about that. Well, here, don't they differ by a factor of 10 squared, right? Here we're multiplying by 10 twice more than we are here. They differ by a factor of 10 squared, or they differ by a factor of 100, we could say. This number here is 100 times bigger than this number. We could also say it's 2 orders of magnitude bigger. This number is 2 orders of magnitude bigger than this number. That just means that the exponent is 2 units bigger. And that's now a very big difference. As we said before, if you just change the exponent a couple of times, that has a huge impact on the number. We don't just increase the exponent by 2 units, but the number got 100 times bigger. So what could you say about the comparison between these two numbers? Well, you would say that they differ by a factor of 10 to the third, right? This number times 10 to the third would equal this number, because 6 plus 3 is 9, but 10 to the third is 1,000. So they differ by a factor of 1,000. This number is 1,000 times bigger, or we would say this number is 3 orders of magnitude bigger than the left-hand number. So what could you say if you had to compare these two numbers? What's the relationship between these two numbers? Pause the video and come up with an answer to that. Well, I hope that the answer that you gave was that this number on the right is 2 orders of magnitude bigger than the number on the left. And I hope another answer you gave was that means that the number on the right is bigger by a factor of 10 squared than the number on the left. And I hope that another answer you gave, that means that this number is 100 times bigger than the number on the left. The number on the right is 100 times bigger than the number on the left, because they differ by a factor of 10 squared. What's the relationship between these two numbers? Pause the video and describe how you would talk about the relationship between these. Well, this number on the right, now these are both huge numbers, right? They're both unimaginably huge numbers, but this number over here is still way huger than the number on the left. They differ by a factor of 10 to the third, or 1,000, right? 10 to the third is 1,000. So this number on the right is 1,000 times bigger than the number on the left. Number 23 doesn't seem that much bigger than the number 20, but it's in the exponent, so it has an exponential effect. This number is 1,000 times bigger than this one. If you wrote them out, this would be the number 6 followed by 20 zeros, and this would be the number 6 followed by 23 zeros. Those are both really big, but this one is still way bigger. So that's the significance here. We would say this number differs by 3 orders of magnitude. So notice that differing by 3 orders of magnitude is a lot. That's a 1,000-fold difference. By the way, another way to see this here is you could divide the numbers. And the 6's would cancel. Do you remember that when you're dividing numbers, you subtract the exponents? Well, 23 minus 20 is 3. If you're dividing two numbers with the same base, you subtract the exponents. And again, this shows that this number over here on the right is bigger by a factor of 10 to the third than this one. It's 1,000 times bigger. Compared to 2. How would you describe the relationship between these numbers? Please pause the video and try to describe their relationship. Well, first of all, you could say this number is bigger by 6 orders of magnitude. This number is 6 orders of magnitude bigger than this one. Or you could say this one is bigger by a factor of 10 to the 6th, because 10 to the 6th times 10 to the 11th is 10 to the 17th. But 10 to the 6th is 1 million, right? I hope that's clear to you. You could work that out using the techniques we talked about earlier. 10 to the 6th is the same as 1 times 10 to the 6th. So you could use our earlier techniques to write this out as 1 million. So this number is 1 million times bigger than this. You might not seem like a difference of 6 in the exponent makes such a huge difference, but it means this number is actually 1 million times bigger. I hope it's clear to you how to change these powers of 10 into numbers, right? So if you have, say, 10 to the 6th, if you wanted to write that, well, one way you could do it is call it 1 times 10 to the 6th. And then we could change this into the number 1. So this number is going to get bigger. So we move the decimal point 1, 2, 3, 4, 5, 6 places to the right. And we'd end up with 1 million. So that's one way to show that 10 to the 6th is 1 million. It turns out to be 1 followed by 6 zeros. 10 to the third is 1,000, 1 followed by 3 zeros. 10 squared is 100, 1 followed by 2 zeros. 10 to the ninth is 1 billion, 1 followed by 9 zeros. You could prove all of that either by doing these out by hand or on your calculator, or putting them into scientific notation and using the techniques we talked about earlier for working with scientific notation, however you like. Let's see here. On the other hand, be careful. Notice that 10 to the third is 1 with 3 zeros, but 10 to the negative 3 is 0.001. There's only 2 zeros to the right of the decimal point, so that's a pesky complication. Here we would start with 1 times 10 to the negative 3. We change this to the number 1 by making it bigger. We have to make this number smaller, which we do by moving the decimal point once, twice, 3 times. And that proves again this comes out to be 0.001. All right, so 10 to the third means 1 followed by 3 zeros, but 10 to the negative 3 means 1 preceded by 2 zeros to the right of the decimal point. It's a little bit tricky to work with. All right, so anyway, going back to the main idea here, this number is 1 million times bigger than this one. So how would you compare these two numbers? Well, first of all, which one is bigger? I hope it's apparent to everyone which one is bigger. Negative 7 is bigger than negative 8. So 3 times 10 to the negative 7 is bigger than 3 times 10 to the negative 8. We went over these ideas earlier. We showed 10 to the negative 2 is smaller than 10 to the negative 1. 10 to the negative 3 is smaller than 10 to the negative 2. 10 to the negative 4 is smaller than 10 to the negative 3. But how much bigger is this number on the right? Well, would you agree it's 10 times bigger, right? Because 3 times 10 to the negative 8 times 10 equals 3 times 10 to the negative 7, right? Remember, add the exponents. Negative 8 plus 1 is negative 7. So this number is 10 times bigger than this number on the left. It's 1 order of magnitude bigger. How would you compare these two numbers? Well, it should be clear the number on the right is 10 times bigger than the number on the left. This number on the right is 10 times bigger than the number on the left. If you multiplied this number on the left by 10, you would end up with this number. So this number on the right is 10 times bigger. So how would you compare these two numbers? Well, now the exponents differ by 2. The exponents differ by 2 units, so the number on the right is bigger by a factor of 10 squared, or the number on the right is bigger by 100 times than the number on the left. So again, the number on the right is 2 orders of magnitude bigger than the number on the left. Or you could say the number on the left is 2 orders of magnitude smaller than the number on the right. So the point I'm making here is that orders of magnitude in the argument we made earlier works just fine for negative exponents. It works the same as for positive exponents. Just look at the difference between the two exponents. These differ by 2 units. That's 2 orders of magnitude. So this number is 10 squared, bigger by a factor of 10 squared, and this number is smaller by a factor of 10 squared. Please pause the video and figure out how you would describe the relationship between these two numbers. I hope you paused the video and tried that. I hope you saw that it's the left-hand number that's bigger, because negative 11 is bigger than negative 13. This is bigger by a factor of 10 squared, or 100. This number is 100 times bigger than this number. You can see that because 7 times 10 to the negative 11. Well, you can see that because 7 times 10 to the negative 13 times 10 squared would be 7 times 10 to the negative 11 if you add the exponents. So how would you compare these two numbers? Pause the video and describe how you would compare these. Well, which number is bigger? Negative 11 is bigger than negative 17, so this number is bigger. I hope you remember that neither of these numbers is negative. These are not negative numbers. These are both just very small fractions. Very small fractions. This number is bigger by a factor of 10 to the 6th, right? Because there's 6 units between negative 17 and negative 11. 17 minus 11 is 6. So this is a million times bigger, because 10 to the 6 is a million. This number is a million times bigger than this one. Or you could say this number is a million times smaller. So remember, this number is very, very small. This is a really spectacularly small number. And this one is even way smaller than that. This number is really, really small, and this number is way, way smaller even than the original really small number. Here we have a really small number, and here we have a number that's a million times smaller than that one. All right, so I think it's important to be able to look at any two numbers in scientific notation and be able to come up with these types of interpretations so that you understand the meaning of the numbers that you're thinking about. So remember that if this number was written out, this would be written as a very small decimal. It would be written as, well, I'll just do it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. To move the decimal point 11 times means putting in 10 zeros here, whereas this number is kind of a pain to write. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I moved the decimal point 17 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, so you can see this number is tiny, and this one is even way smaller than that, is the point. This one is actually a million times smaller. I didn't quite line up the zeros, so it's a little hard to see that. But this one, I think, has 6 more zeros to the right of the decimal point than this one does. All right, so let's say you're comparing, say, 3 times 10 to the 8th versus 4 times 10 to the 15th. How would you compare these two numbers? Well, now I want to use the trick we mentioned earlier. Remember that the coefficients don't make much difference. The coefficients don't make much difference, so this is approximately the same as comparing 10 to the 8th versus 10 to the 15th. Right? So we would say this number on the right is 7 orders of magnitude bigger. The number on the right is 7 orders of magnitude bigger. Or it's bigger by a factor of 10 to the 7th power, which is 10 million. So this number is 10 million times bigger than the number on the left. Now that's not exact anymore. It's not exactly 10 million times bigger, but it's close enough. It's correct to what is called an order of magnitude. So this number is about 7 orders of magnitude bigger than this one. So when we're comparing numbers in terms of orders of magnitude, oftentimes there's an implication that we're just making an approximation, and we're not trying to be exact. Well, pause the video then and try to come up with a verbal description of how you would describe the relationship between these two numbers. Well, I hope that what you said here is that this is approximately the same as 10 to the 16th versus 10 to the 13th. So this number over here is bigger by a factor of 10 to the 3rd, or this number is 1,000 times bigger. This number is 1,000 times smaller. And with practice, we don't even have to write out these steps, right? We can just compare the exponents and see the exponents differ by 3 units, which is about 10 to the third or 1,000. So we'd say this number is about 1,000 times bigger. Please pause the video and compare these two numbers. Come up with a way that, how would you describe the relationship between these two numbers? I hope you gave that some thought. Well, the technique we're using here is just approximating to orders of magnitude. So this number here is about 10 to the 11th. But this number here isn't this a little closer to 10 to the 7th than 10 to the 6th, right? This really counts as, if we're going to approximate, this counts as another 10. So that would bump this up to 10 to the 7th. So then the difference between these differ. This number is bigger by a factor of 10 to the 4th. 11 minus 7 is 4. And 10 to the 4th is the number 1 followed by 4 zeros. So this number is bigger by a factor of 10,000. This number is bigger by a factor of 10 to the 4th. So it's bigger by a factor of 10,000. Or you could say this number is smaller by a factor of 10,000. Okay, so this could be approximated as the number 1 followed by 11 zeros, and this could be approximated as the number 1 followed by 7 zeros. Well, this would have the 4 extra zeros, so it would be bigger by a factor of 10,000. So here we're using our approximation techniques. Now, some people might be a little bit sloppier than this and just compare the 11 and the 6, and they might just say this is 5 orders of magnitude bigger if you just chop off the coefficient rather than rounding up in this case. That's oftentimes that's maybe a good enough approximation, but it's a little bit more accurate to say this is closer to 10 to the 7th. So how would you describe the relationship between these two numbers? I hope you paused the video and came up with an answer. Well, this is actually approximately 10 to the 8th, because this is approximately another 10, and 10 times 10 to the 7th is 10 to the 8th. And this could be approximated as 10 to the 16th, because this coefficient could be approximated as another 10. That would give us 10 to the 16th. 16 minus 8 is 8, right? So that means this number over here is bigger by a factor of 10 to the 8th, 16 minus 8. Or that's 1 followed by 1, 2, 3, 4, 5, 6, 7, 8 zeros. So we could say this is 100 million times bigger, or this number is 100 million times smaller. If you were going to approximate these, you could just call this the number 1 followed by 16 zeros, and this the number 1 followed by 8 zeros. Notice that this is not just twice as big as this number. It's way, way more than just twice. The exponent is twice as big, but when the exponent is twice as big, that makes the number as a whole way, way more bigger than the other number. So this is the exponent is bigger by a factor of 2, but that made the number as a whole bigger by a factor of 100 million. Remember that changing the exponent has an exponential effect on the value of the whole number. Please pause the video and compare these two numbers. Well, this number is approximately 10 to the 5th, and this number is approximately 10 to the 3rd. Because the coefficient is closer to 10 than to 1, we can add another power of 10 here. So that means this number is bigger by a factor of 10 squared. 5 minus 3 is 2. 10 squared times 10 to the 3rd is 10 to the 5th. That's 100. So this number is 100 times bigger. So hopefully with practice, we can just kind of eyeball these and say, yep, this looks 100 times bigger. Or if you're being a little bit sloppier and not rounding up, you might compare the 5 and the 2 and say this is 1,000 times bigger. Well, that wouldn't be as accurate as saying it's 100 times bigger, but it would be better than saying that it was maybe 1,000,000 times bigger. Say it might be close enough in some circumstances. Okay, just to give you a vague sense of the ballpark where each of the numbers resides. This number is approximately 10 to the negative 7th, and this number is approximately 10 to the negative 4th. Both of the coefficients are closer to 1 than to 10, so there's no reason to change the exponents. And then the difference between negative 7 and negative 4 is negative 3. Now remember, this is the number that's bigger. Negative 4 is bigger than negative 7, so this number is bigger by a factor of 10 to the 3rd, which is 1,000. This is 1,000 times bigger. If you were going to write these out, this number over here would be 0.0001. Take the number 1 and then move the decimal point 4 times, which puts in 3 zeros. And this would be 0.1234561. 1, 2, 3, 1. If we were going to do the approximation here, ignoring the coefficient, here we would take the number 1 and then move the decimal point 7 times. This number is then 1,000 times bigger. They're both small numbers, but actually this one is a lot bigger than this one over here. Let's compare these two numbers. Again, please pause the video and come up with a verbal comparison of these. Well, this number could be approximated best as, maybe I'll be a little bit careful about, well, should be approximated as 10 to the negative 9, right? Not 10 to the negative 11. Here, this number, the coefficient is closer to 10 than to 1, so I'll be sticking another 10. Well, 10 times 10 to the negative 10 is 10 to the negative 9th. 1 plus negative 10 is negative 9, making the exponent 1 bigger. So make sure you're clear why we're not approximating this as 10 to the negative 11th. And then this would just be approximated as 10 to the negative 3rd, ignoring the coefficient because it's closer to a 1 than a 10. Well, the difference between negative 9 and negative 3 is 6. So we could say this number is bigger by a factor of 10 to the 6th. 10 to the negative 9 times 10 to the 6th equals 10 to the negative 3. 10 to the 6th is 1,000,000. 1 followed by 6 zeros. So this number is 1,000,000 times bigger than the smaller one, or this smaller number is 1,000,000 times smaller than the bigger one. This number here is 1,000,000th of the bigger number. If you're going to write this out now, the approximation, it would be 1 with 2 zeros in front of it, so that we move the decimal point 3 times, and here we would have 1, 2, 3, 4, 5, 6, 7, 8 zeros, so that if we started with the decimal point here, we move the decimal point 9 times to the left to get this number. And you can see this number is really quite a bit bigger than this number over here. Please pause the video and compare these two numbers. Well, this is approximately 10 to the negative 7. This is approximately 10 times 10 to the negative 11th, or 10 to the negative 10. An order of magnitude bigger than it might seem because there's another power of 10 here. Well, this number then is the bigger one, bigger by a factor of 10 to the third, because there's 3 units difference between the exponents. 10 to the third is 1 followed by 3 zeros, or 1,000. So this number is 1,000 times bigger than the number on the right, or the number on the right is at 1,000th of the number on the left. These are both very small numbers, but this one over here is way smaller. Try comparing these two numbers. Well, let's see, this could be approximated as 10 to the 5th, because here's the coefficient is close to 10. And this would be approximated as 10 to the negative 2. Well, 5 minus negative 2 is 7, so this is bigger by a factor of 10 to the 7th. Because there's 5 units difference between 5 and negative 2. 5 minus minus 2 is 7. That's 1 followed by 1, 2, 3, 4, 5, 6, 7 zeros. So this number is 10 million times bigger than this number. This number is 10 billion times bigger. Now, keep in mind, they're both positive. These are both positive numbers. Just because this has a negative exponent doesn't make it negative. So if we're going to approximate this, this number would be 1 followed by 5 zeros. And this would be, take the number 1 and then move the decimal point 2 places to the left, which involves putting in 1 0. So you can see there certainly is a big difference between these two numbers. This one's bigger by a factor of 10 million times bigger. Okay, let's see. Hopefully then that gives you a sense then, a better sense of how to interpret scientific notation, what scientific notation means. Hopefully we're really hammering home the point that the exponent matters a lot more than the mantissa. The mantissa is this number here, the coefficient. The exponent matters a lot more than the coefficient, or this numerical portion. In many cases it's good enough just to find the right order of magnitude. Here we would say that this number is bigger by 7 orders of magnitude. Here we have this number is bigger by 3 orders of magnitude, or approximately 3 orders of magnitude. Here this number was about 6 orders of magnitude bigger. So when you're likely to hear your professor use that term sometimes, orders of magnitude. So hopefully we're getting a sense of what an order of magnitude is. The order of magnitude basically just refers to the power of 10. The order of magnitude refers to a power of 10. So if this number is bigger by 6 orders of magnitude, that just means that its power of 10 is 6 units bigger than the other exponent. Here this number was bigger by 3 orders of magnitude because its power of 10 was 3 units bigger than this exponent. Here this number was 2 orders of magnitude bigger than the other number because its exponent was 2 units bigger. So hopefully, again, we're getting a better sense of what that phrase orders of magnitude means. It refers to the power of 10, and it just emphasizes the fact that the coefficient doesn't matter that much. It's not that the coefficient is completely unimportant, but oftentimes it's a reasonable approximation to leave the coefficient out. And maybe I'll just mention one more time that there was one part of my presentation here that was maybe a little bit over careful or more subtle than you might need all the time in real life, which is instead of just rounding each number off by just chopping off the coefficient, I've been rounding each number up or down. So for example, in this case, I didn't just round this to 10 to the fourth, I called it 10 to the fifth, because the coefficient is closer to 10 than to 1. That is a more accurate approach than just chopping off the coefficient. But I think in real life, oftentimes, when people are just trying to get a basic feel for their numbers, it's a little bit simpler, even though it's a little bit less accurate, just to chop off or ignore the coefficient and just compare the exponents directly. So if accuracy wasn't too important here, you could just look at these two numbers and say, well, 4 is 6 units bigger than 2. So this number is about 6 orders of magnitude bigger than the number on the right. That wouldn't be quite as accurate as saying that it was 7 orders of magnitude bigger, but you know, what's an order of magnitude between friends? Sometimes that'll be close enough just to give you the basic sense that this number is way bigger than this one. So same deal over here. If you just want to get a basic feel for these numbers, you might just say, well, -7 is 4 units bigger than -11. So this number is about 4 units of magnitude, 4 orders of magnitude bigger. This number is about 4 orders of magnitude bigger. It's a little bit more accurate to say that it's 3 orders of magnitude bigger if you use the rounding approach. But it might be good enough to get a basic feel just to compare the exponents directly. So my point is, I think in real life, oftentimes, people just compare the exponents on the power of 10 to see what the order of magnitude difference is between two numbers. But sometimes that can give you a pretty inaccurate answer. I mean, you know, if you're comparing, say, let me give you this example. Let's say you're comparing 9 times 10 to the -3. I'll do it like this: 9 times 10 to the fourth versus let's say versus say 2 times 10 to the fifth. What's the difference between these two numbers? You might want to pause the video and think about what's the difference between these two numbers. Well, if you just compare the exponents directly, it looks like this number on the right is an order of magnitude bigger. But if you use the more accurate rounding technique, you would round the number 9 up to a 10. And you would round this number down. And you would see that these numbers are actually about the same to an order of magnitude. We could say that to an order of magnitude, these numbers are about the same. There's not that much difference between them. To an order of magnitude, they're approximately the same number. Clearly, this number is bigger, but it's less than 10 times bigger. This number is less than 10 times bigger than this number, and in some contexts, that might mean that the difference between them is not very important. Okay, so again, if you have a coefficient that's like 9, it's a little silly to round this off to 10 to the fourth. If the coefficient is a 9, it really makes more sense to round this off to 10 to the fifth. On the other hand, if you had a coefficient that was just like 6, maybe it might be good enough to round this to 10 to the fourth, even though it would still be more accurate, a little more accurate to round it to 10 to the fifth. So the point is, you can basically see the difference between two numbers to an order of magnitude by just comparing the exponents on the power of 10. Or if you want to be a little bit more accurate, you might round some of those exponents up by 1 unit to take account of a coefficient that's closer to 10 than to 1. And then you can compare the exponents on the power of the 10. All right, I hope that's making some sense. I guess I'm kind of rambling here. Yeah. And anyway, this was a good example here to show sometimes people might say that two numbers are about the same to within an order of magnitude. So here's two numbers that are approximately the same to within an order of magnitude. Whoops. Let's say the difference between 3.2 times 10 to the -5th versus 1.8 times 10 to the -5th. How would you compare these two numbers? Well, to an order of magnitude, they're about the same. These are about the same to within 1 order of magnitude. Which one is bigger? I hope it's clear that this number is bigger because 3.2 is bigger than 1.8. Remember, the coefficients here are not negative. The coefficients are positive. Well, positive 3.2 is bigger than 3.8. So this number is bigger, but it's not 10 times bigger than the other number. So to within an order of magnitude, they're pretty similar to each other. Please pause the video and decide which of these numbers is bigger. I hope you decided which of these numbers was bigger. Well, it should be plain that this number on the left is bigger. They have the same power of 10, so we can just compare the coefficients. 4 is bigger than 3. Therefore, this number is bigger than this one. Let's also confirm this by writing these as ordinary numbers. As ordinary numbers, this would be 4,000, and this would be 3,000. We learned the techniques for doing those conversions earlier. Here, we're moving the decimal point 3 places each time. And we should be moving it to the right to make the numerical portion bigger because we're replacing the power of 10 just with a number 1. Or you could just say to yourself that you know that positive powers of 10 give us big numbers, which would require us to move the decimal point to the right. Okay, so we've compared these two numbers. Now, using our earlier techniques, we would say that these are about the same to an order of magnitude. They're both approximately 10 to the third, so they're pretty similar to within an order of magnitude, but nevertheless, this left-hand number is bigger. So the lesson here, I don't think I've quite spelled this out before, but the lesson is when two numbers in scientific notation have the same power of 10, then the number with the bigger coefficient is the bigger number. I'll say that again. When two numbers in scientific notation have the same power of 10, then the number that has the bigger coefficient, the bigger mantissa, the bigger numerical portion, that's the bigger number. Please pause the video and decide which of these two numbers is bigger, and also confirm that by writing these in ordinary notation. We have the same power of 10, and the right-hand number has the bigger coefficient. 5.4 is bigger than 2.7, so the right-hand number is bigger. We can confirm that if we write them in ordinary notation by moving the decimal point to the right 4 times in both cases. That confirms that the right-hand number is bigger. Please pause the video and decide which of these two numbers is bigger, and then confirm that by writing them in ordinary notation. Well, they have the same power of 10, so the number with the bigger coefficient is bigger. 6 is bigger than 4, therefore the right-hand number is bigger. You could confirm that by putting them in ordinary notation. And you can see that the right-hand number really is bigger. Here, to put it in ordinary notation, we have to move the decimal point 3 times, but we should be moving the decimal point to the left. One way to see that is that we're replacing the 10 to the power with the number 1. That number 1's bigger than this, so this number should be smaller than the numerical portion using our earlier technique. Or maybe you can just say to yourself, well, I already know that when scientific notation involves 10 to a negative power, that involves a small decimal, a small fraction. So clearly we should be moving the decimal point to the left to get a small decimal. Okay. Hopefully this wasn't too hard, but I think sometimes people, again, get confused with negative exponents. The negative exponents might confuse some people, so I wanted to do this example to clarify this. By the way, compare these two numbers. Which of these two numbers is bigger? Well, negative 4 is bigger than negative 6. Right? On the number line, negative 4 is to the right of negative 6. But that doesn't contradict what we said over here, because this is not a negative 4. The exponent is negative, but remember that doesn't make the number negative. So I think maybe that's why people sometimes get confused here. As we've mentioned many times, negative exponents don't give you negative numbers. So you shouldn't think in terms of negative numbers here. 6 is bigger than 4. We shouldn't treat this like a negative 6, and we shouldn't treat this like a negative 4. Just because the exponents are negative doesn't make the coefficients negative. Maybe I would mention also, if we were making a comparison, using our earlier orders of magnitude technique, we would say, well, these are pretty similar to within an order of magnitude. They both have the same number of decimal places, although we might round this one up to 10 to the negative 2, which would make it seem like this one is an order of magnitude bigger. But that wouldn't be a great approximation in this case, though. You can see that actually they're pretty similar to each other. They do have the same number of digits. So to an order of magnitude, they're about the same, but the number on the right is bigger. Pause the video, decide which of these two numbers is bigger, and confirm it by writing both numbers in ordinary notation. Well, they both have the same power of 10, so the one with the bigger coefficient is bigger. 8.1 is bigger than 3.7. If you move the decimal point 4 places to the right, that involves putting in 3 zeros in both cases. I should have said we're moving the decimal point 4 places to the left, and that involves putting in 3 zeros, and that confirms our earlier idea that this number was bigger. Don't get confused by the negative exponent. To within an order of magnitude, well, they're pretty similar to within an order of magnitude because they both have the same power of 10. We might round this number up to 10 to the negative 3 and this number down to 10 to the negative 4 and say this is about an order of magnitude bigger. So I would say they're somewhere between equal and somewhere between equality and this number being an order of magnitude bigger. So they're not exactly equal, and this number is not 10 times bigger. The relationship between them is somewhere in that range, if that makes any sense. All right. Please pause the video, decide which of these numbers is bigger, and then confirm it by writing them in ordinary notation. Well, they have the same power of 10, so the number with the bigger coefficient is bigger. 5.4 is bigger than 5.3, so the right-hand number is bigger than the left-hand number. In ordinary notation, the two numbers would look like this, and that confirms that the right-hand number is bigger. We have to move the decimal point 2 places here because of the power of 10. So our lesson here so far is that in scientific notation, if two numbers have the same power of 10, then the number with the bigger coefficient is bigger. And we did some examples with negative exponents, so hopefully we won't get confused by that. Although this right-hand number is bigger, they actually are quite similar to each other. These are certainly very close to each other. They are certainly within an order of magnitude of each other. They're quite close, as you can see from writing them out in ordinary notation. Please pause the video, decide which of these two numbers is bigger, and then confirm it by writing them both in ordinary notation. Well, now, in this case, they have the same coefficients, but different exponents. This exponent is bigger than this exponent, so the right-hand number is bigger than the left-hand number. We could write these in ordinary notation as 40,000 and 4 million. I think I must have made a mistake there. Let's see. Here, no, this was wrong. I have to move the decimal point 5 times here, which would involve putting in 5 zeros. Well, that confirms this number is bigger. In fact, using our earlier techniques, we would say it's exactly 1 order of magnitude bigger. Well, these are the type of problem that we were working on earlier. So the lesson here is that when you have the same coefficient, the number that has the bigger power of 10 is going to be the bigger number. By the way, this just reinforces one more time that the power of 10 is more important than the coefficient. The power of 10, notice, basically the power of 10 tells you how many digits there are in the number. The power of 10 tells you how many digits there are, and the coefficient just kind of tells you the value of the final digit. Well, it's much more important. So here we have a 6-digit number, and here we have a 7-digit number. The fact that this has 7 digits and this has 5 digits, that's what's most important. And this has, let's see, this has 7 digits and this has 6 digits. That's much more important than what the actual value of that last digit is. That just reinforces what we said earlier. The power of 10 matters more than the coefficient. Please pause the video, decide which of these two numbers is bigger, and then confirm it by writing them both in ordinary notation. Well, they have the same coefficient, so the one with the bigger power of 10 is bigger. -5 is bigger than -6, so 10 to the -5 is bigger than 10 to the -6. Here, some people might get confused because -6 has a bigger absolute value than -5, but the absolute values don't matter here. The absolute values don't matter. -5 is bigger than -6, so this number on the left is bigger than the number on the right. You could confirm that by writing them both in ordinary notation. So here I have to move the decimal point 5 times by putting in 4 zeros, and here I move the decimal point 6 times by putting in 5 zeros. This represents this number. This represents this number, and you can see that the left-hand number was definitely bigger than the right-hand number because we had to go put in more decimal places here. Okay, so here again we have some review and comparing numbers. In fact, using the techniques we learned about earlier, we would say this number is 1 order of magnitude bigger than the right-hand number. We talked about how to make those comparisons before. And again, this just gives us another example of how the exponent matters more than the coefficient. The exponent tells us here how many decimal places there are. Well, it matters much more how many decimal places there are than what the value of the final decimal places is. So the exponent is more important than the coefficient. All right, so the lesson here again is when two numbers in scientific notation have the same coefficient but different exponents, the number with the bigger exponent is the bigger number. And earlier we saw that when two numbers have the same exponent but different coefficients, the number with the coefficient, the number with the bigger coefficient is the bigger number. So far I think that just basically matches common sense. And just to point out, so the purpose of going over this is what we're trying to do here is just make it so that it is easier for you to interpret and compare numbers that are written in scientific notation, so that when you're doing problems that involve scientific notation, what I'm trying to achieve here is that I want you to have a feel for the numbers that are written in scientific notation. When you're doing a problem using numbers that are written in scientific notation, it's important that you have a feel for how to interpret those numbers so that you're not just mechanically manipulating them and just mechanically plugging them into your calculator, but so that you have a feel for what they mean and how they compare to the other numbers. So that's the purpose of all these exercises that we're going through. Why is it worth your while to spend so much time going over this? Because if you're going to take a bunch of science classes, you're going to be using scientific notation over and over and over in those classes. If you're taking science courses, you're going to be using scientific notation on many, many problems. So I think it's well worth putting in a few hours right now to get a feel for scientific notation. That's what we're trying to do here, to get a feel for how to interpret scientific notation and what it means and how to compare numbers in scientific notation. You probably won't see many questions in your courses that just simply ask you which of these two numbers in scientific notation is bigger, or which of these two numbers in scientific notation is bigger, or that ask you to compare things within orders of magnitude. Not many problems that you do in your courses will be asking you these questions directly, but if you understand these ideas, I think you'll just be much more comfortable using scientific notation to solve problems. So that's our goal here, to give you a high comfort level with scientific notation. The things that we're talking about here are not likely to be tested directly very often, but they can increase your comfort level and understanding in scientific notation and allow you to work better with scientific notation and to make fewer mistakes and understand better what you're doing when you're using scientific notation. So let's keep working on that. So the next thing I wanted to give you was this. Please pause the video, decide which of these two numbers is bigger, and then confirm your answer by writing both numbers in ordinary notation. Well, did you notice that this problem is trickier than the ones we went over earlier because both the coefficient and the power of 10 are different. Both the coefficient and the power of 10 are different in this case. So how are we going to decide which of these is the bigger number? Well, the answer is, I don't know, what is the answer? How are we going to compare these? Well, what do you think matters more? What matters more, the coefficient or the exponent? Let me put it this way. So based on the coefficients, it seems like the left-hand number is bigger. This left-hand number has a bigger coefficient, which makes it seem like the left-hand number is bigger. But the right-hand number has a bigger exponent. 4 is bigger than 3. That makes it look like the right-hand number is bigger. Well, which of those is likely to be more important? Well, if you've digested the material that we've been going over earlier, we've mentioned many times that the exponent is more important than the coefficient. So we should have been guessing here that the right-hand number is bigger, and that's correct. The exponent is more important than the coefficient. So since this exponent is bigger than this exponent, we can say that this number is bigger than this number. And then we can confirm that by writing these in ordinary notation. If we write these numbers in ordinary notation, we would get this, and that confirms the right-hand number is bigger. It seems like it's somewhere within, say, 1 order of magnitude bigger, as we might expect, because this exponent is 1 unit bigger than this one. It's not a full order of magnitude, but it's somewhere in that range. Okay, so that would be how we would compare these two numbers. So, if two numbers have different coefficients and different exponents, it seems like the one that has the bigger exponent is going to be bigger. However, that really only works if both numbers are in standard scientific notation. So, if two numbers are in standard scientific notation, the number with the bigger exponent is the bigger number. And then one more thing, what about if they have the same exponent? Then the number with the bigger coefficient. That's what we've been calling the numerical portion, or the mantissa. The one with the bigger mantissa is bigger. So here's our general rule for comparing numbers in scientific notation. It took a little while to write this out, but hopefully when you think about it, it'll make some common sense. So when numbers are in standard scientific notation, just basically compare the exponents, because the exponents are more important than the coefficients. The one with the bigger exponent was bigger. So for example here, these are both in standard scientific notation. 4 is a bigger exponent than 3, so this number was bigger. Going back up to here, here's some numbers in standard scientific notation. The one with the bigger exponent was bigger. Here, this number with the bigger exponent was bigger. Here, they both had the same exponent, so then we move to plan B. If they have the same exponent, then you look at what's less important, the coefficient. The exponents were the same here, but this one had the bigger coefficient, so it was bigger. Here, the exponents were the same, so then one with the bigger coefficient was bigger. Here again, the exponents were the same, so the one with the bigger coefficient was bigger. So we've done a bunch of examples that all illustrate this rule. Let me just point out, though, again, this really only works if the numbers are in standard scientific notation. If the numbers are in standard scientific notation, then it's always, then the one with the bigger exponent will always be bigger. If numbers are in standard scientific notation, the one with the bigger exponent will always be bigger. If they're not in standard scientific notation, though, this rule might not work. Please pause the video, decide which of these two numbers is bigger, and then confirm that by writing both numbers in ordinary notation. Let's see here. These are both in standard scientific notation, so we can just compare the exponents. The exponent's more important. This number has the bigger exponent, so it must be a bigger number. There's not too much difference between these, because this would be rounded to about 10 to the 5th, and this would be rounded up to about 10 to the 5th. So they're pretty similar to within an order of magnitude, but still this number on the right is bigger. If we were going to write these out, we would write them out like this, moving the decimal point 5 places here, and that confirms the right-hand number is bigger. And by the way, this confirms that the exponent really did turn out to be more important than the coefficient, right? 9.7 is way, way bigger than 1.5, right? 9.7 is way bigger than 1.5, but nevertheless, and the number 5 is only slightly bigger than this exponent of 4, but nevertheless, it was the exponent that made the difference. Exponents matter more than coefficients, as we've seen many times. This is a good example then of how having the bigger coefficient doesn't necessarily make you the bigger number. The exponent is more important. I think we saw that in the previous example too, right? Yeah, in our previous example, this number had the bigger coefficient, but it still ended up being the smaller number. So these are some good examples of how the exponent matters more. Please pause the video, decide which of these numbers is bigger, and then confirm it by writing them in ordinary notation. These are both in standard scientific notation, so whichever has the bigger exponent is bigger. This one has the bigger exponent. -3 is bigger than -4, so this is the bigger number. We would write them in ordinary notation like so. Here I have to move the decimal point 4 times, which involves putting in 3 zeros, and that confirms the left-hand number is bigger. And here's another example of where, even though the coefficient was bigger on the right, the number on the right was actually smaller. This coefficient is twice as big as the coefficient on the left, but nevertheless, this number was smaller because it's the power of 10 that matters more. Remember, you can see here, the power of 10 tells you how many decimal places the answer will have. The power of 10 basically is telling us how many decimal places the answer will have. And the coefficient just tells you who's in the last decimal place. Well, who's in the last decimal place matters much less than how many decimal places there are. This has fewer decimal places, which makes it a bigger number. It doesn't matter that 4 is smaller than 8, because they're not in the same decimal place. There's no point comparing the 4 and the 8, because they're not in the same decimal place anyway. Well, please try the same exercise here. Decide which number is bigger, and then confirm it in ordinary notation. Well, these numbers are both in standard scientific notation, so the one with the bigger exponent is bigger. -4 is bigger than -5. So the left-hand number is bigger. Here's how we would write these numbers in ordinary notation. And you can see again that this number on the right is smaller because it has more decimal places. Here we move the decimal point 5 times by putting in 4 zeros. Remember, all of these numbers could also be written like this if you prefer, but that 0 is not necessary. In this case, this number happened to have the bigger coefficient, but that's not why it's bigger. This is not bigger because of its coefficient, it's bigger because of its exponent. All right, so the lesson here reinforces the idea we've seen before. Powers matter more than the coefficients. If two numbers are both in standard scientific notation, the number with the bigger exponent is the bigger number. If they had the same exponent, as we've seen earlier, then you would compare the coefficient. Please pause the video and decide which of these two numbers is bigger, and then confirm that by writing them both in ordinary notation. I hope you gave that a shot. Now, this number on the left has the bigger exponent, but we can't just assume that this number is bigger here because these numbers are not in standard scientific notation yet, so they're not really comparable. Because these numbers are not in standard scientific notation yet, they're not really comparable. Now we can't just assume this number is bigger. We might guess it's bigger because exponents tend to be more important, but we can't be sure. Because this number doesn't just have a bigger coefficient, it has a way bigger coefficient than this one, and maybe that's actually going to override the exponent. So this is the first time we've done a problem like this. I hope you were able to figure out how to figure this out. If you stopped and thought about it, you should have been able to figure out how to compare these numbers. Maybe you might want to pause the video now and see, how do we compare numbers that are not in standard scientific notation? Remember we saw earlier, if two numbers are in standard scientific notation, we have a good way to compare them. So pause the video and see if you can come up with a systematic procedure for comparing numbers that are not in standard scientific notation. I hope you paused the video and thought about that. That's something that everybody should have been able to figure out. It's actually very straightforward. The very straightforward trick is, first, convert the numbers into standard scientific notation. And then you can use the old rule. So that should be pretty obvious. I hope everyone came up with that. Our problem here is that these numbers are not in standard scientific notation. Well, no problem. We'll just put them in standard scientific notation, and then we can use the rule we already learned about. This number is already in standard scientific notation. It's this number I have to work with. Well, now they're both in standard scientific notation. So once again, I'm using the arrow technique that we've used many times in the video. Here, I had to put this, move the decimal point to the left because I wanted the numerical portion to be between 1 and 10. This was not in standard scientific notation because 72 is not between 1 and 10, but 7.2 is. That involved 7.2 is smaller than 72, so I want this number to be bigger. So I increase the exponent by 1 unit because I moved the decimal point by 1 unit. Now we can compare these two numbers, and now it should be clear that the number on the right is bigger. They both now have the same power of 10, so now we compare the coefficients, and 7.2 is bigger than 5. So here we ended up using the second part. If numbers in standard scientific notation have the same exponent, then you compare the coefficients. So you can see that this rule here is really all we ever need for comparing numbers in scientific notation. This is the only rule we need for comparing numbers in scientific notation. At first it might seem like this is restrictive because it only works for standard scientific notation, but that's no problem because by this point we should be very good at putting numbers in standard scientific notation. So you can always put two numbers in standard scientific notation, and then you can use this rule to compare them. And now notice it turned out that the number with the smaller exponent originally actually turned out to be the bigger number. This exponent 3 is smaller than 4, but this actually turned out to be the bigger number, and you can see why, because when you put it into standard scientific notation, its exponent increased. That now you can see maybe why we couldn't just compare these directly, because when we actually put this into standard scientific notation, that changes the exponent. Really, in standard notation, they had the same exponent. Pause the video, decide which of these numbers is bigger, and then confirm it by writing them in ordinary notation, please. I can't compare these directly because this number is not in standard scientific notation. So here's how we put it in standard scientific notation. And now, to compare the two numbers, they both have the same exponent now, so the number with the bigger coefficient is bigger. So even though this number started with the smaller exponent, it turned out to be the bigger number, because when we put it into standard scientific notation, it ended up to have a bigger exponent than it started with. All right, these numbers are about the same to within an order of magnitude, but this number on the right is bigger. In ordinary notation, this would be 3,900, and this would be 5,100. We can see this number on the right is bigger. I think it's a good exercise in all these to keep writing these in ordinary notation, just to keep giving yourself a feel for what scientific notation means. So in all these examples, I've been giving you examples with relatively small exponents so that it's not too much of a pain to write it in ordinary notation. You could have got, if I had given you this problem, the answer would still have been the same. If you were comparing these two numbers, it would still be the right-hand number that was bigger. It would just be more of a pain to confirm that in ordinary notation. So I've been giving you smaller exponents here so that you can get practice with seeing what scientific notation looks like in ordinary notation. And the purpose of that, again, is just to keep giving you a higher comfort level with scientific notation and a better feel for what scientific notation means. A better feel for the idea that in scientific notation, this exponent basically tells you how many digits or decimal places there are, and the coefficient is just telling you kind of the identity of the last digits or decimal places. So it tends to be less important. Please pause the video so that you can compare which of these numbers is bigger and then confirm it by writing them in ordinary notation. Well, to compare these, I have to put them both in standard scientific notation. We can't just assume that this is bigger because it has the bigger exponent, because maybe that's outweighed by this having the bigger coefficient. Exponents are usually more important, but this coefficient is really big, so maybe it's going to outweigh the bigger exponent. The only way to be sure is to put them both in standard scientific notation. All right, so in standard scientific notation, this would get smaller, so this would get bigger. I moved the decimal point 2 places here, so I changed the exponent by 2 places. Now they have the same exponent, and we can see that the left-hand number was bigger. Even though its exponent was quite a bit smaller than this exponent, the exponent got quite a bit bigger when we put it into standard scientific notation. I hope you also wrote these in ordinary notation. And here's what you should have gotten. Please pause the video, decide which of these numbers is bigger, and then confirm it by writing them in ordinary notation. Let's see, I have to put this into standard scientific notation before I can compare them. And then we see that the number on the right was bigger. When we put this into standard scientific notation, its exponent got bigger, but it was still ended up being a smaller number than this number on the right. These numbers are quite similar to each other. This is not much bigger than the number on the left, but it is bigger. Pause the video, decide which of these numbers is bigger, confirm it by writing them in ordinary notation. Before I can compare these, I have to write this number in standard scientific notation. Now they both have the same power of 10, so we compare the coefficients. 7.3 is bigger than 5, so the number on the left is bigger. you're going to write them out, they would look like this. If you write them next to each other, I think you can see that this number is bigger. Might help to compare these to write them like this, and then you can see this number is bigger. Okay, so here's an example going back to negative exponents. I hope that the negative exponents didn't confuse you. We were able to use the same basic trick that we've been using previously. Our trick is first convert both numbers so they're both in standard scientific notation, and then we can use this rule. The number with the bigger exponent is bigger, or if they have the same exponent, the number with the bigger coefficient is bigger, once both numbers are in standard scientific notation. If they don't start in standard scientific notation, the first step is to convert them so that they're in standard scientific notation. These techniques that I'm going over here, these are not necessarily the only ways that you could ever compare numbers in scientific notation, but I think these are good techniques for beginning students. If this is material you'll find difficult, I think these are good systematic techniques for comparing numbers. Okay, please compare these numbers and then confirm it by writing them both in standard scientific notation. Here's how to rewrite this number in standard scientific notation. And now you can see it's bigger than the number on the right. The exponents are the same, but the left-hand number has the bigger coefficient. In standard notation, in regular notation, here would be the numbers, and I hope that you can see that this confirms that the left-hand number is bigger. It might be easier to compare them if you put in a 0 here, and then again we can see the left-hand number is bigger. Let's do it again. Decide which of these numbers is bigger, and then confirm it by writing them in regular notation. Well, this is the number that has to be rewritten, so it's in standard scientific notation. That increases the exponent, but not enough to beat this number on the left. So the number on the left is still ended up being bigger. This confirms that the number on the left is bigger. If you write it this way, that might be easier to see. Okay, please compare these two numbers and then confirm it by writing them in ordinary notation. Well, I need to rewrite this so it's in standard notation. I moved the decimal point twice here, so I need to change this exponent by 2 units. Now, notice here's an example where they don't have the same exponent once they're in standard scientific notation. The number on the right has the bigger exponent, right? -3 is bigger than -4, so the number on the right is bigger. It's true that the number on the left has a bigger coefficient now that they're in standard scientific notation, but remember, it's the exponent that matters more. So we don't even compare the coefficients here, we just compare the exponents. So this is another important example of comparing numbers. At the exponents, once two numbers are both in standard scientific notation, the exponent matters more than the coefficient. If if you had any trouble with this, you should go back and review it. Again, this just reinforces one more time the exponent matters more than the coefficient. Once numbers are in standard scientific notation, pay attention to the exponent more than to the coefficient. So this number on the right is bigger, and we can confirm that by writing these out. I think this confirms that the number on the right is bigger. All right, so now we've seen that this is the basic rule for comparing numbers in scientific notation. First, make sure they're both in standard scientific notation, and then you can use this rule to compare them. Maybe I should mention this only works if you have, if this only works for positive numbers. This only works for positive numbers. Now, by that I mean it only works for positive coefficients. You need to have two numbers with positive coefficients, which would make them positive numbers. It's perfectly okay for the exponent to be negative, of course. We've seen many examples with negative exponents because we know that doesn't make them into negative numbers. But this doesn't work if you have a negative coefficient. So this is a rule when both coefficients should be positive to use this rule. This rule doesn't work if you have negative coefficients. I haven't really talked very much about numbers with negative coefficients in this series because I don't think they come up too much. I don't think they're too important. This video is already getting really, really long. So I think maybe that for a beginner, it's not too important to focus on negative coefficients. That might just confuse the issue. They do come up sometimes, but I don't really want to spend too much time on that. I think that might just end up confusing us. But I'll just give you a simple example here. Suppose that you were comparing, let's see, suppose we're comparing -5 times 10 to the 4th versus 6 times 10 to the 3rd. Well, we can't just use the rules we talked about earlier. You can't just say this has a bigger power of 10, so therefore it's a bigger number. That doesn't work. Remember, so if we were using the rules we talked about earlier, this rule would tend to say that whichever has the bigger power would be bigger, but it doesn't apply to the new example because both coefficients are not positive. Here we have a coefficient that's not positive. So since this coefficient is not positive, you can't just assume that the bigger exponent makes this bigger. I hope it should be plain that this number is bigger because this number is positive and this number is negative, right? After all, 3 is bigger than -11, right? Positive numbers are always bigger than negative numbers. This is a positive number and this is a negative number, so the number on the right is bigger. You can confirm that by writing these in ordinary notation. So to write this number, to write this number in ordinary notation, I would write it like this. If you have to convert into ordinary notation, I would recommend first kind of pull the negative sign out. Ignore the negative sign and just convert the numerical portion, because the negative sign otherwise would kind of confuse the issue of whether these numbers were getting bigger or smaller. But if we ignore the negative sign, we're replacing 10 to the 4th with the number 1, which is smaller than 10 to the 4th, so we need to make this numerical portion bigger by moving the decimal point to the right 4 times. And then this clearly would be 6,000. And anyway, it should be clear now that 6,000 is bigger than -50,000. So like I said, I'm not really planning to spend much time talking about negative coefficients. But I hope that maybe just this one little example here will make it clearer to you what a negative coefficient really is. So when we have a negative coefficient like this, so this is a negative number with a pretty big absolute value. This is a negative number with a pretty big absolute value, but it's still smaller than any positive number. Okay, well, I'm not going to go into too much more detail about negative coefficients here. I don't think it's worth it. That might be more confusing than it's worth at this point. But for the record, I wanted to point out that this rule for comparing numbers only works when they're both positive, when they both have positive coefficients. Remember, this rule works just fine when the exponents are negative. This rule works just fine when the exponents are negative. Negative exponents don't give you negative numbers. So negative exponents are very, very important in scientific notation. We've done lots and lots of examples. Negative coefficients are a little bit unusual when you're using scientific notation, I think. Not hugely unusual, but a little bit, so I haven't talked about them too much. Decide, please, which of these numbers is bigger. I hope you paused the video and decided which of these numbers was bigger. Well, I hope it's plain that the number on the right is bigger. This number is not in standard scientific notation, but so what? This exponent is so much bigger than this exponent that it should be clear that this number will still be bigger even once we put this into standard scientific notation. So I just wanted to point out that we should still keep using our common sense. This number has so many more decimal places than this one, even considering that this has a bigger coefficient than this one. It should be clear that this number on the left is bigger. Now we can confirm that using our earlier technique. If we were going to write this in standard scientific notation, we'd have to move the decimal point twice to move it over here. And that just confirms this number on the left is way bigger than this number on the right. Just comparing the powers of 10 here, you can see this number on the left is somewhere in the realm of 9 orders of magnitude bigger than the number on the right. On the other hand, if you'd compared these exponents, you would have thought that this number was maybe 11 orders of magnitude bigger, and that would not have been a good comparison. So if you want to compare two numbers within an order of magnitude, it's still a good idea to put them both into standard scientific notation. Otherwise, you can't really trust the exponents, so to speak. Which of these two numbers is bigger? Oh, it should be obvious that this is bigger, right? This is a big number. Numbers with positive exponents are big numbers. That's obviously bigger than this number. You could rewrite this in ordinary notation. Well, so how could you do this more mechanically? First of all, if you wanted to compare these both in standard, so hopefully it's just obvious that this number on the left is bigger. If you want to be kind of nerdy about it and write this number in standard scientific notation, this is pretty nerdy, but you could write this number on the right like this, right? This number on the right is 8 times 10 to the 0, and then you can say, well, clearly this power of 4 is bigger than this power of 0. So that confirms what we said before. But this really shouldn't be necessary. It should be obvious just by looking at them. The number on the left is bigger. The number on the left is 30,000, and this is 8. Okay, so this type of comparison should be easy without really using any techniques. Please decide which of these two numbers is bigger. It might have been a little bit tricky for you to compare these because this doesn't look like it's in standard scientific notation, but you could use this trick to make them look more similar, and now it should be plain that the number on the right is bigger. So here's a trick that's oftentimes helpful. If a number doesn't seem to be in regular notation because it's missing a coefficient, that really means its coefficient is 1. So you could rewrite it like this. This number is 100,000 in ordinary notation, and this number is 400,000 in ordinary notation. So here I wanted to go over this trick of sticking in the number 1 when you seem to be missing a coefficient. Please decide which of these two numbers is bigger. Well, we can use the same trick. This number is missing a coefficient, so we can stick in the 1, and then we see the number on the left is bigger. They both have the same exponent, so we just compare the coefficients. You could write this as this number, and this is this number in ordinary notation. Please decide which of these numbers is bigger. Well, it should be obvious that this number is bigger, because we know that when we use negative powers of 10, that means fractions that are between 0 and 1, right? We should just be able to look at this and say this is a small fraction between 0 and 1. So it should be obvious that it's smaller than the number on the left. That should have been easy. Again, if you wanted to do it the nerdy way, well, you could write this in standard scientific notation, so to speak, by writing it as 7 times 10 to the 0th, because 10 to the 0th is 1. And then we can use our earlier method. 0 is bigger than negative 2. Therefore, the number on the left is bigger than the number on the right. But the only reason I am pointing that out is that I'm a nerd. Actually, for all ordinary circumstances, it should just be obvious that the number on the left is bigger than the number on the right. Just obvious from the common understanding that we went over earlier. So we should be able to compare these directly. So it is not, maybe I shouldn't even be mentioning this. It's not usual in science to write numbers like this. This would be weird. When a number just has one digit, you just write it as the one digit. You don't have to write it in scientific notation, but here's how you could do that if you wanted to be nerdy about it. Please pause the video and determine which of these two numbers is bigger, and then confirm it by writing them in ordinary notation. Well, let's see. We have two numbers that are both already in standard scientific notation, so we can compare them just by comparing the powers of 10. And we can see here that 5 is bigger than negative 4, so this the left-hand number is bigger. The number on the left is bigger because it's got a bigger power of 10. 5 is bigger than negative 4. Also, it should just be obvious because remember, numbers with positive powers of 10, these represent big numbers. Numbers that are much bigger, big numbers, and numbers with negative powers of 10 represent small fractions. So that should make it obvious that this left-hand number is bigger. If you write them in ordinary notation, moving the decimal point 5 places here gives you 30,000, and moving the decimal point 4 places to the left here gives you 0.0009. That just confirms what we said before. It should be obvious that the left-hand number is bigger because a positive exponent gives you a big number and a negative exponent gives you a small fraction. Please pause the video and determine which of these two numbers is bigger. And you can confirm that by writing it in ordinary notation. Well, it should be obvious that the number on the left is bigger without doing any work. Again, positive powers of 10 mean fairly big numbers, so it should be obvious that the left-hand number is bigger. You can confirm that by writing this as the number 400. If you wanted to make another way to compare these, again, this is kind of a nerdy way, but you could call this number here 1 times 10 to the 0, and then clearly the left-hand number is bigger. But like I said, this is just a little bit of a joke. Really, it should just be obvious that the left-hand number is bigger because it has a positive power of 10. When a number is in standard scientific notation with a positive power of 10, then it's going to be bigger than the number 1. Positive powers of 10 are used for big numbers. Well, do the same exercise here. Determine which of these two numbers is bigger, and then confirm it by writing them in ordinary notation. Hope you gave that a shot. It should be obvious here that the number on the right is bigger. Here, it should be obvious that the number on the right is bigger, because remember that negative exponents refer to fractions. Well, fractions between 0 and 1. Since a negative exponent refers to a fraction, this number on the left must be smaller than the number on the right. You can confirm it by writing it in ordinary notation, and you can see that it really is smaller, or the kind of nerdy way to do that would be to write it like this. Again, this isn't necessary. It should be obvious from the start that this number on the left is smaller, but one more way to prove that is to write it like this. Now both numbers are in standard scientific notation, and 0 is bigger than negative 1, so the number on the right is bigger. But again, this is just a kind of humorous way to compare them. I guess some people might find it humorous. Really, it should just be obvious that because this is a negative exponent, it's the smaller number. Please pause the video and compare these two numbers. This one's a little bit trickier than the ones I gave you before. You can't just assume that the number on the left is smaller just because it has a negative exponent, because this number here is not written in standard notation. Remember, in standard notation, the numerical portion should be between 1 and 10. So if I rewrite this in standard notation, wouldn't that be this? The way to do that is to say this is 6 times 1. So we've increased this term. So this term must be getting smaller. The way to make it smaller than the number 1 is to give it a negative exponent, and we move the decimal point 1. So that gives us 6 times 10 to the negative first. And now we can actually see that the number on the left is bigger. So the number on the left is bigger here. It should have been pretty easy. Maybe some of you might have found that a little bit tricky. So anyway, the point is numbers are hard to compare if they're not in standard notation. And the standard notation, standard scientific notation, and standard scientific notation would have the numerical portion be between 1 and 10. Or another way to put it is, since these numbers are not both in scientific notation, they're a little bit tricky to compare. So you should change them so they're both in scientific notation. The other thing you could have done was change them so they're both in regular notation. You could have changed this number, the number on the left, so it's in regular notation, and again it would be clear that the number on the left is bigger. Remember, when you look at this, you should say, gee, this is a fraction between 0 and 1. When you see a negative exponent, you should think this is a fraction between 0 and 1. Let me just emphasize that one more time. A negative exponent means a fraction that's between 0 and 1. But this number over here is also a fraction that's between 0 and 1, so it's not obvious from the start which of them was bigger. Here we can see from the negative exponent that this is a fraction between 0 and 1, but this is also a fraction between 0 and 1, so it was not obvious which one was bigger until we changed them a little bit. Taking another look at some of our previous examples. Here you should look at this number and say, this is clearly a fraction between 0 and 1 because of the negative exponent, so it's clearly less than 1. There's no rewriting necessary. How about a positive exponent? When you see a positive exponent, when a number is written in standard scientific notation, you should say, this is a number that's bigger than 1. A number with a positive exponent is a number that's bigger than 1. After all, remember, 10 to the 0 equals 1. So when the exponent is negative, 10 to a negative exponent always gives you something that's less than 1. And 10 to a positive exponent always gives you a number that's bigger than 1. 10 to a negative exponent, and to even make it be, I could also say this. So 10 to a negative exponent is always a fraction between 0 and 1. 10 to the 0 is 1, and then 10 to a positive exponent is always greater than 1. So clearly this would be greater than 1. So here we have a number that's bigger than 1. Here we have a fraction that's between 0 and 1, so it should have been clear that the number on the left was bigger. Here we have a fraction that's between 0 and 1. Well, obviously that's going to be less than the number 7. Here we had two fractions that were between 0 and 1. So that makes it slightly more complicated to compare them, but not much. They look so similar, it was pretty obvious that the number on the left was bigger. Okay. Again, the purpose of all these little things we're talking about here is just to try to give you a really firm understanding and feel for scientific notation. I'm trying to improve your feel for scientific notation so that you can work with it smoothly and with high confidence when you're solving problems. That's our goal. I'm hoping that most of these little questions I've been shooting at you you found pretty easy, but hopefully by doing them we're going to build that greater feel and confidence for what scientific notation means. Please pause the video and determine which of these two numbers is bigger. And then you can confirm that by writing them in ordinary notation. Well, it should have been obvious from the start that the number on the left is bigger because it's a positive number. It should have been obvious that this was a positive number. Of course, it has a negative exponent, but we've said many times that negative exponents don't give negative numbers. So it should be obvious that this number is positive, therefore it's bigger than 0. That's the definition of positive. Another way of putting that is we were just reviewing that negative exponents mean that the number is between 0 and 1. A negative exponent means the number is between 0 and 1. That must mean it's bigger than 0. And we can confirm that one more time by writing it in ordinary notation. And then you would get this. Let's see. So the nerdy part of me is asking if there's any way to write this number in scientific notation. But I don't think so. I think it's just going to lead to confusion because after all, remember that the only way to ordinary standard scientific notation, the numerical portion is supposed to be between 1 and 10. In ordinary scientific notation, the numerical portion is supposed to be between 1 and 10. Well, there's no way to give this a numerical portion that's between 1 and 10. All right, so the number 0 does not ever get written in scientific notation. No matter how big of a nerd you are, you would not write the number 0 in scientific notation. You would just write it as 0. What I'm talking about here is not very important at all. But for example, you couldn't say this, right? You couldn't say this. This is not standard scientific notation because the numerical portion is not between 1 and 10. This would not be standard scientific notation because, again, the numerical portion would not be between 1 and 10. All right, so nobody should try to write 0 in scientific notation. That doesn't work. You just have to write it as a plain number 0. Okay, well, that was a detour. It should be obvious that 7 times 10 to the negative 4 is bigger than 0 because we know that negative exponents give you fractions between 0 and 1. We were just reviewing those ideas. Please pause the video and rewrite this number in ordinary notation. Please write this in ordinary notation. That should have been easy, and you would have gotten 6,000. Please pause the video and write this number in ordinary notation. That should have been easy, and you should have gotten this number. Please pause the video and write this number in ordinary notation. Please write this number in ordinary notation. Okay, so what I want to do now here is something that I've been trying to skirt over is I haven't really been dealing with negative coefficients. But now I just want to spend a minute or two talking about the interpretation of negative coefficients. So how would we write this in ordinary notation? Well, I think that the best way to go here is first rewrite it like this. That is, kind of take the negative sign out, factor out the negative sign. We know that that's legal because negative xy is the same as negative x times y. This is the variable x, not a multiply sign. I'm trying to show that by writing it in cursive. And then here, let's see. So now we could use our ordinary approach, focusing just on what's in the parentheses. We're going to change the power of 10 into the number 1. That involves making it bigger, so this number has to get smaller, which we do by moving the decimal point 3 places to the left. And we would end up with negative 0.006 as our answer, bringing the negative sign back in. You don't really need this systematic approach here. Maybe you could just say to yourself, well, I know that this number is going to be, we know we're going to move the decimal point 3 times, and we know we want to end up with the fraction that's between 0 and 1. So clearly it should be 0.006. That would be a more straightforward way maybe to work it out. So here we have that this is negative 0.006. Also, since we already worked out this one, you could have just said, well, this answer is just the negative of this answer and gone straight from here to here. That would be another way to work it out. Okay, so now we're seeing a little bit more how to deal with negative coefficients. So my advice for a negative coefficient is maybe kind of ignore the negative sign at the start. Take the negative sign out of the parentheses. transform the part in parentheses into standard scientific notation and then bring the negative back in. The reason I'm doing that is because if you leave the negative in, it confuses the issue of which part is getting bigger and which part is getting smaller. Keeping track of whether negative numbers are getting bigger or smaller can be a little confusing. So to avoid having to deal with the negative number, I just take it out of the parenthesis, and then I can just treat this like a normal positive number, and then just stick the negative back in at the end. I hope that makes some sense. Please pause the video and rewrite this number in ordinary notation. Well, let's see, using the same approach that we were talking about before, I would kind of factor the negative sign out of the parentheses. So now I'm just dealing with the positive number inside the parentheses. And now inside the parentheses, I already know that this number inside is 6,000. Right? 6 times 10 to the third. From our previous methods, we know that that's 6,000. And now I'll just bring the negative back. So my advice is, if you're dealing with a negative coefficient, take the negative out of the parentheses, use your ordinary methods for now turning the positive number into ordinary notation, and then stick the negative back in. So this comes out to be negative 6,000. All right, so that gives us a little bit more practice here using negative coefficients. Another question I'd ask you, so now put these in order. Rank these numbers now from biggest to smallest. Please pause the video and rank these from biggest to smallest. Well, it should be obvious that 6,000 is bigger than 0.06. That's bigger than negative 0.006, and that's bigger than negative 6,000. So they're already ranked from biggest to smallest. This is the biggest, next biggest, and the least big, the smallest. Here we're using the idea of the number line. 6,000 is to the right of 0.006 on the number line. So we would say negative 6,000 is less than negative 0.006. That's less than 0.006, and that's less than 6,000. Okay, that's just an ordinary way to compare numbers. Also, where would the numbers 1 and 0 fit in? Where would numbers 1 and 0 fit in here? Well, wouldn't they go here? I hope you paused the video and tried to figure that out. So the number 1 is between 0.006 and 6,000, right? And here's the number 0 between the positive and the negative number. Now maybe try that exercise again now. So rank these numbers from biggest to smallest and put in the number 0 and the number 1. Obviously we just did this, but I want to make sure you can do this without using regular notation. Well, let's see. So the point here is this is, we know, a very big number, so that goes first. This is, I'll start down here. So this number here is a negative number with a very big absolute value. So it goes first. So here we have a negative number whose absolute value is bigger than 1. The positive exponent here now tells us that the absolute value is bigger than 1, although it's a negative number. Now here the negative exponent tells us that the absolute value is a fraction between 0 and 1. The negative exponent tells us that, that this is a fraction between 0 and 1 in absolute value. But the negative sign means that it's actually between negative 0 and negative 1. And then this is a positive fraction between 0 and 1. And this is a positive number that's bigger than 1. You might want to pause the video now and really study this. I think this can be a little confusing here. Notice how the exponents kind of cycle. Positive, negative, negative, positive. So the exponents here I think could be a little confusing. So pause the video and try to make sure that you can convince yourself of why this is the correct pattern, and try to come up with a way to think about this so that you could have figured this out on your own easily without writing the numbers in ordinary notation. Maybe I should do some more work here and also stick in all right. So because of the positive exponent here, the absolute value, oh, I'm getting confused. Should be 10 to the third and 10 to the negative third. Okay. So yeah, it's easy to get confused here. This means that we have a negative number, and this negative exponent means that its absolute value is between 0 and 1. Here it is. It's a negative number, but because of the negative exponent, it's a fraction between 0 and negative 1. Here we have a negative number, but because of the positive exponent, it's just less than negative 1. Yeah, that's kind of confusing. All right, so I hope you'll study that to try to get a feel for what negative exponents mean. Let's see. Yeah, good enough. Okay, so where was I? I'd like you to pause the video and rewrite all these numbers in standard scientific notation. I hope you gave that a shot. This one should have been easy. It's 8 times 10 squared. You can use our standard approaches that we went over before, or you can just say to yourself that you know that the numerical portion should be between 1 and 10, and it should have a positive exponent because it's a number that's bigger than 1. Here we would have 8 times 10 to the negative 2. This needs a negative exponent because it's a fraction between 0 and 1. Or you can use the methods that we went over earlier. The systematic approach for doing that is to say we're making this number bigger, so we want this number to be getting smaller, so it needs a negative exponent. That would be 10 to the negative 2. Now, how about this down here? Well, remember my advice to you is just think of that as negative parenthesis 0.08. Now, just change the thing in the parenthesis into scientific notation. Well, we already did that. We already said that that was 8 times 10 to the negative 2. So the whole thing is... So the point is, I guess what I'm basically telling you is if there's a negative coefficient, you basically kind of ignore the negative sign at the beginning and just change the rest of the number into standard scientific notation, and then you just tack the negative sign back on at the end. And then we can do the same thing with the negative 800. That's just negative times 800. Well, inside the parenthesis now we have a positive number. We know that 800 is 8 times 10 squared. So that gives us negative 8 times 10 squared. Now I'd like you to take these numbers, arrange these numbers in order from smallest to biggest, and also include the numbers 1, -1, and 1. So put these numbers in order and include these numbers. Please pause the video and do that. Now, of course, it would be very easy to put them in order if you just go back to the ordinary notation we just talked about. But I hope you tried to do that by focusing on the scientific notation. Well, let's see. We know that 8 times 10 squared, this is a number that's bigger than 1. Here we have 8 times 10 to the negative 2. That would be a fraction between 0 and 1. So those are the easy ones with the positive coefficients. Then with the negative coefficients, we know that this means now a fraction that's between 0 and -1. The negative exponent still means a fraction. Negative exponents, maybe that's the most useful trick, huh? Negative exponents mean fractions. So this is still a fraction. Now it's a fraction between 0 and -1. And positive exponents mean non-fractions, numbers that are bigger than 1 in absolute value. So here they would go in order. Of course, that's obvious if you remember that in ordinary notation, the numbers were -800, -0.08, 0.08, and 800. So if this is giving you any trouble, please pause and study this pattern so that you can start to feel more comfortable with it. Please pause the video and put these numbers in order. Put them in order from smallest to biggest. Please rank these in order from smallest to biggest on the number line. Try to do that without writing them in ordinary notation. See if you can rank these without writing them in ordinary notation, just by focusing on the scientific notation. Well, I hope you gave that a shot. So maybe it's easiest to start with the biggest number. I think it should be clear. This number is the biggest. Here we have a number that's bigger than 1 because of the positive exponent. And then we have negative exponents give you fractions between 0 and 1. Now we're dealing with the negative numbers. Well, the next one is this one, because remember, the next on the list should be a fraction between 0 and -1. The next on the list should be the fraction between 0 and -1. Well, the negative exponent here gives us a fraction whose absolute value is between 0 and 1. And because of the negative sign, its actual value is between 0 and -1. And then the last one that we haven't used yet is 7 times... No, oh, I forgot. Getting careless here. So this should be 7.3 -7.3. Okay, here we have this. Here we have a number whose absolute value is bigger than 1. So its real value is less than -1. We can list them in order like this. All right, so here they are listed. So I guess the basic pattern here is numbers with positive exponents always have big absolute values. A number with a positive exponent always has an absolute value that's bigger than 1. And a number with a negative exponent always has an absolute value that's less than 1. Numbers with positive exponents always have absolute values that are bigger than 1. Numbers with negative exponents are always fractions whose absolute value is between 0 and 1. A number with a negative exponent is going to be a fraction whose absolute value is between 0 and 1. That's why the negative exponents end up in the middle here, and the positive exponents end up on the end. Something else that we can do now here, pause the video and add these 3 numbers. Where would these 3 numbers go? Well, remember, this positive exponent makes this number bigger than 1. This negative exponent makes this number a fraction between 0 and 1. This negative exponent combined with a negative coefficient makes the number between 0 and -1. So, positive exponent, positive coefficient, a number bigger than 1. Positive coefficient, negative exponent, that gives a fraction between 0 and 1. Negative coefficient and negative exponent, that gives a fraction between -1 and 0. And negative coefficient and positive exponent gives a number that's less than -1. Now, please confirm this ordering by writing each of these numbers in ordinary notation. Well, I hope you did that on paper. So using the methods that we've used in the past, well, let's just practice this one more time to make sure those methods are crystal clear. Here, I think it's clear we're going to move the decimal point 4 times. But should we move the decimal point to the left or to the right? Well, we already now should be clear in our minds that when you have a positive power of 10 like this, we're going to end up with a big number, a number that's bigger than 1. So the only thing that makes sense is moving the decimal point to the right. So that's one way to see that we should move the decimal point to the right, because we already know from our knowledge of scientific notation that this number should be bigger than 1. And you can only get that if you move the decimal point to the right. Alternatively, we can use the more technical or mechanical method that we talked about before. We can say that when we're getting rid of the power of 10, it's like we're replacing it with the number 1. So this portion of the number would get smaller, so this portion has to get bigger, and the way to make this portion bigger would be, again, to move the decimal point to the right. So now this up arrow tells us, again, we should move the decimal point 4 places to the right. So those are 2 equally good ways to do it. So you can use whichever of those 2 methods you like to show that this number would be 73,000, which, as we've said, was bigger than 1. Let's review one more time how to turn this number into scientific notation. Well, you could say to yourself that it's clear we're going to move the decimal point 4 times, so the only question is, should we move the decimal point to the left or to the right? And we already know that negative exponents should give us fractions between 0 and 1. From the negative exponent, we know we're going to get a fraction between 0 and 1. Well, that means the only thing that makes sense would be to move the decimal point to the left, because that's the thing that would give us a fraction that's between 0 and 1. And if we move the decimal point 4 times to the left, we would get this number. We have to put in 3 zeros as placeholders. Or using our more technical approach, if we're going into ordinary notation, we're removing the 10 to the power, which is like we're replacing it with the number 1. Well, then this portion of the number would be getting bigger, because 1 is bigger than 10 to the negative 4. So this portion has to get smaller, and the fact that this is a down arrow tells us, again, to move the decimal point to the left. We want to move the decimal point to the left to make this portion of the number smaller than we started. So that would be the other way to see that we should be moving the decimal point to the left, and again, we would get this answer. As far as the negative numbers are concerned, we could say negative 7.3 times 10 to the negative 4 is negative parenthesis 7.3 times 10 to the negative 4. Now disregard the negative sign and just change the number inside the parenthesis into ordinary notation. Well, you could use our normal methods for doing that. In this case, we've already done that. We did that up here. So using our ordinary methods, we would get that the number inside the parenthesis, ignoring the negative sign, was this. So putting the negative sign back in would give this. Whoops, I didn't mean to do that. Maybe it's a little late to be mentioning this, but I hope everyone is familiar with these greater than and less than signs, right? So the way I learned this when I was in elementary school is that you think of the greater than sign as if it was like an alligator mouth, and the alligator would always be turning to eat the bigger number, because alligators have a big appetite, right? They want to eat the big numbers. So in each of these cases, the opening of the mouth, the sign is opening up towards the bigger number. So this means this number is less than this number. Well, presumably by this point you must have figured that out. Okay, so let's see here. We have, here's negative 1. And then this number here, again, with the negative coefficient, the trick that we've been discussing has been take the negative sign out, so to speak, of the parenthesis and just focus on putting the number in parenthesis into ordinary notation, which we could do using ordinary methods. We already saw that 7.3 times 10 to the fourth is 73,000, and then you just stick the negative sign back on. So there we would get negative 73,000. And here we have these in ordinary notation. All right, I wanted to do one more careful review of how to change numbers in scientific notation into ordinary notation, because I'm just about ready to wrap up with this portion of the videos and move on to the next topic. So I guess while we're at it, pause the video and rewrite this number in standard scientific notation. Well, we know that the numerical portion should become between 1 and 10. So I would write this so the numerical portion is between 1 and 10. That would give us this, and then what power of 10 should we put on here? Well, there's two ways to do this. One way, kind of using our understanding, would be we know this has to be a positive exponent because we know the original number was bigger than 1. If you want to express a number that's bigger than 1 in scientific notation, we know you're supposed to use positive exponents. So that would be the quick way to see this should be positive 2 instead of negative 2. Or we can use our more mechanical approach. We can say to ourselves that it's as if we're changing the 820 into 8.20, which would involve making it smaller. So the other portion of the number has to get bigger. And what we imagine is that we're replacing the number 1 with 10 to a power. Well, then this has to be a positive exponent in order to make this portion bigger than the portion that it's replacing. So that again would confirm that this is the right way to write the number. It's not actually necessary to put on this 0 here, so you can leave that 0 in or take it off. If you were worried about significant figures, whether the 0 was there could have some meaning. When you're writing numbers carefully to show significant figures, this 0 could have a meaning, but that's an issue that I don't want to get into in these videos. So if you're not thinking in terms of significant figures, these two numbers both represent the same number. So you can write it whichever way you want. I guess this one is simpler. Please pause the video and rewrite this number. What did I want to do here? Rewrite this number in standard scientific notation. Well, we need to make the numerical portion between 1 and 10. We know we've moved the decimal point 2 places here, so the question is, should this be 10 to the 2 or 10 to the negative 2? Well, the common sense way to do this is just to say to yourself, we know that we started with a fraction between 0 and 1, and we know that those are represented by negative exponents. So it's got to be negative 2. So that would be the common sense way to see that this has to be negative 2. Or, alternatively, you could use our mechanical approach that we've demonstrated many times in this video. The mechanical approach is to say that the numerical portion got bigger when we moved the decimal point, so this portion should get smaller. Since we think of it as replacing the number 1, it has to be 10 to the negative 2 and not to the positive 2 to make this portion smaller, and that would confirm again that we have a negative exponent. All right, so like I said, I want to wrap up this portion of the video. We've gone over a lot of different topics here, so I want to make sure that even though we've gone over many topics, I want to make sure that some of the topics haven't kind of erased the most important topic we went over. The most important topic we went over was how to take a number that's in ordinary notation and write it in standard scientific notation. And the other very important topic we went over was how to take numbers that are in scientific notation and rewrite them in ordinary notation. Those are the most important skills that we've gone over so far in the video. Those are the things that have to be boringly easy for you. If those skills are still not boringly easy for you, then you should just pause the video right now and do a bunch more practice until they are boringly easy. I don't think I need to give you any more practice problems like that because you have plenty of practice problems in your notes from this video that you could go back and redo, or you could just make up some problems on your own perhaps to practice. But make sure at this point that you pause the video and don't proceed until it is boringly easy for you to take numbers in scientific notation and rewrite them in ordinary notation, and until it is boringly easy for you to take numbers in ordinary notation and write them in standard scientific notation. Please make sure that's a skill that you've completely mastered and that's boringly easy for you and that you never make any careless mistakes on before proceeding with the rest of the video. Okay, well, hopefully now you've gotten pretty comfortable with moving numbers between different representations in regular and scientific notation. What else is there that's important for everybody to know about scientific notation? Well, I think the other main skill that people need to know about scientific notation is just how to use scientific notation on their calculator. So I'd like to now go over how to use scientific notation on a calculator. This is a little tricky because everybody has different calculators, but most calculators work with scientific notation in pretty similar ways. So I'm going to be using the TI Inspire calculator, or actually I'm using an emulator for the TI Inspire calculator. But your calculator will probably deal with scientific notation pretty similar to this. Okay, so let's see here if I'm using this. I've actually just started using this Inspire software, but let's see, it says press menu. I want to do some calculator stuff. Okay. For example, let's say that you wanted, let's say that you wanted to do 5.2 times 10 to the third, I'll call it 10 to the 8th plus 6.9 times 10 to the 9th. Now, there is a way to do this type of calculation without using a calculator. Maybe I'll go over that later in this video, I don't know. To avoid making careless mistakes, probably most people would be best off using a calculator to do this type of calculation. So how would we enter this onto the calculator? So let's see, 5.2 times 10 to the 8th, 5.2. Now, how do we enter scientific notation? Well, I think the best way for most students is just to write it in just the way it looks on your sheet. So times 10. And then we need to put in an exponent of 8. So on this calculator, this is the exponent key. There's some calculators where the exponent key looks like this, I think. Some calculators, the exponent key looks like this. But most calculators nowadays, I think the exponent key looks like this. Anyway, you'll have to figure out on your own calculator where the exponent key is. And we can see here we're going to put in 10 to the 8th. Done with the exponent. Then I'm going to add 6.9 times 10 to the exponent 9. And then we just hit enter, and here we get our answer. Now, here's one of the main things I wanted to discuss with you. Now, probably most of you already know how to interpret this, but just in case, what does this notation here mean, 7.42E9? 7.42E9. Well, perhaps you already know that that's just the way that scientific notation is shown on a calculator. So this really means 7.42 times 10 to the ninth. So unfortunately, calculators usually don't display scientific notation the same way it would be written in your own scratch work or in your textbook. They use this little shortcut. So when you see E, the E stands for scientific notation, and it tells you the power of 10. So notice the E is basically telling us the exponent, but you're expected to know that the base is 10. Anytime they use this E for exponent, they mean that the base is 10. So the answer here was 7.42 times 10 to the ninth. Okay, well that's one of the main things I wanted to go over right there, just what this E notation means. So let's do another example. Let's say we have 6.72 times 10 to the negative 11 plus 8.4 times 10 to the negative 10. So now would be a good time for you to take out your calculator and try this on your calculator to make sure that you can get the right answer. So please pause the video and use your calculator to figure out the answer to this. You don't need to try working this out on paper. I mean, if you want to challenge yourself, you can try to work these out on paper. But my main goal here is to learn how to do these calculations on a calculator. So I'll go back to the calculator here. 6.72 times 10 to the negative 11th plus 8.4 times 10 to the negative 10th. By the way, just so there's no confusion, obviously, if we were using a real calculator, the display would be up here in this region. But since I'm using an emulator software, this particular software happens to put the screen display off to the side of the keypad. So here's what the keypad looks like for the TI Inspire, and here's what the display would look like. If this was a real calculator, the display would be up here, but putting it off to the side, I guess, gives us a little bit more room so that it's a little bit more visible. And let's just practice again interpreting what this E notation means. This means 9.072, and then the E means times 10 to the negative 10th. So that would have been our answer in this case. Now, some of you may know that there's an alternative way to do scientific notation. There's actually a special key on most calculators. It usually looks like this, the capital E key. Most calculators have a key like this. This gives you an alternative way to enter scientific notation. For example, in this case, it would be written, to write the same calculation, it would have been 6.72, and then we would type E, and then negative 11 plus, now I'm going to type in this portion. So that was the 8.4 times, oops, nope. Now I wanted to use the scientific notation key, 8.4, and then E here would be 10 to the negative 10th. Okay. Get that right. And obviously we get the same answer as before. So this is simply an alternative way to enter it. If you understood the E notation over here, you can understand it over here. Notice that when you hit the E key, it only puts one E in the display usually. And we already know that this is an alternative way of writing scientific notation. 6.72 E negative 11, that means 6.72 times 10 raised to the negative 11th power. And 8.4 E negative 10, that means 8.4 times 10 raised to the negative 10th power. This is an alternative way to do scientific notation on your calculator. There are some advantages occasionally to using this EE key, but I actually, since I suppose the people that are watching this video, most of the people watching this video are people that are having some difficulty with this material, I would actually recommend doing it this way instead. For a beginner or for someone whose math skills are weak or for someone whose calculator skills are weak, the most useful thing is to try to enter things on your calculator so that they look the same as in your scratch work. People make the fewest mistakes if they can enter things in their calculator so that it looks the same as their scratch work. You'll make fewer mistakes that way, and it'll be easier for you to check your work. So in that light, this is a slightly better way to put it into the calculator because it just looks more like we would write it in our scratch work. In our scratch work, we don't write down these little e's for scientific notation. In our scratch work, we write the scientific notation like this. So I think that for a beginner, for someone whose math skills might be weak or whose calculator skills might be weak, it's actually better not to use the scientific notation key. It's better just to type things in as times 10 to a power. That way it's easier to check your work and you're less likely to make mistakes. If you're already used to using the scientific notation key and it works fine for you and you don't make mistakes, then that's okay. You can stick with that. If you're not set in your ways for how you do that, I would recommend that for beginners, it's actually better not to use the scientific notation key. Just for the record, the advantage of the scientific notation key is that there's certain circumstances where you need fewer parentheses when you're using a scientific notation key. There's some situations where you would need a parenthesis when you don't use the scientific notation key, but you would not need the parenthesis with the scientific notation key. And for someone whose math skills are a little stronger or whose calculator skills are stronger, that can be a significant advantage. But not for someone who's finding this material to be challenging or difficult. That's not, if you're finding this material a little challenging, or if you tend to make careless mistakes, or if you often make mistakes on your calculator, then again, I think it's better not to use the scientific notation key. Instead, just to write the numbers like this. Okay, so there we go. Let me give you another example here then, so we could have 8.2 times 10 to the negative 15 plus 8.5 times 10 to the negative 14. Please do this calculation on your calculator. Well, 8.2 times 10 to the negative 15th plus 8.5 times 10 to the negative 14th. And you can see I'm going to follow my own advice. I'm not going to be using the scientific notation key. I'm going to be writing the numbers so that they look more like they would look like in my scratch work. And then we would write our answer in the scratch work as 9.32 times 10 to the negative 14. Let's do 5.8 times 10 to the 13th minus 6.2 times 10 to the 14th. Please pause the video and try that on your calculator. I hope you're doing all these calculations on your calculator. Even if you think you already know how to do it, remember our goal here is to learn how to do these easily and boringly so that we avoid making careless mistakes. Well, on my calculator here, I'm going to do that as 5.8 times 10 to the 13th minus 6.2 times 10 to the 14th. And then here's our answer, negative 5.62. Notice that the exponent is not negative here. It's the numerical portion that's negative. We haven't really worked much so far with scientific notation that comes out negative. But anyway, here's an example that came out negative. The numerical portion was negative. The power of 10 was still 10 to the 14th. All right, so I'm just hoping that these examples will make it very clear what this E notation means, which most calculators use to show scientific notation. Then we could try 8.4 times 10 to the third times 1.7 times 10 to the ninth. Try this on your calculator. Whoops. So over here on this calculator, that would be 8.4 times 10 to the third times 1.7 times 10 to the ninth. Okay, and again, if you feel more comfortable using the scientific notation key for these types of problems, that's fine. But my recommendation for beginners who tend to make mistakes is to not use the scientific notation key and instead to type in the numbers so that they look exactly like they will in your scratch work. That, once again, makes it easier for you to check yourself and check for careless mistakes. In this particular case, we don't actually have to put it in the parentheses. You'd get the same answer either way. But again, for a beginner, if you're not sure about that, the safest thing is just to put in the same parentheses in the calculator that you have in your scratch work. All right. By the way, I hope that you're doing all these on your calculator, and I hope that you're writing the answer on your scratch work to get practice with this E notation. So this now would mean 1.428, and then remember this means times 10 to the 13th power. Notice that the calculator always puts the numbers in standard scientific notation, so the numerical portion is between 1 and 10, as we discussed earlier. 8.9 times 10 to the 6th divided by 8.3 times 10 to the 20th. Try this on your calculator. So that would be I hope you're using a calculator that has a fraction template. On the TI Inspire, the fraction template is here above the divide key. So I hit Control and then the divide key and I get the fraction template because that allows me to enter my answer or enter the numbers so they look exactly the same as in the scratch paper. 0.3 times 10 to the 20th. So by using that fraction template, we're able to enter these in so they look exactly the same as they do on the scratch paper. And then we can hit enter and get our answer. I keep getting these little bees here because I'm trying to use my my stylus here before I changed the window. I need to change the window over here to the drawing program first, in case you were wondering where those bees keep coming from. All right, so let's see. This gives me 1.07229 times 10 to the negative 14th power. Now, you might just round this off to something less than this because not all these digits are necessarily significant. But anyway, that's what this means over here. Okay, so I did want to review here that, again, I hope you're using a calculator that allows you to enter fractions so that they look the same on the screen as they do on your paper. That's the best way to avoid making mistakes. If your calculator does not have a fraction template, then this gets trickier to enter. If your calculator doesn't have a fraction template, then you have to use parentheses to show the calculator where the denominator starts and stops. Or in that case, at least you have to use parentheses if you're entering the scientific notation in this form. So anyway, there's no reason. I was at first I was thinking I might cover how to do these types of problems if your calculator doesn't have a fraction template. But actually, there's not much point because you can get a good calculator that has a fraction template for about 15 bucks. So there's really no reason for anybody to have an old-fashioned calculator anymore that doesn't allow them to enter fractions directly. So if your calculator doesn't allow you to enter numbers like this, why not just shell out the 15 bucks and get a better calculator that does. So I don't think I'm going to go through how to use those old-fashioned calculators since everyone, I think, should be able to get a calculator that allows you to enter fractions so they look the same on the screen as on your page. Okay, so anyway, we just went over how to divide scientific notation here on our calculator. I suppose I could give you another example. We might have 55 times 10 to the 13 squared. Try figuring this out on your calculator. Well, on a good calculator, you should be able to just type this in so that it looks pretty much the same on your calculator as it does on your scratch work. Since we're squaring this whole thing, we're going to have to put it in parentheses. But it shouldn't be hard to remember to put in the parentheses on your calculator here, because you would normally write down the parentheses on your own scratch work in this case to show that we're squaring both the numerical portion and the power of 10. And we'll raise this to the second power. Notice that in this case, the number I'm entering is not in standard scientific notation. That's no big deal. We've got a number here that's not in standard scientific notation, but that's no big deal. The calculator doesn't care whether you enter numbers in standard scientific notation or not. It's still going to give us the right answer. Okay. So the TI Inspire here, even when you get a pretty big answer, it doesn't necessarily put it into scientific notation for you. But I think I can Control Enter. There we go. So on the TI Inspire, if you want to put something into scientific notation, you would hit Control and then Enter to get it in a different form. So here's our answer. 3.025 times 10 to the 29th power. Or if you want to see the number in its full glory, the calculator also wrote it out this way. But most calculators don't write out numbers that are this big. They just go straight to scientific notation. Okay, so here's how we could raise something to an exponent. Now, all of these little things that we did, these are all things that you could have done on paper, with pencil and paper by yourself. It's nice if you know how to do that. That would be a good thing to go over. But it's probably not really crucial, because you can always do it on your calculator instead, or in most cases. Now, there are some situations where you might need to be able to do these on paper if you were like studying for a test that doesn't let you use a calculator. But most of the time, you can just do these calculations on your calculator. So I just wanted to go over that, and I just particularly wanted to go over this E notation. Let's put in something else. So let's say I was going to do, what did I want here? 5 to the 12th power. All right, so I just wanted to point out here, again, this calculator normally in normal mode doesn't put things into scientific notation, but then I can rewrite this, so it would put it into scientific notation. So I would see that 5 to the 12th equals 2.44141 times 10 to the 8th. Okay. My only point with this last little example is that sometimes even if you don't use scientific notation yourself, the answer will come out so big or small, then it's most convenient for the calculator to give it to you in scientific notation. This calculator is a little bit unusual in that it normally does not put numbers in scientific notation unless you ask for it. But here I could ask for it to put it in scientific notation. Okay, so what is there left for us to do in these videos? I think we've covered what's most important. What I'm going to do next is I'm going to go over how to do arithmetic with scientific notation without a calculator. We've already gone over how to use your calculator to do arithmetic with scientific notation. And the next topic, I think the last topic I'm going to go over in these videos is how to do arithmetic without a calculator. So for example, how would you add, say, 8.2 times 10 to the 4th plus 6.7 times 10 to the 5th? How could you add these two numbers if you couldn't use a calculator? Or how could you multiply these two numbers or divide them? Or how could you take a square root in scientific notation? I think that's what I'm going to go over next. I would say the next part of this video is optional. In the sense that if you're allowed to use a calculator in your class, if you're allowed to use calculators on the tests that you're preparing for, then you don't really need to know how to do this arithmetic. And the fact is, even if you do learn how to do this arithmetic on paper, I would recommend that you still do these calculations as a double check on your calculator anyway, just to make sure you're not making careless mistakes. So this is kind of optional material. So why would it be useful to go over this? Well, first of all, I think it's nice not to be completely reliant on your calculator for some of these simple calculations. There is some value to knowing how to do these without your calculator. Also, some of you might be taking a course where you're not allowed to use a calculator on the tests. Sometimes in a class, the instructor might not let you use a calculator. In that case, it might be very important to know how to do calculations with scientific notation on paper. Also, if you're trying to prepare for standardized tests, some standardized tests don't let you use calculators. For example, say the MCAT. If you're trying to prepare for the MCAT exam, you can't use a calculator there. In fact, that's probably maybe one of the most important groups of people that this part of the video might be useful to. If you're preparing for your MCAT, then it's a very important skill to know how to do arithmetic on paper with scientific notation. So if you are preparing for the MCAT, I definitely would encourage you to watch this part of the videos. Very often, scientific notation is a very important part of figuring out the answer on the MCAT. Very often, it's helpful to put numbers into scientific notation on your own and then do the calculations with them on the MCAT. So if you're preparing for a test like the MCAT where you're not going to be allowed to use a calculator, then this part of the videos is important for you to master. On the other hand, if you are allowed to use a calculator in your class, then maybe you might want to skip this section. If you're allowed to use a calculator in your class, and if you're maybe falling behind in your class, and there's a bunch of other topics that you need to learn, then this next section is not a top priority. So I would say that this section of the video should not be a top priority for people that are allowed to use a calculator on the test they're preparing for. If you're behind in your class, or if you have many other topics you have to learn, you might want to skip this next section of the videos. On the other hand, if you are not allowed to use a calculator on the test you're preparing for, then I would encourage you to try to learn this material. Okay, so to go over this material, let's see here. We've got, first of all, I'm going to remind you of some basic math facts. Here's a few basic math facts that are going to be useful to us. Do you know a way to rewrite this in a simpler form? Please rewrite this in a simpler form. Well, I hope you were able to come up with this. This is what's called adding like terms. So 5x plus 3x is 8x. Just like 5 oranges plus 3 oranges is 8 oranges, or 5 apples plus 3 apples is 8 apples. Now I'd like you to pause the video and rewrite this in simpler form. Please rewrite this in a simpler form. Don't spend too much time on that. All right, I hope you didn't spend too much time on that. That was kind of a trick question. There is no way to rewrite this in simpler form. There is no way to combine these terms. So that was a trick question. We cannot combine those terms. Okay, because they're not like terms. You can combine these because they're like terms. They're both in terms of x. But here we have an x and a y. You cannot combine those terms. Just like you can't really add 5 apples and 3 oranges. Or there's no way to simplify 5 apples plus 3 oranges. You can't combine these terms. All right, some other math facts that I wanted to review with you. This is preparation for doing arithmetic with scientific notation. Let's see. Would you agree? So this is x times y times a times b. Would you agree that that could be rewritten as x times a times y times b? If you wanted to, you could even put parentheses around these. This is just one of the ways we could rewrite this. So x times y times a times b, that could be rewritten as x times a times y times b. That's called the commutative property. It doesn't matter what order you multiply things in. So it doesn't matter what order you multiply things in. I wanted to remind you of that. So this is x times y divided by a over b. I just want to remind you that that could be written like this. Could be separated out into 2 fractions. You're probably more used to going from right to left here. If you remember how to multiply fractions, you should know that you multiply fractions by just multiplying the numerator and multiplying the denominator. So if you think about it that way, it should be clear that the left side is equal to the right side. There's a couple other ways we could rewrite this, but here's one way I wanted to remind you of. So I just wanted to remind you that when we have a fraction with a product in the numerator and the denominator, it could be split up into 2 separate fractions. We'll see later how that is useful to us. Can you find any other way to rewrite this square root? Pause the video and ask yourself if you know any way to rewrite this square root. Well, did you come up with this? This is a correct way to rewrite that square root. We can rewrite the square root like this. This might not seem simpler, but this is simply a trick that's sometimes useful. You can evaluate the 2 square roots separately. By the way, is this true? Is this true? No, you can't do this. You can't split up a square root for an addition, so this would be wrong. You can only use this trick for multiplication. One of the hard things in math is not just remembering what's legal, but what's not legal. Okay, so those are a couple of math ideas that we'll be using. I have a few more math ideas that I want to review with you here, all about exponents. Say we have x to the a times x to the b. Please pause the video and rewrite this. Do you know another way to rewrite this? Well, do you remember that when you're multiplying numbers with the same base, you add the exponents? So it could be rewritten like this. I hope it's clear that I'm trying to write a b here, not a 6. I'm trying to write that kind of like in cursive, so you can see that's a b and not a 6. All right, so when you're multiplying numbers with the same base, you add the exponents. Do you remember that terminology? Remember, this number here is what we would call the base, because it's down below in the basement, so to speak. And this number up here is the power or the exponent. So here the base is the number x, and the exponent is the a. So I'll be using that terminology. Pause the video and see if you can come up with another way to write this. Okay, this was another trick question, actually. There is no really good way to rewrite this. There's no way to combine the terms. We cannot combine the terms here again. We cannot. Combine the terms. If you want to get fancy here, you might try removing a common factor from the two terms, but that won't really simplify things. That's not really what I was going for here. So for the most part, there is no good way to rewrite this. Notice that then there is a way to rewrite the product here, but there is no way to rewrite this sum. You certainly don't just add the exponents here. So you need to know what's legal, but also what's not legal, what you don't have a good formula for in math. So of course, if we were subtracting, there would be no way to combine the terms either. X to the a minus x to the b. There's no good way to combine those either. X to the a divided by x to the b. Please pause the video and see if you remember how to rewrite this. Even if you didn't remember, you might be able to figure it out from here. Notice that when we're multiplying two numbers with the same base, we add the exponents. So maybe it's intuitive that when you divide two numbers with the same base, you're subtracting the exponents. So here we ended up subtracting the exponents, x to the a minus b. Do you see how that's kind of like the counterpart to what we did with the multiplication? All right, so that's another rule for exponents that I wanted to remind you of. On the other hand, just to remind you of some things that there isn't anything you can do anything with. There wouldn't really be any way to combine these. You can't add the exponents here because we don't have the same base. This adding the exponents trick only works when you have the same base. So for this expression, there really is there's no way to rewrite this. There's no way to rewrite this. And the same if you had x to the a over y to the b. There wouldn't be a very good way to rewrite this because the top and the bottom of the fraction don't have the same base. This is x to the a all raised to the b power. Pause the video and see if you remember how we can rewrite this. Well, it turns out that in this situation, you multiply the exponents. So this would be x to the a times b power. By the way, a lot of these exponent rules can be kind of proven by doing little examples. For example, let's say that you had x squared times x to the third. Well, doesn't that really mean x times x times x times x times x, right? Here's the x squared, and here's the x to the third. But that would give you x to the fifth, right? And then you'd ultimately have 5 x's being multiplied times each other. And now we've just kind of proven, or at least given an example for why this rule works. We've shown that when you're multiplying two numbers with the same base, you really should add the exponents. It's possible to give proofs, or at least to give little examples that show why most of these other rules make sense as well. I'm not going to go into that. That would take us a little far afield from scientific notation. But the point is, if you started to forget some of these, you might be able to figure them out again by doing a little example. The best thing, though, is, I suppose, just to have these rules memorized. Well, now I realize there is one or two more other formulas that I wanted to give that are going to be useful to us. Oops. Let's see. No. How about This is x times y raised to the a power. See if you can pause the video and think of another way to write this. Well, did you know that that could be written like this? We can distribute the exponent over the two bases, so to speak. So that's one more rule that I wanted to make sure was clear to you. By the way, can we distribute this exponent? There is no distribution that you can do here. This does not equal x to the a plus y to the a. So you can only distribute the exponent, so to speak, over multiplication, not over addition. I just wanted to remind you of what is legal and what's not legal with this new rule as well. Okay, anything else that we need? I think that might just about cover it for the math skills that we're going to need here. If you didn't already know all these little facts that I went over, maybe now would be a good time to go back and re-watch this section of the video. Go back and try to answer these questions again from memory and make sure that you do understand these math facts. These are all things that have to be easy for you. There's no way you're going to do a more complicated or more difficult problem if you have to stop for 30 seconds to remember these basic facts. So if there were some facts here that you didn't know or that weren't obvious to you or that weren't easy to you, before you proceed with the video, it would be a good idea just to review these basic ideas. Write these down over and over from memory a couple of times until these are easy for you. It's not enough to kind of know this material. You've got to know this material really well to avoid making careless mistakes and to be able to do harder problems. Okay, so now let's go to work with scientific notation. So let's say we've got 5.2 times 10 to the 8th plus 2.3 times 10 to the 8th. Pause the video and see if you can figure out how to add these two numbers. Well, this would just be 5.2 plus 2.3. That's 7.5 times 10 to the 8th. Do you see which of the earlier math facts am I using here? Do you see that what I'm really using is this? 5x plus 3x is 8x. Do you see how that applies here? Who's playing the role of x? Well, the 10. The term with the 10 to the 8th, that's playing the role of x. Both of those have those same term. Notice how that doesn't change in the final answer. The x here and the x here turns into an x here. What we add as the coefficients, the 5 and the 3, or in this case, the 5.2 and the 2.3. Hopefully now you can see why we didn't kind of add the 10 to the 8ths. The 10 to the 8ths, but that wouldn't really follow the pattern that we established up here. Okay, so this is our example for how to add numbers in scientific notation. So how do you add numbers that are in scientific notation? Basically, you simply add the coefficients, and the power of 10 stays the same. You add the coefficients, and the power of 10 stays the same. Please pause the video and add these two numbers. Hope you gave that a shot. Well, again, I guess I'll ignore that. Let's see, where was I? So to add these two numbers, again, we would simply add the coefficients. 3 plus 8 is 11. And then we still have 10 to the 7th. Here's another way that you might look at this. You might say to yourself, I'm going to factor out the 10 to the 7th. Do you see how we could factor out a 10 to the 7th here? You could factor out 10 to the 7th from the first term, that would just leave a 3, and factor out 10 to the 7th from the second term, that would leave an 8. And then 3 plus 8 would give you the 11. So that's another way to see why the 10 to the 7th term is not changing. It's the 3 and the 8 that are changing. But did you notice here that this is not in standard scientific notation? So I hope that you went further and changed this into standard scientific notation. Well, we need to make the numerical portion between 1 and 10. This was bigger than 10. So that got smaller. Therefore, I know I need to make the exponent bigger to balance off that change. Now I move the decimal point 1 place to go from here to here, so I'm going to change the exponent by 1. I made it 1 bigger. So here would be the best way to write the answer. Okay, so I hope that didn't give you too much trouble. So it's always good after you add numbers. They might not be in standard scientific notation anymore, so you might want to change them to the standard scientific notation. Although that's only if that's kind of your final answer. If you're just going to use this for other calculations, it doesn't really matter very much whether it's in standard scientific notation or not. Please pause the video and add these two numbers. I hope you gave that a shot. Now, did you notice that this one was trickier than the previous cases? You can't just use the previous trick and add these directly because we have different powers of 10. You can't just add these directly because they have different powers of 10. So we have to come up with another trick here. Were you able to come up with the trick on your own? Well, the trick is we need to change these so they both have the same power of 10. I'm going to change these so they both have the same power of the 10. So I'm going to change the first number. So instead of 10 to the 7th here, I'm going to change that into 10 to the 8th. Now notice that what I did here is I made the power of 10 bigger. Therefore, to balance that, I need to make the numerical portion smaller by moving the decimal point 1 place to the left. I changed the exponent by 1 unit, so I'm moving the decimal point 1 place. Now these are both in scientific notation, and now I can say 4 plus 0.2, that's 4.2 times 10 to the 8th. So here would be our answer. So now we've learned a new trick. The earlier examples I gave you all had the same power of 10. What do you do when you don't have the same power of 10? Well, when you don't have the same power of 10, you need to change the numbers so they do have the same power of 10. Do you see which of the earlier math facts that we went over are we using here? Well, this is the reason why I reminded you earlier that if you have, say, 3x plus 4y, there's no way to combine these. Earlier we saw that if you have unlike terms, you can't combine them. Unlike terms can't be combined. Well, we started here with unlike terms, so there was no way to directly combine these. But here we could use a trick. We could change one of the numbers so that now they do have like terms, so that they both have like terms now. They both have 10 to the 8th, and then we can use our earlier method for adding two things together. Okay, so as our earlier work reminded us, you can't add 3x plus 4y. You can't add unlike terms, so you can't add 2 times 10 to the 7th and 4 times 10 to the 8th. You can't add these directly. Instead, we have to change it so they're like terms. I hope you were able to see how we were able to change this. I wanted to make this into a 10 to the 8th to match this 10 to the 8th. Since this number got 1 exponent bigger, we moved the decimal point 1 place to the left here to make that number smaller. please pause the video and add these numbers. Remember, you should be trying to do these on paper, not using your calculator. The whole point here is to learn how to do these problems on paper, although it would be good practice to use your calculator to check your work, but try to do these on paper. I hope you gave that a shot. Now, we can't add these directly because they have different powers of 10. So I'm going to change one of the numbers. I'll change the second number so that it also is the same power of 10, 10 to the 9th. This got bigger, so this should get smaller. I had to change this exponent by 1 unit, so I moved this decimal point once. So this ends up being 4.42. Times 10 to the 9th. Do you know how to add these decimals? It's 4.1 plus 0.32. You need to line them up so that the decimal points line up. And then we have 0 plus 2 is 2, 4. So that's how I got this number here. Okay. Okay. So here again is the trick. If you're trying to add two numbers, then they don't have the same power of 10. Change one of them so they do have the same power of 10. Now, why did I change the second number here? Why didn't I change the first number into a 10 to the 8th? Well, you could do that. That's perfectly fine. If you want to, you could change this number so that it's 10 to the 8th. Usually, though, it's better to change the smaller number. That way your answer is more likely to come out in standard scientific notation. It's better to change the smaller number because that way your answer is more likely to come out in standard scientific notation. After all, this number here is, the point is that in the answer, the bigger number is kind of going to overwhelm the smaller number, right? This is a power of 10 bigger than this number, so that the answer is going to be pretty close to this. Well, this is already in standard scientific notation. So if I leave it like this, then the final answer will be already in standard scientific notation. If you changed this number so that it would be a 10 to the 8th, then your final answer wouldn't come out in standard scientific notation. So you can change either of these two terms. You can change the 10 to the 8th into a 10 to the 9th, or you can change the 10 to the 9th into a 10 to the 8th. But it's a little bit better. You're more likely to get an answer in standard scientific notation if you change the smaller number. Okay. Please pause the video and do this calculation on paper without using a calculator. I hope you did that. I hope you really are trying all of these on paper. The only way to learn this material is to do it yourself. You're not going to learn much just from watching me do these problems. Remember, your goal here is to get to the point where these calculations are boringly easy. So even if you think you can get this right, you should still do it on paper so you can get to that point where the problems are boringly easy for you. I can't add these directly because they don't have the same power of 10. Now, the trick we learned earlier is we could change either term, but our answer is more likely to come out in standard scientific notation if we change the smaller term to match the bigger term. This is the smaller term. So I'm going to change this into 10 to the negative 9 so that it matches this term here. Let's see, so I just made this term bigger, right? Negative 9 is a bigger number than negative 10. On the number line, negative 9 is bigger than negative 10. 10 to the negative 9th is a bigger fraction than 10 to the negative 10th. We saw that earlier when we were working with powers of 10 way back in ancient history. We saw 10 to the negative 2 is bigger than 10 to the negative 3. 10 to the negative 3 is bigger than 10 to the negative 4. So I need to make this number smaller by moving the decimal point one place to the left. only one place because we only changed the exponent by 1. And then we would have 1.1 plus 0.32. We have to be careful to line up the decimals. I think that gives 1.42. And the 10 to the negative 9 doesn't change. 0.32, 10 to the negative 9s, and 1 plus 1.1, 10 to the negative 9s gives 1.42, 10 to the negative 9s. Okay. Now, if you did this a different way and got the same answer, that's fine. You could have changed this number so that it's expressed as 10 to the negative 10th. That would be fine. But then your answer wouldn't come out in standard scientific notation, and there would be one more step to change it to standard scientific notation. So this is a slightly better approach. Pause the video and try this problem on paper. We can't add them directly because they're not the same power of 10. We've learned that it's a little bit better to change the smaller number. So I'll change this to be 10 to the negative 11 too. 10 to the negative 11 is bigger than 10 to the negative 12 because negative 11 is bigger than negative 12 to the right on the number line. So this is going to get smaller. And again, we're just going to move it by 1 decimal point. Again, the whole point here is we're trying to prepare for tests where we can't use a calculator, so I'm not going to do this calculation with a calculator either. I'll do it on paper. .92 times 10 to the negative 11. Okay, there's our answer. Please pause the video and do this addition. This might have looked a little bit different than the problems we did earlier. Were you able to figure out how to handle this? Maybe the best trick to use here is to rewrite this term like this. That's totally legal, right? 10 to the negative 5th is the same as 1 times 10 to the negative 5th, but putting in the 1 just makes it easier for us to add these two terms because now they're in the same form. And now it should be pretty clear that this is 9 times 10 to the negative 5th. Okay, so here's a special case. We saw how to handle this. We can stick in a number 1 to make it easier to multiply these two numbers. And then once we do that, they both have the same power of 10. So we didn't have to do any adjustments. We could just add them directly. Try adding these on paper. Well, I'm going to change these here. So one thing we might try to do is make a prediction here. What would you predict before you actually did this calculation? What would you predict? Well, I hope that you can see that we could predict that the answer here is going to be approximately this. It'll just be a little bit more than 8 times 10 to the 13th. That is, it's going to be pretty much the same as this number. Do you see why? Well, that's because this number is way smaller than this number, right? there might not seem like there's that much difference between 10 to the 13th and 10 to the 9th. 13 and 9 seem like they're pretty close, but remember that's a difference of 4 decimal points. There's a difference of 4 decimal places between these two numbers, or 4 zeros. Well, two numbers that differ by 4 zeros, there's a big difference. So even though this is a big number, it's still much smaller than this number. So adding this relatively smaller number to this relatively bigger number shouldn't make much difference at all. So the answer here should just be a little bit bigger than 8 times 10 to the 13th. Well, let's see if we can confirm that. I want to change this so that it's also 10 to the 13th. We've seen that it's better to change the smaller exponent, so it matches the bigger one. This just got bigger, so this has to get smaller. Now, 13 is 4 units bigger than 9, so I'm going to move the decimal point 4 times. So the decimal point starts here, and then it moves once, twice, 3 times, 4 times. We have to put in a few zeros to accommodate that, so we ended up with this. Since I changed the exponent by 4 units, I moved the decimal point 4 units. And now you can see, as I was saying before, this number is really a lot smaller than this number. Now it's much easier to compare them, and we can see this number is a lot smaller than this number. So we can see now that the answer is 8.0005. Times 10 to the 13th. As we saw, it's pretty much the same as the original number that we started with here, just a little bit bigger than 8 times 10 to the 13th. The way you would write these is like this, if you're going to add them. 1, 2, 3, 5. You'd line them up like this. And then we get this is our answer. Okay, so the point here is that when you're adding two numbers that are in scientific notation, actually the answer can kind of usually be approximated by just ignoring the smaller number. If the smaller number is more than just an exponent or two away from the bigger number, it can almost just be ignored. It's not going to make that much impact on the final answer. This might be useful again if you're like taking a standardized test like the MCAT, where all you have to do is pick out the right choice. So if you were doing this calculation on the MCAT, there wouldn't really be any point in doing this addition. You could just say, well, I'm just going to pick the choice that's pretty close to 8 times 10 to the 13th. There's probably only going to be one choice that's in that vicinity. It's not even necessary to add these if all you need is the approximate answer. Okay. So something that we learned in that previous example here, let's say you're comparing, say, this number and this number. What can you tell me about the comparison between these two numbers? You might want to pause the video and think about that. Well, what should jump out at you is that this number is way, way, way bigger than this number. This number is way bigger than this number. How many times bigger? Well, remember, this would be 5 with 30 zeros to the right of it, and this would be 3 with 20 zeros to the right of it. Now, this is a very big number, but it's still really small compared to this one. So the point is that even if the power of 10 only differs by a couple of units between two different numbers, those numbers end up being very different, very, very different numbers. That's just a point about scientific notation I wanted to make. 30 is pretty close to 20. 30 is only slightly bigger than 20. But 10 to the 30 is way bigger than 10 to the 20. Remember, this is the bigger than sign. Well, when you write something like this, you mean way bigger. So 10 to the 30 is way bigger than 10 to the 20th. Even though 30 is only a little bigger than 20, 10 to the 30 is way bigger than 10 to the 20. Pause the video and try this calculation. We can't subtract these directly because they have different powers of 10. So I'm going to change the smaller number so that it's also in terms of 10 to the 8th. This got 1 unit bigger in the exponent, so I'm going to move the decimal point 1 place to the left here to make this number smaller. Now this is going to be 8.9 minus 0.35. I have to line up the decimal points, put in a 0 here. Now it looks like I have to do some borrowing. 10 minus 5 is 5. 8 minus 3 is 5. So we get 8.55. Times 10 to the 8th. Okay, so this is the first example we've done that involved a subtraction. But I hope you were able to figure out that the rules for subtraction are pretty similar to the rules for addition. Pause the video and try this problem. We have to make them like terms, so I'll change the smaller number so that it's also in terms of 10 to the 11th. This got bigger, so this is going to get smaller. Remember, the goal here is not just to get these right, but to get these right every time without making careless mistakes. So I really encourage you to put in these arrows every time. It really helps to actually write down these arrows so you make sure that you know whether you should be moving the decimal point to the left or to the right. So then we would have 4.5 minus 6.2, lining up the decimal points. Well, it looks like we need some more borrowing. 10 minus 2 is 8. Borrow again. 14 minus 6 is 8. .88 times 10 to the 11th. If you want to, it would be perfectly fine to also practice your calculator skills by checking all these on your calculator, but remember first to do them on paper. As I've mentioned, if you wanted to, instead of changing this term into 10 to the 11th, you could have changed this term so that it's expressed as 10 to the 10th power. But if you change the bigger term, then your final answer probably won't come out in standard scientific notation, and you'll need another step to change it into standard scientific notation. Pause the video and see if you can figure out how to do this problem. Now, did you see this is different from all the earlier problems we did? Now we are no longer trying to add numbers in scientific notation. Now we're multiplying two numbers in scientific notation. That might have been clearer if I'd stuck in some parentheses here to show we're basically multiplying these two numbers that are in scientific notation. Well, here's the trick. Would you agree that we could rewrite this like this? Isn't that the commutative property of multiplication that we reviewed earlier on? This is the reason why we went over this idea. We saw earlier that when you're multiplying a bunch of terms, you can multiply them in any order you want. When you're multiplying a bunch of terms, you can multiply them in any order you want, and you can stick the parentheses in wherever you want. It doesn't matter where we put the parentheses because the order that we multiply these terms isn't going to change the final product. Well, that's the basic idea that we're using here. Now, why was it helpful to rewrite it like this? Because we know what 8 times 2 is. That's 16. And we know what 10 to the third times 10 to the fourth is. That's 10 to the 7th, because we're adding the exponents, right? 3 plus 4 is 10 to the 7th. That's another math fact that we went over earlier. Here's now we're using another math fact. We saw that when you're multiplying two numbers with the same base, you add the exponents. When you're multiplying two numbers with the same base, you add the exponents. So now we're using a couple of the other math facts that we reviewed earlier. So that would give us this. Okay, good. So here we have our answer. Now, notice when you're multiplying numbers, it's not necessary for the powers of 10 to be the same. When we multiply numbers, it's not necessary for the powers of 10 to be the same. If we were adding these numbers, it would be necessary for the powers of 10 to be the same. So that's something that we have to be careful about here. It might be easy to get confused about that. We don't need the same power of 10 here because we're multiplying, not adding. Now, the answer here did not come out in standard scientific notation, so maybe we should do one more step and write this in standard scientific notation. Because 16 is not between 1 and 10, so I'll change it to 1.6. Now, this got smaller. 1.6 is smaller than 16, so this should be bigger by 1 unit. The exponent should be bigger by 1 unit. We moved the decimal point 1 place here. So this should be bigger by 1 unit. So this would be maybe the best way to write our final answer. So what we just went over here now is how to multiply numbers that are in scientific notation. Here's how you multiply numbers that are in scientific notation. Now would be a good time to compare this to how we added and subtracted numbers. Notice that the method is very different. When you're adding numbers or subtracting numbers, the powers of 10 have to be the same. But when you're multiplying, the powers of 10 don't have to be the same. It's important not to confuse those two. Pause the video and try this. Well, we can rewrite that like this. When you're multiplying two numbers with the same base, you add the exponents. And now to write it in standard scientific notation, we had to move the decimal point to the left to make this number smaller. So this power of 10 should now get bigger by 1 unit. All right, so again, now we've carried out our goal here of multiplying two numbers that are in scientific notation. Pause the video and try this. Maybe I should have written this like this to show that we're thinking of this as multiplying two numbers in scientific notation. But the parentheses make no difference. You can multiply four numbers in any order you want. -5 plus -4 is -9. You have to be extra careful to avoid careless mistakes when you're using negative numbers. But -5 plus -4 is -9. We're still adding the exponents. So don't think of yourself as doing subtraction here. We're still adding, it's just that we're adding negative numbers. Remember that -8 is a bigger number than -9. On the number line, -8 is to the right of -9. So this is the right way to change this into scientific notation. Pause the video and try this problem, please. Oops, gotta be careful here. So the calculation here is -11 plus 5, which is -6. Be careful to avoid careless mistakes when you're working with negative numbers. -5 is bigger than -6. So this is the right way to change this into standard scientific notation. So take your time and write down all the calculations on paper when you're working with negative numbers. It's easy to make a careless mistake there. Please try this on paper. All right, looks like this is the answer. So a point I wanted to make here is, do you remember, how would you do this? You might want to pause the video and think about how you would do this calculation. Well, the main thing you should say to yourself is that it's not really even hardly worth bothering to do this calculation, because this would be almost the same as 5 times 10 to the 20th, right? 5 times 10 to the 20th is way bigger than 3 times 10 to the 10th. When you add a number that's much smaller to a number that's much bigger, it hardly changes the outcome at all. So this would still be almost 5 times 10 to the 20th. The 3 would just be many decimal points away from the 5, so it would be hardly worth even working it out. But notice that didn't apply when we're multiplying. 3 times 10 to the 10th is still much smaller than 5 times 10 to the 20th, but it still makes a big difference to the multiplication. The answer here is not similar to 5 times 10 to the 20th. It's much bigger than 5 times 10 to the 20th. So the point I'm trying to make is when you're adding a much bigger number to a much smaller number, the much smaller number makes very little difference. But when you're multiplying a much bigger number by a much smaller number, every number makes a difference. You can see that because, for example, what is, say, 1 million plus 2? Well, 1 million plus 2, that's almost 1 million, right? It's just 1 million and 2. The 2 hardly makes any difference. But what is 1 million times 2? Well, that's 2 million, which is a lot different than 1 million. All right, so anyway, I just felt like mentioning adding a much smaller number doesn't change the bigger number very much, but multiplying by a much smaller number does make a big change. So the approximation ideas that we talked about for addition certainly would not apply when you're multiplying. When you're multiplying, you have to take every single number into account, and hopefully this little example here gives you a sense for why that is. Just to give you an example here, if you were a millionaire, would you get excited about earning $2 more? Well, I don't think so. If you were a millionaire, you wouldn't really care very much about whether you earned $2 more or not. But if you were a millionaire, would you be excited about doubling your money? Well, I think that even if you were a millionaire, you would still be pretty happy if you learned that you were doubling your money. Well, that just shows you that multiplying by a small number still has a big effect, whereas adding a small number doesn't make much effect. Okay, these are things you don't necessarily have to think about every time when you're doing calculations with scientific notation, but these are some of the issues that naturally come up. The point here is when you're working with scientific notation, oftentimes one of the numbers might be much bigger than the other number. So this was a reasonable time to talk about what happens when you're combining numbers that are very different in size. When you're adding numbers that are very different in size, the smaller number makes hardly any difference. But when you're multiplying numbers that are very different in size, the smaller number still makes a big difference. Please pause the video and try to do this calculation on paper. Well, we need to multiply the 6.23 and the 5.2 together. That would be a little bit of work to do on paper. First of all, though, I'd like to point out that we could just approximate. 6 times 5 is approximately 30. And then 8 plus 5 is 13. So the answer here is approximately 30 times 10 to the 13th. And in many cases, this might be a good enough approximation because what's more important in scientific notation? The coefficient or the power of 10? Well, after all, the power of 10 here is exact. It was only this coefficient that we were approximating. Well, the power of 10 is what's way more important, right? The power of 10 is what's way more important. Because that tells you how many decimal places or how many zeros you have. So this probably is not really going to be really 30. It's going to be more like, I don't know, 34, 35, 36, something more than 30. But at least we're getting the right number of decimal places here, which is going to be by far the most important part of the answer. When you're approximating, it's much more important to get the right power of 10 than to get the right coefficient. Of course, we could now rewrite this as 3 times 10 to the 14th, which is still just an approximate answer to the original calculation. Now again, the coefficient here shouldn't really be 3. It should be maybe 3 point something or 4 point something. It's going to be bigger than 3, but that's not going to make much difference to the final answer. What's really important is getting the right exponent on the 10. For example, there's not that much difference. Let's see. So let's say we talk about someone who's got $5 million or $6 million. Well, there's a big difference there. That's a sizable difference, but that's not nearly as important as the difference between someone that's got $5 million and $500,000, right? Now this is a big difference. Well, these are two numbers that differ in the power of 10. These are two numbers that differ in the number of decimal places. This would be 5 times 10 to the 6th, and this is 5 times 10 to the 5th. You wouldn't want to look at these two numbers and say, gee, they have the same coefficient, so they're pretty much the same number. This number is 10 times bigger than this number. This number is 10 times bigger than this number. So by the same token here, over here what we have is 5 times 10 to the 6th and 6 times 10 to the 6th. So there's some difference between these. I'd rather have $6 million than $5 million, but it's not nearly as important as getting the right power of 10. That makes a big difference to the answer. So the coefficient has much less influence on your answer than the exponent does. In scientific notation, the coefficient is much less important than the exponent. So it's perfectly fine in many cases just to approximate the coefficient. In particular, say if you're working on the MCAT. If you're prepping for the MCAT, on the MCAT, you would rarely want to actually do this calculation on paper. You would just approximate. There's probably only going to be one choice that's relatively close to 3 times 10 to the 14th, so there's no need to do more work here. Okay, so the point is, if you're preparing for a standardized test where you're not allowed to use a calculator, it's perfectly okay to approximate the size of the coefficient when you're doing scientific notation. Now, we can't approximate the exponent. That one we have to get exactly. I can remind you how to do this if you had to do it exactly. Now, we saw that when you're adding, you have to line up the decimal points. When you're multiplying, you do not line up the decimal points. When you're multiplying, you don't line up the decimal points. Instead, you just put both numbers, you line up the rightmost digits. You line up the rightmost digits. Now we just ignore the decimal point. 2 times 3 is 6. It's just like long multiplication. 2 times 2 is 4. 2 times 6 is 12. 5 times 3 is 15, carry the 1. 5 times 2 is 10, plus 1 is 11, carry the 1. 5 times 6 is 30. Then we add these together. 4 plus 5 is 9. So I'm just using the technique for long multiplication here. And now, so far we've just been ignoring the decimal points. Now we put the decimal points in. Since there are 3 decimal points in our 2 original numbers, there should be 3 decimal places down here. That's the mechanical method. There's 1, 2, 3 decimal places up here, so there should be 3 decimal places in the answer. And so we ended up with 32.396. Notice that that's pretty close to 30. Here we had 30, here we had 32. It doesn't make that much difference compared to this 10 to the 13th over here. So in this case, the approximation was pretty good. The important thing was to get the right power of 10. But if necessary, here's a little reminder on how to do long multiplication and how to do long multiplication when you have decimals. You don't line up the decimals when you're multiplying the same way you would when you were adding. All right, the big lesson here is that when you are multiplying numbers in scientific notation, in many cases, it's okay to just approximate the coefficient, because the coefficient has much less impact on your answer than the exponent on the 10 does. Let's see, so suppose we had, say, 8.7 times 10 to the 5th times 3.2 times 10 to the 6th. Please pause the video and calculate an answer here. Well, we could rewrite this as 8.7 times 3.2 times 10 to the 5th times 10 to the 6th. And one thing you should have said to yourself is that if you're taking a test where you're not allowed to use a calculator, you would probably be allowed to approximate the coefficient here. You'd be allowed to approximate the numerical portion if you're not allowed to use a calculator. So probably the best thing here is just to do an approximation. Well, 8.7 is approximately 9, 3.2 is approximately 3. Notice how it makes sense to round this number up and this number down. And over here we have 5 plus 6, which is 11. I'm using approximate signs still to show that this is still only an approximation to the original calculation. Now I'm going to change the numerical portion so that it's between 1 and 10. That involved making it smaller. So I should make the power of 10 bigger by 1 unit since I moved the decimal place by 1 unit. So here would be the approximate answer. Okay, and that's probably good enough. It's probably not necessary. If you're not allowed to use a calculator, it's probably not necessary to come up with an exact answer in this case. The important thing is to be able to get the approximate answer. The important thing is to get the right power of 10. The numerical portion, as we've seen, matters much less. For the record, we could work out 8.7 times 3.2. Now we're not trying to line up the decimals, we're lining up the rightmost digits. 2 times 7 is 14, carry the 1. 2 times 8 is 16, carry the 1. 3 times 7 is 21, carry the 2. 3 times 8 is 24, plus 2 is 26. 7 plus 1 is 8, 1 plus 6 is 7. Since there is a total of 2 decimal places in the original two numbers, there should be 2 decimal places here as well. Looks like I made a mistake. Rats. Let's see here. Did I make a mistake? Or maybe not. So let's see. Yeah, actually, I think I got that right. Okay, good. So it's always much easier to do calculations with a calculator, huh? So, and you can see that the approximation here was pretty good, right? There wouldn't be too much difference between 2.7 times 10 to the 12th. The exact answer here would be 2.784 times 10 to the 12th. Well, these extra digits don't make a big difference. What matters is getting the right power of 10. All right, so I think we've done a bunch of multiplication problems here. Let's see what we do. We did some negative exponents, positive exponents, negative and a positive exponent. And we talked about how you can approximate by just doing the numerical portion approximately. It's the power of 10 that really matters. Please pause the video and do this calculation. Well, this is addition. We know that we can only add if we have like terms. So we need to make these both into like terms. We saw that you can change either term, but it's usually more convenient to change the smaller term. So I'm going to change this so that it's also 10 to the 5th. That involved making this number bigger, so this number has to be smaller, which happens by moving the decimal point to the left. We changed the exponent by 1 here, so I should move the decimal point 1 place. And that ends up giving me 2.3. And notice we don't alter the power of 10 here. These are just the like terms. So this is still 10 to the 5th. Notice we would not add the exponents in this case. In this case, we don't add the exponents. So here would be our answer. Please pause the video and do this calculation. Well, you should have gotten here that it doesn't matter what order we multiply these numbers in. So we can rewrite them like this, so that similar terms are next to each other. 3 times 2 is 6. And here, since we're multiplying two numbers with the same base, we add the exponents. All right, well, did you see? What I wanted to do now was make sure that we're not confusing adding numbers in scientific notation and multiplying numbers in scientific notation. Now would be a good time to make sure you can tell the difference between adding and multiplying. So one big difference is that notice that in order to add numbers in scientific notation, they both have to have the same power of 10, because we can only add like terms. But to multiply numbers in scientific notation, it doesn't matter whether the powers of 10 are the same or not. we can multiply any terms, whether they're like or not. Another difference is that notice here, the powers of 10, once they were both the same power of 10, that didn't change when we did the addition. But when we multiplied the numbers, we ended up adding the exponents. So I think you can see how if someone was in a hurry, they might start to confuse these two methods. Or I think how you can see how, maybe this is clear to you now, but maybe you can see how in a few weeks or a few months, it might be easy to start forgetting how to do these things or confusing them. So I just wanted to try to clarify these approaches. So to add numbers, you need to have the same power of 10. To multiply numbers, you don't need the same power of 10. Maybe I'll give you a little analogy here to maybe make more sense to you. Do you remember how to do this addition? Well, remember that you can't add these directly. You need a common denominator. So first of all, we'd have to give these both a common denominator. 1/2 is the same as 2/4. Only now that they have the same common denominator, only now can we add them and get 3/4. You can't add numbers unless they have the same denominator. You can't add fractions unless they have the same denominator. Now, do you remember how to do this multiplication? Well, when you're multiplying fractions, you don't need a common denominator. So this would just be 1 times 1, which is 1, and 2 times 4, which is 8. You just multiply the numerators and multiply the denominators. All right, well, maybe this was an unnecessary example, but I just wanted to give you another example that's kind of similar to what we had here. So when you're adding fractions, you need to have common denominators. Just like when you're adding numbers in scientific notation, you need to have like terms. If you don't start with like terms, you have to change one of the terms so that they are the same power of 10. Just like if you're not starting with a common denominator, you have to change one of the denominators so that they are a common denominator. On the other hand, multiplying fractions is actually a lot easier than adding fractions, because when you're multiplying fractions, you don't need to have a common denominator. And by the same token, multiplying numbers in scientific notation is actually easier than adding them, because you don't need to have the same power of 10. Hopefully you're not having too much trouble digesting all this stuff that we've been going over. If you're getting still a bunch of questions wrong, or if you missed these questions, or if you started to forget how to do addition of scientific notation, maybe now would be a good time to go back and just redo all the little examples we just did. You should keep redoing these examples until they're boringly easy. So don't move on until the stuff that we've already gone over is boringly easy. Of course, you can always make up examples for yourself, right? You can make up an example of adding or multiplying numbers in scientific notation, and you can do it on paper. And then you can always check yourself to see if you got it right by also doing it on your calculator. So if these problems are not boringly easy for you yet, now would be a good time to pause the video and redo them or make up some more problems on your own. Just with some random numbers, and keep doing them until they become boringly easy. Remember, you can always make up problems on your own, because then you can check whether you got the right answer by doing it on your calculator. Please pause the video and see if you can figure out how to do this calculation. Now, this is something that we haven't gone over explicitly, so we haven't gone over a method for this, but you might have been able to figure out how to do this. So one trick that we can use here is rewrite this like this. This is legal. That uses one of the math facts about fractions that we talked about earlier. And the advantage of that is now we can do the two divisions. 8 divided by 2 is 4. Do you remember how to do this division? Well, remember we reviewed that when you're dividing two numbers with the same base, you subtract the exponents. When you're dividing two numbers with the same base, you subtract the exponents. So here we have our answer. This is the correct answer. This is what you would get if you did this division. So now we've used a couple more of the math facts that we talked about earlier. Let's see here. We used this one here. We talked about how you can take kind of this glob and break it up into the product of two separate fractions. That's what we used for this step going to here. So we focused on the division of the numerical portion and the powers of 10 separately. We know that's legal, right? Because as we were just reviewing, if you were going to multiply these two fractions, you would just multiply the two numerators to get this numerator and multiply the two denominators to get this denominator. So if it's legal to go from right to left here, it must be legal to go from left to right. And then we also used the idea we talked about earlier of dividing numbers with the same base. When you're dividing numbers with the same base, you just subtract the exponents. So that gives us this. Please pause the video and do this calculation. Well, we can rewrite that like this. 6 divided by 2 is 3. When you're dividing two numbers with the same base, you subtract the exponents, and here's our answer. Pause the video and try this division. Nine divided by 3 is 3. Be careful here when you're subtracting the exponents. 4 minus 12 is negative 8. So here we got 3 times 10 to the negative 8 power. Okay, that's another example. Pause the video and try this problem. I hope you really are trying all these problems on paper. With the goal of getting to the point where they are boringly easy. 9 divided by 2 is 4.5, 4.5. That's how we do that division. Now, let's be very careful with the power of 10 here. So we're going to have negative 13 minus 24. It's always best to be really careful when you have negative numbers. We need to subtract the top exponent minus the bottom exponent. I don't know if I quite made that clear before. We're subtracting the top exponent minus the bottom. Well, that would end up being negative 13 plus 24, right? The two negatives cancel. So we end up with a positive exponent of positive 11. Yes. So this answer ends up being very big. By the way, you should have been able to predict ahead of time that this would be very big, because just by looking at this, we can see that the bottom here is a much smaller number than the top. Since the bottom of the fraction is a much smaller number than the top, we would expect that the bottom is going to go into the top many, many times. And that's what ended up happening here. I haven't mentioned this, but maybe it would be a good idea to try to get predictions for these calculations as you're going through these. Please pause the video and get an answer. Did you try to get a prediction here? What would we predict? Well, we're dividing a very small number by a very big number. If you divide a very big number into a very small number, don't we predict that we're going to get a very small number as the answer? So it's really good to build your intuition here by getting a prediction in this case. We predict a very small number as the answer. Let's see, because we're dividing a very small by a very big number. We're going to do here negative 15 minus 24, so that comes out to be negative 39. We can already see we are indeed getting a very small number. We got to do 4 divided by 6. You could reduce that to 2/3. This is not standard scientific notation. Maybe you already know that 2/3 is about 0.67, or you could work that out off to the side. Now I'm going to change this so that it's in standard scientific notation. Well, I need the numerical portion to be between 1 and 10. It got bigger, so I need to make this smaller. Negative 40 is smaller than negative 39. 10 to the negative 40 is smaller than 10 to the negative 39. And we moved the decimal point 1, so we changed the exponent by 1. And we certainly matched our prediction. We were predicting a very small number as the answer, and that's what we got. Please pause the video and try this calculation on paper, without using a calculator, of course. I hope that you tried to get a prediction ahead of time. What could we predict here? Well, we're dividing a very big number by a very small number. A very small number would go many times into a very big number. So our prediction is a very big number. So let's see here. That would give us 8.3 divided by 4.1 times 10 to the 15th, 10 to the negative 8. So as far as the power of 10 is concerned, this is going to be 15 minus 8. Well, the negatives cancel, and that ends up being 15 plus 8, or positive 23rd. And we've already confirmed that we're getting a very big number as our answer. One advantage of making this type of prediction is, as I've mentioned, it's easy to make careless mistakes when you're working with negative signs, but you can catch that mistake if you've already predicted what type of answer you want. Now, how would we do this division? Well, this would be now long division. But actually, I hope that you thought to yourself, gee, we might as well just approximate this. Remember, if you were taking a test where you were not allowed to use a calculator, the purpose of the test is probably not to test your skills at long division. So they'll probably allow you to just do an approximation with the coefficient here. So we can just approximate this as 8 over 4, rounding both of them down. And that would end up giving us this as our answer. All right, and that's probably a good enough approximation to the answer here. I don't know if it's even necessary for us to review how to do long division here with these numbers. I guess we may as well. First of all, you have to move the decimal point so that there's no decimal over here. All right, so we're getting that this is, say, around 2.02. Well, you can see 2 times 10 to the 23rd, that's pretty close to 2.02. And in any case, the most important thing is, remember, the coefficient isn't all that important. What matters is getting the right power of 10. This numerical coefficient doesn't matter so much. What matters is getting the right power of 10. So if you're taking a test where you can't use a calculator, you should probably feel free to approximate this type of division. Please pause the video and try this calculation. Well, first of all, I hope that you predicted. Now, both of these numbers are pretty small, but the one on top is much smaller. The number on top here is much smaller than the number on the bottom, so we should predict a very small answer. A very small number as our answer, because the number on top here is way smaller than even the number on the bottom. Negative 15 minus 3 equals negative 15 plus 3, or negative 12. So we can already see we really are getting a very small number. Here is the answer. And now the numerical portion, well, I hope that you thought of approximating in this case. We can approximate the division here. We don't need to get this numerical portion that exact anyway. 6/8 is the same thing as 3/4. This is coming out nice. Maybe you already know that 3/4 is 0.75 as a decimal, or you could work that out on paper. Now this didn't come out in standard scientific notation, so I'll adjust it. Let's see, that involves making this bigger, so this should be smaller. So I need a smaller exponent here. I moved the decimal point one place here, so I changed the exponent by 1 unit, and here we have our answer. As we predicted, a very small answer. And again, we were reviewing, feel free to approximate the coefficients if you're not allowed to use a calculator. That'll usually be fine. What matters is making sure you get the right power of 10. Well, looks like we've done a bunch of examples of that now. Please pause the video and do this calculation. First of all, we can predict. Now, the top here is a very big number, but the bottom is still way, way bigger. The bottom of the fraction is still way bigger than the top, so we would predict a very small answer. I hope you really are trying to get these predictions. Trying to get these predictions on these problems will really help you to build your intuition and understanding of scientific notation, I think. This problem is just a little bit different than the others because the bottom here doesn't seem to have a coefficient. But that doesn't really make any difference. We can still rewrite this like this. (14 minus 20 is -6. As we predicted, the answer came out quite small. So here's the answer. So I just wanted to review what to do when one of the numbers doesn't quite look like normal scientific notation. If it makes you feel happier, how could you have written this bottom number in standard scientific notation? Well, if it makes you happier, you could have written the bottom number like this, couldn't you? And then you could have done this, and then we would have gotten the same answer anyway. Did I go over how to do that for powers of 10? Well, I've got over a lot of stuff here. Let's see. Yeah. So we talked about here an example. This number here didn't seem to be in normal scientific notation. Well, we dealt by that by just putting this number 1 in front of it. Let's see, where were we? Please pause the video and do this calculation. Now we're shifting gears for a second and going back to subtraction. In order to subtract, you need to have like terms. We do have like terms here. Some people might be uncertain how to proceed here, though, because the second number doesn't seem to have a coefficient. But doesn't that just mean we could write it like this? You can always stick the number 1 in front as the coefficient. And now it should be clear that here's how to do the subtraction. Okay, so I think maybe I forgot to talk about this when we were doing subtraction before. So here's how to handle just a bare power of 10 without a coefficient. You can always add a coefficient by sticking in the number 1. Well, please pause the video and see if you can figure out how to do this. Okay, so let's see. This is something new that we haven't talked about before. The first thing you could do is this. This uses one of the math facts we talked about earlier. We talked about how you can distribute an exponent over a multiplication. So I've distributed the number 2 over the multiplication. 3 squared is 9. And here we use another math fact. Remember that when you have a number to a power all raised to another power, you end up multiplying the exponents. So here's our answer, 9 times 10 to the 8th. So now we've learned yet another skill for scientific notation. Now we're seeing how to raise a number in scientific notation to a power. And we can review what are the math facts we were using here. I guess now we finally got to use this fact. We used the fact that you can distribute an exponent over a multiplication. And then we also used this math fact that if you end up with a number to a power all raised to another power, that's the case where you multiply the exponents. We know when you're multiplying two numbers with the same base, you don't multiply the exponents, you add the exponents. Here's the case where you multiply the exponents. So this fact and this fact are the math facts that we just used for our new skill with scientific notation. Please pause the video and try this calculation. Maybe we should start trying to get predictions again. What do you get if you have a pretty big number and you multiply it by itself 3 times? Well, we're going to get a really big number. A really big number, a number that's way bigger even than this. Well, let's work that out. So we distribute the exponent over the 2 portions of the number. 2 times 2 times 2 is 8. This means 2 times 2 times 2, which is 8. And here this would be 4 times 3, which is 12. And that did come out to be a big number, a number that was even much bigger than the fairly large number that we started with. What are the common mistakes people make here? Well, how do a lot of students do this calculation? A lot of students say that 2 to the 3rd power is 6. They confuse it with 2 times 3. So this would be wrong, right? So be careful about that. Raising something to an exponent is not like multiplying. So don't just multiply here. I guess it's especially confusing because in this case, we did end up multiplying. When you have a number to a power and that whole thing is raised to another power, then you really do end up multiplying. But what you're multiplying are the exponents. We're never multiplying the exponent times the base. Remember that this number here, the 2, is called the base. This number 3 is called the exponent. So when you have a base raised to an exponent, please don't multiply the base times the exponent. On the other hand, in this case, we do end up multiplying the 2 exponents times each other. So I guess it can be kind of confusing. It's important to do a bunch of practice here so that you get to the point where this is boringly easy and you can get these problems right without making any careless mistakes. Remember that if you really are preparing, say, for a standardized test like the MCAT, you're going to be under pretty harsh time pressure during that test. You really have to know this material very well to avoid making careless mistakes under time pressure, if that's the reason why you're going over this material. Okay, let's see here. Please pause the video and try this calculation. Well, first we can write that. We'll raise each individual term to the power. So this is 3 times 3 times 3 times 3. Here we just multiply the exponents. 4 times -5 is -20. As usual, we need to be careful with the negative sign. Oh, I forgot to get a prediction. Rats. Well, going back, what should we have predicted? We have a pretty small number here. What we have here is a fraction. What happens when you multiply a fraction by itself? Every time you multiply a fraction by itself, it gets even smaller. So we should have predicted a very small answer. Predict a very small answer. Well, it doesn't matter that I forgot to do the prediction because I'm sure that when you were doing the problem on your own, I'm sure you tried to get the prediction. That's what matters. So here we predict a very small answer because we're multiplying a fraction by itself, and that makes it an even smaller fraction, right? For example, what happens if you do 1/2 times 1/2 times 1/2 times 1/2? Every time you multiply, it gets even smaller. This ends up being 1/4, 1/8, 1/16, right? you can see that every time you multiply a half by a half, it becomes an even smaller fraction. You get a fraction of a fraction of a fraction of a fraction. So here we would predict a very small answer. So let's see, 3 times 3 times 3 times 3, that's 9 times 9, right? This is 9 and this is 9. So that would give us 81. This didn't come out in standard scientific notation, so I'll change it. Negative 19 is 1 unit bigger than negative 20. I had to move the decimal point one place here. Okay, so here we have our answer. Please pause the video and try this calculation. Well, now I'm going to remember to do a prediction first. I think this is similar to before. We're taking a fraction and multiplying it by itself 5 times. Well, a fraction of a fraction of a fraction of a fraction of a fraction, that's going to end up being an even smaller fraction. So we predict an even smaller answer. An even smaller number than we originally started with here. In fact, a lot smaller. So this will be 2.1 to the 5th power times 10 to the negative 5th to the 5th. Now, working over here, remember this is negative 5 times 5, or negative 25. In this situation, we multiply the exponents. And over here, I hope that you thought of using the approximation technique. I hope you didn't actually try multiplying 2.1 times 2.1 times 2.1 times 2.1 times 2.1 on paper. There's really no practical need for that skill, right? If you were ever taking a test that required you to get an exact answer here, I'm sure they would allow you to use a calculator. And if you were taking a test that did not allow you to use a calculator on this type of problem, I'm sure that it would be good enough just to have an approximate answer. For example, on the MCAT, it's fine to approximate because there'll probably only be one choice that's in the right range. So obviously the obvious approximation here is just to do 2 to the 5th power. Since, after all, remember the thing that's most important is getting the power of 10 right. This coefficient matters much less. So let's see, we have 2 times 2 times 2 times 2 times 2. So this would be a 4. This would be a 4 times 2. So that would give us 4 times 8, or 32. I'm using some little tricks here. But you could also just do the multiplication. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Now we have to put this in standard scientific notation. We move the decimal point once. Negative 24 is 1 unit bigger than negative 25. And as we predicted, we got actually a much smaller number than we started with, because we were taking a fraction of a fraction of a fraction of a fraction multiple times here. All right, here's our answer. I hope that nobody said that 2 to the 5th power was 10. I hope everyone is not making the mistake of just multiplying the base times the exponent. We never multiply the base times the exponent. Instead, the exponent tells you how many times to multiply the base by itself. So this is not 2 times 5. Please try this calculation on paper. Well, first of all, you would predict a very big answer, an even bigger number than we started with. Probably a much bigger number. This would give us 5.4 to the third power times 10 to the seventh. So working with the power of 10 first, that's what matters the most. Here we do multiplies. This is 7 times 3, or 21. Here we can multiply, right? Because when you're raising a number to a power to another power, that's when you multiply the exponents. And over here, again, we should not actually do the calculation on paper. We should do an approximation. So we'll call this 5 to the third. This won't be that great of an approximation because 5 is not that great an approximation to 5.4, but it's pretty sure to be good enough. Again, the power of 10 matters much more than the coefficient. Well, 5 times 5 times 5, that's 25 times 5. And 25 times 5 is 125. We have to change this into standard scientific notation. Here I moved the decimal point 2 places, so I need to make this exponent 2 units bigger. And we certainly did get a very big number as our answer. Okay, so that was another example. Please pause the video and try this. Predicting here would be a little bit trickier. You could get a prediction here, but if you got a prediction here, that's great, but I think I'll give that a pass this time. And instead, I'll just call this 2 times 10 to the negative 2 times 10 to the 8th to the negative 2nd. Remember that over here we multiply the exponents. Here we don't multiply though. This is not 2 times negative 2. You never multiply the base times the exponent. Well, whoops. Do you remember how to deal with this? Remember, this really means 1 over 2 squared, right? We talked about negative exponents way back at the beginning of this series of videos. We talked about negative exponents. So based on what we said earlier, this would be the same as this. So that would be 1/4. All right, putting this into scientific notation. Good. So here's our answer. All right, so the same basic method could work if we had a negative exponent here on the outside. We could follow the same basic approach. Please try this calculation. Well, this should have been very easy. It's just 10 to the 15th. The fact that there's no coefficient here doesn't make much difference. We can just use what we have. It's 5 times 3 is 15. If it makes you feel better, you could have written it like this. if you really want to put this in the same scientific notation we've been using all in our earlier problems. 1 to the third is just 1. But it should be fine just to go straight from here to here. There's really no need to stick the number 1 out in front. What's the square root of 9? That's 3. Now, how do you know? How would you test this? Well, you know this is true because 3 times 3 is 9. What's this? Well, you know this is 8. How do you know that? How would you test this? How do you know this is a true statement? It's because 8 times 8 is 64, because 8 squared is 64. What's this? It's 5. How do you know? How would you test this? Well, you know this because 5 squared, 5 times 5 is 25. All right, so I just wanted to review what square roots mean. Hopefully these examples refresh your memory of what a square root is. The square root is the number that if you multiply it by itself, it gives you the number you were trying to take the square root of. It's kind of a mouthful to try to put all of that into words, but hopefully these examples make it clear what we mean when we say we're taking the square root. We're trying to find the number that you could multiply by itself to give the original number that you were trying to find the square root of. Pause the video and see if you can figure out how to do this problem. Well, here we have a new situation that we haven't had to deal with before. What are the math facts we could use here? Well, one thing we could do is this. Do you remember the math fact that told us that this was allowed? We saw earlier that if you have the square root of a product, you can change that into the product of the square roots. Now, square root of 4 is easy. That's just the number 2. What's this? Now, it might not have been obvious to you what this square root was, but I hope you were able to figure it out. In fact, maybe now would be a good time. Try to really figure out what the square root is. What is the square root of 10 to the 6th? Please pause the video and make sure you can actually figure out what the square root of 10 to the 6th is. I don't want you to necessarily rely on any rules. If it's not obvious to you, just take some guesses. Just take some guesses and see what works. Take some guesses and see what works. All right, I hope that you really just took a bunch of guesses and tried to figure out what would work here. Well, what are some guesses we could try? Well, we could try, I don't know, 3. Is 3 the square root of 10 to the 6th? No, because 3 squared doesn't equal 10 to the 6th. How about 4? Is this the square root of 10 to the 6th? No, because 4 squared is not 10 to the 6th. How about, say, 10? Is this the square root of 10 to the 6th? Well, no, because 10 times 10 is 10 squared. It's not 10 to the 6th. How about this? Is this the square root of 10 to the 6th? Well, let's check. What is 10 to the 3rd times 10 to the 3rd? That is 10 to the 6th, right? When you're multiplying two numbers with the same base, you add the exponents. So this really should be now 10 to the 3rd. All right, so everybody who's watching this actually should have been able to figure out what the square root of 10 to the 6th was. We didn't need any rules here or any tricks. We could just do it by trial and error. I hope that you tried that on paper to try to build your intuition for what's going on here. Okay, so I hope that you agree with me now that this is the square root of 4 times 10 to the 6th. In fact, you could check it, right? You could now do 2 times 10 to the 3rd squared using the techniques we went over earlier, and we know that would be 2 squared times 10 to the 3rd squared, which is 4 times 10 to the 6th, and that proves that this really is the square root of 4 times 10 to the 6th. Just like this proves that 8 really is the square root of 64. Pause the video, please, and try this calculation. Well, we would do this. and maybe it might take a little trial and error, but I hope you agree that the square root of 10 to the 12th is 10 to the 6th, because 10 to the 6th times 10 to the 6th clearly is 10 to the 12th. When you're multiplying two numbers with the same base, you would add the exponents. Well, you might be starting to see the pattern here. How do you take the square root of a power of 10? What we're going to always end up doing is just cutting the exponent in half, right? We're always just going to end up cutting the exponent in half. So that's the trick. But even if you forgot that trick, you should be able to figure out the square root by trial and error. But the trick is to cut this exponent in half. Please pause the video and try this problem. This number didn't start in standard scientific notation, but that shouldn't make much difference. We can still work out the square root using our old approach. Square root of 36 is 6. And our trick here, remember, is just to cut this exponent in half. So if I cut this in half, that would end up being 10 to the 9th. And you can check that. 10 to the 9th times 10 to the 9th, that really is 10 to the 18th. In fact, you could do the whole problem and you would see that 6 times 10 to the 9th times 6 times 10 to the 9th, that really is 36 times 10 to the 18th, using the skills we've gone over earlier for multiplying numbers that are in scientific notation. So we were practicing the trick here of cutting the power in half. Notice that we don't take the square root of the number 10 here. We just cut the exponent in half. That turns out to be the right way to get our answer. So again, what are the rules that we're using from the math facts that we went over earlier? We go over these rules. So I guess we're using this key rule here. The square root of a product is equal to the product of the square roots. You can separate out a product into two separate square roots. That really seems to be one of the main things, and we're still using a lot this idea that multiplying two numbers with the same base means you add the exponents. Please pause the video and try this problem. So that's how we would do it. This is the first example I've given you with a negative exponent. But notice that the trick of just cutting the exponent in half still works. You can check that because 10 to the negative 4 times 10 to the negative 4 really is 10 to the negative 8. So this really is the correct answer. Pause the video and try this problem, please. Ten to the negative 6 times 10 to the negative 6 really is 10 to the negative 12th. Now, what did you do over here? Well, I hope that what you said to yourself was that the coefficient only has to be approximate anyway, usually. What matters is getting the right power of 10. So I hope you said to yourself, well, this is pretty close to the square root of 9, which would be 3. And this would be a fine answer, I think. If you're taking a test where you're not allowed to use a calculator, they're not going to expect you to get a precise answer for the square root of 8. So it would be perfectly fine just to approximate it. This is pretty close to the square root of 9, which is 3. All right, so again, we're using our approximation technique. Make sure you get the exact right power of 10, but feel free to approximate when you're working with the coefficients. This is the first example that we've seen like that for working with square roots. Please pause the video and try this problem. I haven't been getting predictions here, so maybe we should try to get a prediction. Well, the main thing is, do we predict the answer will be bigger or smaller than this number? We would predict that it's going to be smaller. It'll still probably be a very big number, but it'll be a smaller number than we started with. So we predict a smaller number than we're starting with. Because when you take the square root of a regular number, it gets smaller, right? For example, the square root of 16 is 4. When you take the square root of a normal number, it gets smaller. So we would predict this is smaller. So then we would end up with this. Ten is half of 20. 10 to the 10th times 10 to the 10th is 10 to the 20th. And here we have to approximate again. Well, probably the closest approximation we could get here would be 2. Square root of 5.2 is pretty close to the square root of 4. So we'll just say this is approximately 2 times 10 to the 10th. That should be close enough. What matters is getting the right power of 10. And we also started talking here about how to get predictions for these types of problems. Normal numbers get smaller when you take their square root. Please pause the video and try to do this problem. Did you think about predicting first? This one is a little bit tricky to predict. You might want to pause the video again and think about how to predict this. Now remember, we're taking the square root now of a fraction. What happens to a fraction when you take its square root? Well, let me give you some examples. What's the square root of 1/4? That must be a half, right? Because 1/2 times 1/2 is a quarter. What's the square root of 1/16? That must be a quarter, right? Because a quarter times a quarter is 1/16. What's the square root of 1/9? That must be 1/3, because 1/3 times 1/3 is 1/9. So what happens to a fraction when you take its square root? It actually gets bigger, doesn't it? Kind of weird. But when you take the square root of a fraction, it actually gets bigger. When you take the square root of a fraction, it gets bigger. So this number should get bigger when we take its square root. To be more precise, I should say, when you take the square root of a fraction that's between 0 and 1, you get a bigger fraction between 0 and 1. When you take the square root of a fraction that's between 0 and 1, you get a bigger fraction that's between 0 and 1. So in these cases, we expect this to be a bigger number. That's our prediction. Well, let's check that here. So we're going to have square root of 6.3 times the square root of 10 to the negative 6. Cut the exponent in half. 10 to the negative 3 times 10 to the negative 3 does equal 10 to the negative 6. And then approximating here, well, I guess you could call this either 2 or 3, right? Because 2 squared is 4, and 3 squared is 9. So it's a matter of taste whether you call this 2 or 3. Maybe if you wanted to, you could call it 2.5. Although that might be more detail than we need, right? We don't really care about the exact coefficient here. What matters is the power of 10. But maybe it might be a good approximation to call this 2.5, because 2 squared is 4 and 3 squared is 9. So here we have our approximate answer. Now, does that match our prediction? Yes, 10 to the negative 3 is bigger than 10 to the negative 6, right? So when you take the square root of a fraction that's between 0 and 1, you get a bigger fraction between 0 and 1. Please pause the video and try this calculation. Okay, well, here you might have run into some difficulty. It's not so easy to take the square root of 10 to the negative 9, is it? If you followed the rules we talked about earlier, you would get 10 to the negative 4.5. And you can see that that's right. That is correct. 10 to the negative 4.5 times 10 to the negative 4.5, that does equal 10 to the negative 9. But that seems kind of weird. We don't usually want a decimal in our exponent. There's nothing wrong about this, but this would not be the answer we were usually looking for. If you're taking a multiple choice test like the MCAT, you can be pretty sure that the answers won't have decimals in them. So this is not a good approach here. So we need some way some trick here. Well, the trick is, the reason why this problem is harder than all the earlier problems is because we don't have an even exponent. What we need to do here is change this exponent so that it's even, right? All the earlier examples were easy to work with because the exponent was even. 10 to the negative 6, 10 to the 20th, 10 to the negative 12, negative 8, 10 to the 18th. All of these had even exponents. The thing that's messing us up here is the odd exponent. So all we need to do here is, before we take the square root, we have to change this so it has a positive exponent. I'm sorry, we have to change this so it has an even exponent. Why did I make this negative 9 then? That's making this unnecessarily difficult. Oh, that's okay. We can handle it. All right, so going on here, you might want to pause the video now that I've given you that hint and see if you can now figure out the problem if you couldn't before. Okay, let's proceed. Actually, I guess before I did anything, I should have gotten my prediction. So I predict here a bigger number, right, for the final answer. As we were discussing a second ago, when you take the square root of a fraction that's between 0 and 1, you get a bigger fraction between 0 and 1. All right, now that we've done that, I'm going to change this over here. So I'm going to change this into 10 to the negative 10th, making this smaller. Therefore, I'm going to make this number bigger. So this should then become 53, right? Did I do that right? Yeah. All right, so we should all agree this is another way to write this answer. And now we have an even exponent. I moved the decimal point one place because I changed the exponent by 1 unit. And now it's pretty easy. (10 to the negative 5th times 10 to the negative 5th is 10 to the negative 10th. And what's the square root of 53? Well, it's approximately 7. Close enough. Because 7 times 7 is 49. So this would be the closest integer to the square root, and that's probably good enough. All right. So that gives us our method. That's our method for doing these problems now. When you're trying to take the square root and the power of 10 is odd, you should rewrite the number so that you have an even power of 10. This is one of the reasons why we've been, one of the many reasons why we've been going over this mechanical method for moving the decimal point when you're doing scientific notation. At this point, you should be getting very comfortable with this idea of using these two arrows and making one number bigger and the other number smaller so that you can take a number that's got one version of scientific notation and write it in a different version. We need that. Now you can see why we need this mechanical method that helps us to avoid careless mistakes, because that's a technique that comes up a lot. All right, so please study this example so you can convince yourself that you could have gotten this problem right using that technique. Please pause the video and try this problem. I hope that first you predicted, and your prediction should have been a smaller number. because when you take the square root of a regular number, it gets smaller. Notice, when you take the square root of a regular number, it gets smaller. But when you take the square root of a fraction that's between 0 and 1, it gets bigger. You might want to compare this example here with this example here. Here's the two things that can happen when you take square roots. At least this is what happens when you take the square root of a positive number. Normal numbers that are bigger than 1 get smaller when you take their square root. Fractions that are less than 1 get bigger when you take their square root. Let's see here then. The first thing I have to do is rewrite this so that we have an even power of 10. So I believe this is the way to do that. 13 changes into a 12, so this number gets bigger. Moving the decimal point over one place. So that gives us now this. So let's see here. This is, you could either say this is 6 or 7. 6 times 6 is 36. 7 times 7 is 49. I guess 6 seems a little bit closer. If you wanted to, you could call this maybe 6.5 or so. So this is 6 times 10 to the 6th. Maybe 6.5 times 10 to the 6th might be a closer approximation. Okay, so here we go. Here's our technique. Something you might wonder is, why did I change this to 10 to the 12th and not 10 to the 14th? Well, I could have done that. I could have changed this to 10 to the 14th. And then the number 4 would have to get smaller, right? So it would change to 0.4. So we could have ended up trying to do this calculation. Well, this is fine. It's just it's a little bit of a pain to try to take the square root of 0.4. So you could do this, but since you'd be doing this without a calculator, I think it's a lot better to end up with this number not being a decimal. So the point is, when you're using this trick, it's better to make the power of 10 smaller so you can make the numerical portion bigger because it's easier to take the square root of this type of number than it is to take the square root of this type of number. You could do this, but this would now be kind of a pain. Okay, so we'll stick to this approach. Please pause the video and do this calculation. Well, we predict a smaller number as our answer because we're taking the square root of a regular big number. I need to get this to be an even exponent, so it's easier to take the square root. So I can do that like this. (10 to the 13 times 10 to the 13 is 10 to the 26th, because you would add the exponents. And let's see, what's the square root of 72? Well, 8 times 8 is 64. 9 times 9 is 81. 8 times 8 is 64. 9 times 9 is 81. So, I don't know, maybe we could call it 8.5, about. Somewhere between 8 and 9. The square root is somewhere between 8 and 9. So this is hopefully a good enough approximation. And we did end up with a smaller number than we started with, as we would have predicted. Please pause the video and try to do this square root. Well, first of all, we would predict a bigger number. Because now, remember, this is, what is this? What are we trying to take the square root of? We're trying to take a square root of a little fraction. If you take the square root of a fraction that's between 0 and 1, you get a bigger fraction. I need to adjust so that I have an even exponent to make it easier to take the square root. Negative 18 is smaller than negative 17, so I need to make this part bigger. Square root of 32. Let's see, 5 squared is 25, and 6 squared is 36. So it's between 5 and 6. Maybe I'll call it 5.5. Now, why did I change this into 10 to the negative 18th? Why didn't I change it into 10 to the negative 16th? Well, if you'd wanted to, you could have changed to 10 to the negative 16th, making this part bigger than 10 to the negative 17th. Then you'd have to make this smaller, and you'd end up trying to do this square root. Well, this is kind of a pain trying to take the square root of a decimal. So if you started off this way, it probably would be better to retrace your steps and do it this way. So in general, I guess the trick is to reduce the power of 10. We reduce the power of 10. That gives us a bigger coefficient, because the danger is, and it's pretty easy to take the square root of numbers that are bigger than 1. It's hard to take the square root of numbers that are less than 1. Pause the video and try this calculation, please. Well, we predict a bigger number than we started with inside the square root, because we're taking the square root of a fraction that's between 0 and 1. Let's see, we're going to make this exponent smaller so that we get an even exponent. Then we make this bigger. Remember, it would be a mistake probably to change this into 10 to the negative second. If you change this into 10 to the negative second, the problem then is that you'd end up with a numerical portion that's hard to take the square root of. So let's see, here we would have, let's see, 7 squared is 49, so this is pretty close to 7. Oh, I usually write it like this. Okay, so then we would end up with this as our answer, and this is a bigger number than we started with. Do you agree this is a bigger number than we started with? Yeah, because 10 to the negative 2 is bigger than 10 to the negative 3. So that does match our prediction. Okay, so let's see. I think that about covers most of those basic types of calculations. So I guess now we just have to review. Let's see here. Please pause the video and try this calculation. Now we predict a smaller number. When we multiply a fraction by a fraction, we get a smaller fraction. So here's our answer, and this is smaller than we started with. Please pause the video and try this calculation. Well, our prediction, we're dividing, the number on top is the smaller number. The number on top is the smaller number. So, and this number is actually quite a bit bigger, so we should predict a very small answer. Predict a very small answer, because we're taking a number and dividing it by something that's much bigger. Dividing by something that's much bigger gives you a very small answer. So this would be 5, 6 times 10 to the negative 12th over 10 to the negative 3rd. Be very careful with the exponents here. Negative 12 minus negative 3. That's negative 12 plus 3, or negative 9. And we can already see that we did end up with a very small answer. Not as small as it turns out as the original numerator, but still a small answer. And then we have to do 5 into 6. Well, it might be good enough just to say that's approximately 1. You could just say this is approximately 10 to the negative 9th. That might be good enough. But if you want to be a little bit more in detail, you could call that. Let's see. So this comes out to be 0.8. Or 8 times 10 to the negative 10th here as our final answer. Again, you wouldn't have been too far off if you just called this the number 1 times 10 to the negative 9th. That's pretty close to 8 times 10 to the negative 10th. Very often it's fine just to approximate this numerical coefficient. Pause the video and try this calculation, please. Well, you should have predicted that we would have a very small answer. Because the bottom here is much bigger than the top of the fraction. So we get a very small answer. I hope you really are trying to get these predictions. That's a really good way for building your intuition for what scientific notation means. So let's see, how could we write this? Well, you might feel more comfortable if you rewrote the top of the fraction like this. I think this is a trick we've seen a couple of times. Then we could write things like this. 7 minus 15 is negative 8. As we predicted, we're getting a very small answer. And 1/5 is 0.2. You might already know that. 1/5 is 0.2, or we can prove it over here. So now we can rewrite this in standard scientific notation. So here's our answer, 2 times 10 to the negative 9th. Please pause the video and try this calculation. Well, we predict a bigger number. Fractions that are between 0 and 1 get bigger when you take their square root. Now, in this case, we were fortunate. The power of 10 is already even, so we don't have to adjust the number at all. So we already have an even power of 10. 10 to the negative 6 times 10 to the negative 6 is 10 to the negative 12. What's the square root of 7.7? Well, let's see. 2 squared is 4, and 3 squared is 9, so this is probably closer to 3 than to 2. So this is only an approximation, but that should be a good enough approximation. It's approximately 3 times 10 to the negative 6. We did end up with a bigger number as our answer. Pause the video and try this calculation, please. Well, let's see. We would get this. This. I forgot to get a prediction. I hope you didn't. You should have predicted that the answer would be bigger. When you square a regular number, it gets bigger. When we take the square of a regular number, it gets bigger. So we would have predicted that this would be bigger than we started with, and that would match up. Please pause the video and try this problem. All right, here I have a negative number. You might have tried to predict here, but I'm not going to worry about the prediction too much here. I'm just going to go ahead and do the calculation. So we're going to have negative 3 to the 4th times 10 squared to the 4th. Well, this would be negative 3 times negative 3 times negative 3 times negative 3. Can you see this is definitely going to come out even, right? This is going to be 9 times 9, or 81. And here we multiply the exponents. Put it into standard scientific notation. Here's our answer. pause the video and try this calculation. Well, we would predict here a very big answer. Because the number on top is very big and the number on the bottom is very small. So the bottom is going to go into the top many times. Be careful with the negative numbers here. 17 minus 5 is 22. As we predicted, a very big answer. And 9 goes into 83. Well, we could just approximate and just say it's 9, right? That's pretty close. 9 times 10 to the 22nd. So that might be a good enough approximation. Or if you wanted to be a little bit more precise, we can call it 9.2. So here we would have that answer. Please rewrite this number in regular notation. Please pause the video and write this number in regular notation. Well, let's see here. We're going to change the 10 to the 5th into the number 1, which would make it smaller. So we need to make the other portion bigger, which would involve moving the decimal point to the right 5 times. So that would give us 1, 2, 3, 4, 5. And then our final answer would be 8, 4, 5, 1, 2, 3, and 3 zeros. So here's how we would write this number in standard notation. What I'm just trying to do here is just give you a bunch of problems to let you practice all the various techniques we've gone over in this video series so far. Remember, it's not enough to kind of sort of know how to do these problems. These problems need to be boringly easy for you so that they don't slow you down and so that you don't make careless mistakes in the middle of a harder and more complicated problem. So this is a very important part of the videos here where we just get a bunch of practice and make sure that we've really reached the point where these problems are boringly easy for us. Please pause the video and do this subtraction. Well, to do a subtraction, we need like terms, so I'm going to change the smaller term so that it's similar to the bigger term. So that's how we would do that. Now we have like terms, so we have 8 minus 0.3. And here's how we do that subtraction without a calculator. We have to borrow. When you're subtracting, you have to line up the decimal points. Okay, and here's our answer. Well, I guess something I forgot to do here was get a prediction. Did you remember to try to predict here? What should have been your prediction? Your prediction should have been that the answer would be not that much smaller than 8 times 10 to the 5th. We should have predicted the answer would be close, but a little smaller than 8 times 10 to the 5th, because we're subtracting a substantially smaller number from a substantially bigger number. There's not a huge difference between these, But here we have 10 to the 5th power, and here we have 10 to the 4th power. So this number is about 1 order of magnitude bigger than this one. This number is about 10 times bigger than this one. Not exactly, but it's in the range of 10 times bigger. So notice that subtracting this smaller number didn't have that much impact on the final answer. It had an impact, but not too much. So that's how we could have predicted this. Remember that if you wanted to, instead of changing this number so that it's expressed as 10 to the 5th, you could have changed this number so it's expressed as 10 to the 4th. That would be fine. The problem with that then, though, is then I think you would end up with an extra step at the end where you had to change your answer into standard scientific notation. If you subtract these when they're both looking like 10 to the 4th, the answer doesn't come out in standard scientific notation, and there would be one more step. So you usually save a little time if you alter the smaller number, because we know the answer is going to end up being pretty similar to the bigger number, which is already in standard scientific notation, if that made any sense. Okay. Please change this number into standard scientific notation. Change this number into standard scientific notation. I hope you gave that a shot. You should be able to predict, should we predict on these problems? I don't know. You should be able to predict right off the bat that it's going to end up involving a negative power of 10 because it's a small fraction. We should know it's going to end up involving a negative power of 10 because it's a small fraction. That would be our prediction. So let's see. We have to make this portion between 1 and 10. That would involve making the numerical portion bigger than we started. So then the other portion here should be getting smaller to balance, so we need a negative power of 10, so that this will be smaller than 1. And how many times did we move the decimal point? Once, twice, 3 times, 4 times, 5 times, 6 times. 1, 2, 3, 4, 5. We moved it 6 times. So we end up with this answer, and we did indeed match our prediction and get a negative exponent of 10. Please do this calculation. Predict. What would we predict? We predict a smaller number. When you take the square root of a regular number like this, you get a smaller number. So we predict a smaller number as our answer. This is a relatively easy problem because we already have an even power of 10. Those are the numbers that are relatively easy to take the square root of. Square root here is just half because 10 to the 6 times 10 to the 6 is 10 to the 12th. And we've talked about how the coefficient doesn't matter that much, so I'll just approximate its square root. Well, it's maybe around 2, a little bit more than 2. Closer to 2 than 3, though, it seems like. 2 squared is 4, so that's not too far off. So if you wanted to, you might say it's 2.2 or something. I don't know. Anyway, that should be a good enough approximation. Let's see how we're doing here. Please pause the video and do this calculation. Let's see. First of all, I'm going to try to get a prediction. So here's our prediction. We're adding a substantially smaller number to a substantially bigger number. This is about 10 times smaller than this number, so adding shouldn't make that much difference. Now, it's not exactly 10 times smaller. It's just kind of in that ballpark because the coefficients are not the same. All right, so now let's see. We need to change these so they have like terms, and we've learned it's more efficient to change the smaller number. I want to change this to be 10 to the 9th, so it matches this 10 to the 9th. That involved increasing the exponent by 1. So I should make the numerical portion smaller to balance, and that involves moving the decimal point one place to the left. By the way, now that we've actually done that, you can see, as I was saying earlier, that this number is substantially smaller than this number. You can see this one really is substantially smaller than this one. It's not literally 10 times smaller because the coefficients originally were not the same, but it's vaguely in that ballpark. Vaguely in that ballpark of 10 times smaller. Okay, so anyway, we'd have here 4.2 plus 0.84. You have to line up the decimal points. Here we've got a carry. 2 plus 8 is 10. So we end up with 5.04 times 10 to the 9th. So it's somewhat bigger than this number. Not that much bigger. Not too much bigger than the number that we originally started with. That matches our prediction. Remember again that if you're taking maybe a standardized test like the MCAT, it's very likely not even necessary to do this addition with this much precision. It might be good enough to look at these and say, well, this is about 4.2 plus 0.8, so it'll be about 5, because there's probably only going to be one choice that's in the ballpark of 5 times 10 to the 9th. So on a standardized test, you could often get away by approximating the coefficient, the numerical portion, rather than doing the calculation in precise detail here. Please pause the video and do this calculation. Should we try to predict here? I don't know. What could we predict? Well, we're taking a small fraction of a very big number. A small fraction of a very big number. So is the answer still going to be pretty big? Well, this number is a pretty small fraction, but this number is really big. I don't know quite how to put this, but the bigness of this number outweighs the smallness of this number. So if you take a relatively small fraction of a really, really big number, I suppose you would still end up with a big number. So I don't know. So that's a kind of a vague prediction here. So we would predict still a pretty big answer, but smaller, but substantially smaller than we started with. A pretty big answer, but substantially smaller than we started with. So maybe in this case it is getting a little confusing to try to predict it, but maybe not. Maybe it helps us to try to think about the prediction even here to build our intuition. Okay, so let's see, doing the calculation. Remember that when you're multiplying, you don't need like terms. When you're multiplying, you don't need like terms, and we can just rewrite the multiplication like this. It doesn't matter what order we do the multiplication in. The parentheses are not making any difference here. 5 times 8 is 40. And when you multiply two numbers with the same base, you add the exponents. 12 plus -3 is 9. And then we would put this in standard scientific notation. We move the decimal place once here, so we change this by 1 unit and we make it bigger to balance out this change. So here's our answer, 4 times 10 to the 10th. And this kind of matches our prediction. So we did end up with something that's quite a bit smaller than we started with, but still a pretty big number. All right, there we go. So please pause the video and try this calculation. Let's see, what could we predict here? Well, we're taking a pretty small fraction and taking a much smaller fraction of that. So we're taking a tiny fraction of a tiny fraction, so we should end up with something that's small. Notice the answer should be much smaller than even the smaller number here. Maybe I'll put it this way. We're taking a fraction of this fraction. So we're going to end up with something that's a lot smaller even than 8.7 times 10 to the negative 11. So we're going to get a very small answer, something that's actually much smaller than 8.7 times 10 to the negative 11th. I don't feel like writing that down. But anyway, also maybe here we should start practicing an approximation technique too. How would we approximate this? Well, approximately this is going to be about 10 to the negative 4 times now, this is a pretty big coefficient. So this is actually closer to 10 to the negative 10 than to 10 to the negative 11th, right? This is like because 8.7 is closer to 10 than to 1. So approximately this is going to come out to be about 10 to the negative 14th. About 10 to the negative 14th. And you can see it does match our prediction, substantially smaller than even this small fraction here. Then we could do the actual calculation. So let's see here. So that would be, the actual calculation would give us 3.2 times 8.7 times 10 to the negative 4 times 10 to the negative 11th. So we get 10 to the negative 15 here. And you could do this calculation precisely, but let's just approximate it. This is about 3 times 9, or about 27. And then putting that in standard scientific notation, not too far off from our prediction. You can see that the powers of 10 are the most important thing in getting the right answer. Please pause the video and try this calculation. Let's see, our prediction here would be slightly smaller than 8.2 times 10 to the negative 4. We're subtracting a substantially smaller number from 8.2 times 10 to the negative 4, so it should be smaller than 8.2 times 10 to the negative 4, but not that much smaller. Okay. In fact, if we were just going to use a approximation technique here, can we approximate it? I guess on these subtractions, that approximation technique's not quite such a good idea. All right, but we expect it to be not too far from 8.2 times 10 to the negative 4. Let's see here. This would be... I'll change this. Now you can see why it's not going to be that much smaller than 8.2. All right, and you could just approximate this as 8.2 minus 0.6, say. We've got to borrow if we're going to do it exactly. 11 minus 5 is 6. So we ended up with 7.61 times 10 to the negative 4th. I think that matched our prediction of being not too much smaller than 8.2 times 10 to the negative 4th. That approximation trick that I used on the previous problem, that doesn't work so well here because if you approximate these too much, you don't, let's see, this could be approximated as, let's see, so 8.2 times 10 to the negative 4. Well, that's about 10 times 10 to the negative 4, or 10 to the negative 3, and here we had 5.9 times 10 to the negative 5, so that's not far from 10 times 10 to the negative 5, and then that would give you 10 to the negative 4. So you would end up with this approximation, but this is not so easy to do. You can't really subtract these directly unless you have like terms. The one thing you could say is, again, this is going to be just a little smaller than 10 to the negative 3. The answer is going to be a little smaller than 10 to the negative 3, which is, we did get something that's not too much smaller than 10 to the negative 3 over here. Because 10 times 10 to the negative 4 would equal 10 to the negative 3. So you can see this was somewhat smaller than 10 to the negative 3. All right, so when we're multiplying numbers, the technique of just ignoring the coefficients and just focusing on the powers of 10 is actually quite effective as an approximation technique. When you're adding or subtracting, there's not as much point to using that approximation technique. Please pause the video and change this number into standard scientific notation. Please change this into standard scientific notation. That was a trick question. It's already in standard scientific notation. Just a little trick question there. This is already in standard scientific notation, so we don't have to do anything to it. It's already in the form that I was asking you for. Please pause the video and take this square root. Let's see, what's our prediction? Well, we predict a bigger number, right? We predict a bigger number here. Because when you take the square root of a fraction that's between 0 and 1, as we saw earlier, you get a bigger fraction that's between 0 and 1. Just like the square root of 1/4 is 1/2, a bigger fraction. All right, on these problems, there's not too much point using any, there's not much point ignoring the coefficient and just focusing on the power of 10. So I'll just go ahead and say we need to change this number. Let's see here. So I need to make this into -8 or -6. I'd like this number to get bigger, so it's still bigger than 1, so I'm going to try to make this smaller. All right, so I'm going to make this into 10 to the -8 so that it's even. And since I made it 1 unit smaller, I need to move the decimal point one place over here. And then this is approximately 9. That'll be probably a good enough approximation. And this is 10 to the -4. So we did end up with a number that's bigger than the number that we started with. What if you had changed this into 10 to the -6? That's also even. Well, if you had done that, you would have ended up with 0.85 times 10 to the -6. And that's a little bit of a pain to try to take the square root of a decimal. So it would be better off, we've seen, it's better off to make the power of 10 1 unit smaller, so the coefficient gets 1 unit bigger so that it's still bigger than 1 and it's relatively easy to take the square root. Please pause the video and do this calculation. Let's see here. So what would we predict about this? It's a little bit of a pain to try to predict with all the negative numbers and everything here. I guess you would predict, we have one negative number and one positive number, so we would predict a negative answer. We would predict a negative answer, and its absolute value should still be pretty big. It's a little bit of a pain to try to get a prediction here. All right, so let's see here. We could rewrite this as -5 times 4 times 10 to the -3 times 10 to the 8th. -5 times 4 is -20th. -3 plus 8 is +5. And then we need to put this in standard scientific notation. So what we want here is we want this coefficient, the numerical portion here, to be between 1 and 10. Or I suppose with a negative sign between -1 and -10. So I change this into the number 2. But I guess the best thing to do here to avoid getting confused is forget about the negative. If you just focus on the 20, changing 20 into 2 makes this numerical portion smaller. So we should make this portion bigger. I moved the decimal point one place here, so I'll make this 1 unit bigger. I'm putting the negative off to the side for a second so that we can say if you change 20 into 2, that makes it smaller. So to balance that, you need to make this part bigger, and then we can put the negative sign back in. So while I was adjusting into standard scientific notation, I pulled the negative sign out of the number, so to speak. so that it wouldn't confuse the issue of whether the coefficients were getting bigger or smaller. But now that the numerical portion is written in standard scientific notation, we can put the negative sign back in, just like so. And here's our answer. Remember the algebra fact, negative xy is just the same as negative x times y. So we just used that fact here. And here's our answer. So we haven't done very many problems using negative coefficients. We've done a lot of problems with negative exponents. We've done many problems with negative exponents, but not much work with negative coefficients. Well, if you had trouble with that, here's an example of how to work with a negative coefficient. By the way, so now, is this a negative number? Yes, this really is a negative number. A negative exponent wouldn't be enough to make you into a negative number, but a negative coefficient definitely does make the number negative. Please pause the video and write this number in standard scientific notation. Please write this number in standard scientific notation. Well, it's kind of a trick question. It pretty much it already is in scientific notation. You could just say this is the answer. Or to make it a little bit more standard, you could stick this number 1 out in front so that it has a numerical coefficient. We know that multiplying by 1 doesn't change something. So you could say it's already in standard notation, or you could rewrite it like this. Please try this calculation. I hope that you're still pausing the video and trying all of these on paper. If you're finding this boring, outstanding. That means that we're succeeding. The goal here is to get to the point where these problems are boringly easy and we never make careless mistakes. That's also important. So by the way, if you're getting about, say, 90% of these right, that's terrible. 90% is not good enough. You should be getting 100% of these right easily and boringly. If you're still making 10% careless mistakes, that's not good at all. You don't want to make careless mistakes on these parts of a harder problem. So be tough on yourself. Try to have a systematic method where you write down the steps so that you almost never make careless mistakes on these problems. That's one of the reasons why I'm giving you so many examples here, to give you the opportunity to work those careless mistakes out of your system. Now, when you're subtracting two numbers, they have to have the same, they have to have like terms. But these do have like terms, the same exponent, so we can just subtract them directly. This is just 5 times 10 to the 4th. This is a lot like 8x minus 3x, right? What would that be? It's just 5x. So we used a pretty similar trick up here. Okay, so there we are. There's our answer. Please do this calculation. Now, some people get flummoxed by this, but I think we've seen what to do in this situation. This number over here is confusing because it doesn't have a coefficient. Well, here's a trick we've used a couple of times. We can give it a coefficient of 1. That doesn't change that term. And then this just becomes 9 times 10 to the 4th. So here's our answer. In this case, we had like terms, so we could just add directly. Please pause the video and try this calculation. Here we have to make these into like terms. We can kind of predict the answer will be slightly bigger than 7 times 10 to the negative 2. This is the bigger number. This is substantially smaller. So the answer should be just somewhat bigger than 7 times 10 to the negative 2, not too much bigger. So I need to change this into 10 to the negative 2. That involved making this bigger, so this should get smaller. So here's the addition we have to do. And now you can see this number really is substantially smaller than this one, and we just end up with 7.8 times 10 to the negative 2. So the answer is slightly bigger than 7 times 10 to the negative 2, as we predicted. Remember again, if you'd wanted to, instead of changing this into 10 to the negative 2, you could have changed this term into 10 to the negative 3. You could have changed this into 10 to the negative 3, but then your original answer would not come out in standard scientific notation, and you'd need another step. Please rewrite this as an ordinary number. Rewrite this as an ordinary number. Oh, we'll change the 10 to the negative 1 into just the ordinary number 1. Remember that trick? That made that get bigger, so the other part will get smaller. That tells me that we're moving the decimal point one place to the left, in case that wasn't obvious. All right, I hope that was very easy for you. That should have been boringly easy for you. I'm getting confused here. What was my answer? 0.878. I just wanted to make sure you're very familiar with this, our basic trick here, that when we put something in normal notation, we imagine we're taking out the power, the 10 to a power, and replacing it with the number 1. We focus on whether that part of the answer is getting bigger or smaller, and that tells us which way to move the decimal point. So that should be a technique that's very boringly easy for you at this point. If it's not, it's important to go back and do a lot of practice with the examples that we had done earlier. Please write this number in standard scientific notation. Write this in standard scientific notation. Well, let's see. I have to make the numerical portion between 1 and 10, which would involve making it smaller. So this part has to get bigger. Remember, I'm comparing now this to the number 1. So this should be 10 to the first power. So we're taking out the number 1 and replacing it with 10 to a power, and we know this should be bigger. To balance out this is getting smaller. So here's our answer. 8.9 times 10 to the first power, or just 8.9 times 10. And again, hopefully this is a technique that was very boringly easy for you, that didn't give you much trouble. Okay, well, I'm certainly getting pretty bored at this point, so I'm not going to make up any more examples. I really shouldn't have to at this point. There's a whole bunch of examples now, hopefully in your notes or in the videos. So remember, at this point, all of these types of problems should be boringly easy, and you should be making almost no careless mistakes on them. What types of problems am I talking about? Well, I'm talking about taking regular numbers and turning them into scientific notation. I'm talking about taking scientific notation and rewriting it in regular notation. I'm talking about adding numbers that are in scientific notation, subtracting, multiplying, dividing numbers that are in scientific notation, raising numbers in scientific notation to powers, taking the square root of numbers that are in scientific notation. All of those should be boringly easy. Hopefully you haven't made any careless mistakes for quite a while now here in this series of videos. If you haven't gotten to that point yet where these problems are boringly easy, well, just go back and do the problems again. I think you have enough problems now that if you keep doing them over and over from this series of videos, you should get to the point where these problems are boringly easy and you almost never make careless mistakes. If you get really bored with these problems, you can always make up problems of your own, right? Just make up some random numbers. make up a random problem, and for example, you could make up two random numbers and try to add or subtract or multiply or divide them. And then you can always check your answer on your calculator, right? You can always check your answer on your calculator to make sure that you actually did that problem correctly. So I think you have the tools now to make sure that you really master this material. Okay. All right, so maybe it's about time to call it a day with this series of videos. You can see that the video series ended up being on the long side, it might seem like. But if you've stuck with it and you've learned this material, I think that's time well spent. The point is that scientific notation is a tool that you're probably going to use many, many times in the rest of your academic career, and maybe in practical situations as well. If you're going to be taking any more science classes, like physics or chemistry, for example, pretty much any class that you take, like physics or chemistry, you're going to be using scientific notation over and over. So you want to make sure that you absolutely mastered that skill. So that's why I think it's worth taking a few hours to really get on top of this, because as I said, when you're taking, say, a physics or a chemistry class or some other class that involves scientific notation, you're not going to have many problems that are just like the ones I've been giving you, right? The instructor is not just going to give you problems like the ones we've been talking about, but they are going to be giving you problems that involve as a step working with scientific notation. And you don't want to get bogged down on that step. You want those little parts of the problem to be boringly easy. So I hope that you've achieved that goal by working through these videos, or that you'll keep working on this so that you get to the point where these are boringly easy. Now also, the main thing that this last portion of this video was about was how to do calculations with scientific notation, how to add, subtract, multiply, divide, raise to a power, or take the root if you're doing a calculation with scientific notation. And remember, like, who's it most important to have that skill? Well, first of all, some of you may be taking physics or chemistry courses where you're not allowed to use a calculator on the test. And in that case, it could definitely be to your advantage to be able to do these calculations without a calculator. But probably the most important group of people that need those calculation skills are, as I've mentioned before, people preparing for standardized tests like the MCAT. The MCAT doesn't let you use a calculator, and scientific notation is a very important part of working through the calculations on the MCAT. So that's, again, one of the reasons why I've given you so many practice problems here, and I've emphasized the importance of being able to do these problems easily without making careless mistakes. When you're taking a standardized test, you're going to feel like you're under a lot of pressure, you're under harsh time pressure. Unless you know these skills really well, it's really easy to make mistakes. So one of the things that you can do to help yourself improve your score if you're preparing for a standardized test is really master this material we were just going over on how to do calculations with scientific notation without using a calculator. So if you are preparing for a standardized test, I really recommend keep working on this over and over until you've mastered how to do the calculations, until you don't make careless mistakes, and then keep revisiting the material to make sure you don't forget how to do these things. When you're in the middle of the test, you don't want to be stymied just because you don't know just because you can't remember how to take the square root, say, of something that's in scientific notation. Also, for standardized tests, we've emphasized that for standardized tests, oftentimes all you need to do is approximate your answer. So that's something to keep remembering. You don't necessarily need an exact answer. Maybe just getting the right power of 10 might be good enough. So that's another lesson to make sure that you remember as you continue preparing for whatever test you're going to take. Also, I've been also trying to help you have a better understanding of what scientific notation means. We've talked about predicting the answer and estimating the answer and trying to understand better what scientific notation means. That way, hopefully, when you're using scientific notation in a physics or chemistry class or some other type of science class or some other class where you're using scientific notation, hopefully now the numbers in scientific notation are not just going to be kinds of, like, I don't know, vague, indecipherable objects that you're just blindly manipulating. Hopefully now you have a feel for what those numbers really mean. and that should give you, again, better intuition and better confidence when you're using this material. Okay, so the point here is scientific notation is a very important tool in many classes and subjects. So it's well worth the time that you've put in to try to master this material. And if you haven't mastered it yet, keep working on this until you do have it down. Also remember, even if you've pretty much got this material down, it would be easy to forget it pretty quickly, right? So try to keep revisiting this every once in a while to make sure that you don't lose the progress that you made when you were working through these videos. Make sure that you've mastered this material and try to revisit this material from time to time to make sure that you don't lose all the progress that you've made. Okay, thanks, and good luck using scientific notation. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you.